Hello, everyone. What is happening? Welcome to Apply. This is pretty exciting. I think we have got an incredible day planned ahead of us. It's nice to see some familiar faces in here. And looks like this event is shaping up to be one of the best conferences of the season, potentially of the year. We're glad to have everyone with us, but before we start, Tecton has asked me to read this disclaimer, so I'm just going to go ahead and do that and get it out of the way real fast. Tecton is pleased to have you joining the event. Before we start, we would like to take a moment and stress that the statements, thoughts, and opinions of Dimitrios Brinkman in no way reflect the opinions of Tecton AI or the partners. In no way does Tecton assume any legal responsibility for the actions of Dimitrios Brinkman. All right, now that that is out of the way, thanks for the vote of confidence there, guys. I am Dimitrios Brinkman, in case you were wondering, and I want to say a few things before this whole event kicks off. We have a Slack channel. I want to remind everyone that the Slack channel is where all the banter and all of the great insights are going to be shared. So I know it's tempting to put something in the chat here on Zoom if you're with us live in Zoom, but go ahead and check out the link that should be in the Zoom chat right now and join us in Slack if you're not in it already. And you also can use Twitter and any kind of social like LinkedIn to let the world know about this conference. If you're having a great time here, we encourage you to let people know, and hopefully it will spread and they will be getting all the insights that you're learning here. You can post with the hashtag, I think you saw it if you were here earlier, you can post with the hashtag ApplyConf or just MLOps or machine learning, whatever you feel is right. Or don't post anything, that's fine. No pressure. All right, now let's thank Tecton for this incredible event. We also would like to thank all of the partners who are here with us today. There's some incredible folks that have joined us, and if you did not see the slide, we've got people like Algorithmia, Arise, Converge.io, Fiddler, Monte Carlo, Notable, Provectus, Redis Labs. Oh, there's so many. We've got slides. You'll see those slides coming up. And the last thing that I will mention is, just like in any event, we would appreciate it if you be cool and you follow the code of conduct. As with in-person events, you want to be nice and have fun. So I think that is about all the announcements that I have. Now we are going to start getting into the actual event, as we say. So before we get into the event, I will just take one moment to mention that, in case you didn't know, I'm coming from the MLOps community, and that is a community that we've started for MLOps specifically. And so if you would like to join and learn about the MLOps movement that is happening, please come and check out our MLOps community Slack, which you will be able to find in the chat, and you can learn from a lot of smart people. There are quite a few incredible beings that are in that Slack, and they are very generous with their knowledge, their time, their information, and they help out the rest of us, because I'm sure that we all know this is a pretty wild space right now. And so we are demystifying that in a way. All right. Now, if you have any questions or comments, throw them in the chat, in the Slack, I should say, and I will mention that the first talk is going to be from Mike Del Balso and Willem Pinar, who you may have heard of. Mike is the founder and CEO, one of the co-founders, I should say, and CEO of Tecton, and Willem Pinar is the co-founder or creator of Feast. And you may have heard that Feast and Tecton have joined forces recently in a way that is pretty exciting. So this video, and you actually, so Mike and Willem are going to be available, and as hopefully every speaker is available in the chat. So jump in the chat and you'll be able to talk with all of the speakers after their talk. And you can ask them questions, you can get more insights from them. Should be a good time. Now, the other thing that I will mention is that there is a selfie contest going on. And if you're in the Slack, this is just a side note. Sorry, I totally derailed from this, but I forgot to mention it in the beginning. And I see there's more people joining right now. So I will mention, my job is to make this hopefully be a little bit more fun in between all of the talks, and we can take our minds off of the deep knowledge learning that we have. So there is a selfie contest, and the best selfies will get some swag at the end of the day. So if you would like, please put in either on Twitter or LinkedIn and put it with the hashtag applied selfie. And if you don't want to be so public about it, you can put it into the funny channel that is in the Slack that we've got for this conference. And yeah, you might be able to see that I'm wearing a crazy shirt. So if you have costumes, that's +1 for the selfie. And if you have pets, that is +1 also for the selfie. So feel free to snap a selfie, get entered to win in some swag giveaway. And we're going to be choosing the best ones at the end of the day. And that should be a lot of fun. As they're coming in, we'll be showing some of them and spotlighting some of you all with the good selfies. So it's an easy way to jump on the bandwagon and get some free stuff. All right. There we go. Now let me jump back into introducing Mike and Willem. And so before I got horribly derailed, let's talk about Mike and Willem. If you missed, I said it. Mike, co-founder of Tecton. Willem, co-creator of Feast. Willem, before he was working at Tecton, he was the data science platform lead at Gojek. And Mike, before he was working or creating Tecton, he was working at Uber. And I'm excited for this. This is the way that we're kicking off the conference. So it's going to be a good one. Now, last but not least, as I mentioned, if you want to talk with Mike and Willem after this talk, you can do so in Slack. And that is about it. I think we are queuing it up. Mike and Willem, to the stage if you can.
Hello, and welcome to the Apply Conference. I'm Mike. I'm the CEO of Tecton, and we're hosting Apply. We hope that you guys like it. It's the first time running Apply, and so if it goes well, we'll do it again. Maybe in 6 months, maybe a year from now. You know, what is this conference about? It's about all the data engineering challenges that we have when putting machine learning into production, when doing applied machine learning. And, you know, this is a really huge space. There's a variety of different problems, and the talks in this conference will be deep dives into different sub-problems. The idea of the conference is to just bring people together and talk about some of the solutions, the things that they've built that have worked or that haven't worked. And hopefully by participating, you'll get some great ideas that you can bring back to your own teams. Okay, we're going to talk about productionizing machine learning with feature stores. Also joining me in this talk is Willem, who's the creator of Feast, an open source feature store, and a tech lead at Tecton. So where did feature stores come from? Well, we worked on and built a machine learning platform at Uber called Michelangelo. That platform, supported all the machine learning that runs in production at Uber, thousands of real-time models like fraud detection systems, ETAs, stuff like that. And this platform is really three parts. There's a feature store layer, there's a model management layer, and then there's this observability model monitoring layer. And the feature store was really like a central hub for managing the data flows in the ML application, and allowed teams to iterate really quickly on features, to transform data from raw data into ML features and deploy them to production quickly. And this feature store kind of became the foundation for all the ML systems at Uber. Today, feature stores are a whole category. We left Uber to create Tekton. Tekton is a fully managed enterprise feature store. Feast is another great feature store option. It's an open source feature store. Today, we're going to talk a little bit about both of these. There's a new release for Feast that we're going to talk about and show a demo of at the end of this presentation. But overall, today, we're going to talk about why it's so hard to productionize machine learning and how a feature store helps with a lot of these data engineering challenges. We're also going to talk about what's within a feature store, how do they work, and how are they relevant for core ML ops workflows. And then at the end, we have an announcement of a new release of Feast, and we're going to talk about the key design principles and show a nice demo of it. So let's talk about why productionizing machine learning is so hard on modern data stacks. First, let's talk about just what defines modern data stacks. Modern data stacks are really built around these cloud native data platforms. So this is your cloud data warehouse or a next generation data lake. And they have really risen in popularity dramatically over the past few years. We love our data warehouses. And they're great because the modern data platforms finally offering teams good ways to centralize their business data, good ways to reliably clean that data and aggregate it into useful formats, refine it into much higher value versions of that data that can be used for analytics, and share that team, that data with their team for analytic purposes. So these systems have really enabled analytics to be self-serve, to be near zero maintenance, and to be really scalable. But more than that, they've essentially revolutionized the analyst role, right? But they unlocked insane productivity for them. But what about machine learning? What have they done for ML? Not the exact same thing. So let's just look at what is required to build a machine learning system. So with ML, of course, we have to train our model. And so we can do that with a data science environment, say a Jupyter notebook and an ML framework. But it's not just that. We also have to deploy our model. And we deploy our model into a different environment. Our models run in production. Imagine this is like a real-time model that's doing fraud detection or recommendations. And so they need fresh access to feature data to make their predictions. So both model training and model serving need access to different feature data. And what's really important and unique about machine learning is it just doesn't work unless they get the same data, unless it's consistent data. So how do we get this data into our training environment for model building? Well, ideally, we can use the same data, the same high value data that we have in our data warehouse or a data lake that our analytics teams have been refining and cleaning and making much higher value. We've put a lot of energy and investment into that already. However, this is not always super easy, right? There's a variety of reasons for this, and we'll just jump into a couple of different ideas here. One is just there's the data that my model can use for predictions and in production is not always available in my data warehouse, right? It could be for security reasons. Production data doesn't go there. Another reason is just often the data that does land in the warehouse has been transformed. It's been cleaned in some way. For example, it's been sanitized, it's been typecasted, downsampled, ordered, and it's not necessarily representative of what my model would see in production. So it introduces some data consistency issues. And let's also think about what about the data that is in production that my model would get for predictions? Well, maybe we can use the same kind of data warehouse for that. And this also isn't really easy. It's actually even harder. These systems don't have real-time serving. They don't have good streaming support. They can't do real-time transforms or transactional features. And what's even a larger issue for important models is that engineering teams, production teams run your production fraud model. And they don't really trust taking a dependency for their production fraud model on an analytic data system like a warehouse that has really minimal governance on changes. And so they don't want to make their models, their production systems, easier to break because these people are going to be on call for this thing. So there's just a lot of complexity with this data. And there's always this question of like, what data can I use when, and where is that data? And again, the challenge isn't just connecting some offline data to a model in production. It's in managing the complexity of ensuring that data is consistent across environments. For machine learning teams to be fast and effective, they can't be dealing with this complexity in every single iteration loop. They need tools and workflows to be able to iterate quickly on features and have them be easily available for training and production inference. Just remember that the correctness of these ML systems, them functioning at all, depends on getting the same data inputs across these environments. So dealing with all of this complexity is like the problem in productionizing ML. And it's why it can take teams months, quarters, sometimes even more than a year to get a new model into production. This is a huge topic. There's a bunch of different problems here. And a lot of the talks in this conference are deep dives into different sub areas of these problems. In the real world, teams fail for a variety of different reasons. And let's just look at like one of the common workarounds for one of these problems, just as an experiment, which might resonate with you. You might see this in your team. One thing that's quite common for teams to do is to rebuild the offline pipelines online. So they'll take some transformations that have been built in a warehouse or some analytic environment, and then they'll rebuild them in a streaming system, or they'll rebuild them in some operational ETL environment. This doesn't solve our problems. It allows data to get to these models, but it's super slow and painful. Engineering teams have to be really heavily involved in every single iteration, and it's very error prone. The data across these systems is now going through 2 different transformation pipelines, and so there's no guarantees of data consistency, and it always leads to maintenance messes. And the biggest problem here is that like data scientists don't end up owning their work in production. And they don't even know how the data that is being consumed by their model in production got generated. So it's a tricky situation. So how can we make productionizing machine learning as fast and easy as building something like a dashboard on a warehouse? Feature stores are built exactly for this, right? They're the hub for a data flow and a machine learning application. And they're focused on solving these data complexities for putting ML applications into production. So they do a bunch of things like ensuring transformations are consistently applied across environments, organizing data for use in ML, and making feature data accessible for online inference and offline training, and monitoring this data and keeping it validated. The most important thing, though, is offering a very simple workflow for teams to quickly iterate between development and production with their data. So the feature store does this not by duplicating your data stack, but by integrating with it and extending it to provide data workflows and interfaces for ML developers. We believe that those workflow implications of feature stores are more impactful than any other component in the ML stack. And they're critical if we want to make ML as easy as common analytic workflows today. So let's talk about what's in a feature store and how does it work. Well, let's kind of draw this out, right? So of course, the feature store, we need to serve features in production. So we have, your production application, it has to request features. The feature store has to deliver features to a model to make a prediction. It also needs to interact with your development environment. So, your notebook or your data science environment, you need to be able to talk to the feature and ask for a training data set, right? Ask for different features so you can build your models. And the feature store, of course, is connected to your upstream data, stream sources, batch sources. This can also be operational sources like operational databases, even third-party data sources, kind of common like vendor APIs. And so what's going on within the feature store? Well, there's a couple of main capabilities. First is serving. So it's all about delivering feature data to, to your model. So ML models can require a consistent view of feature data across training and serving. When we're creating training data, we need to actually train on historical examples. And so it's actually pretty common to not only need to join features together to generate a training data set, but also to have historical values of features that represent what a feature's value was at a specific point in time in the past. This is a really huge concept and one that we could do a whole deep dive on. Or from Lemonade is giving a talk on this, I think tomorrow, and on basically like all of the challenges of getting like point in time feature data. So you should check that out. And then on the serving side, your models need data, need this feature data fresh. They need it in real time, and they need it served at scale. And so where does the feature store get this data from? Well, it has a storage layer. Feature stores contain both an online storage layer and an offline storage layer. So the online storage layer is what contains the freshest values of each feature, and it powers that real-time serving to your model for inference. And the offline storage layer is what contains all the historical values of different features, so such that you can go back in time for training, for assembling training data sets that represent historical examples. And the feature stores organize the data in these storage layers in a really nice way to make features really easy to join together. So they're organized by like a primary key, like an entity. We call them an entity ID, user ID for features that are user features, and they all are tagged with a timestamp, so we can go through different historical values. And then feature stores actually run the feature engineering transformations to convert raw data into feature data. This happens by orchestrating transformation jobs on your existing infrastructure. So think about like running a SQL query on your warehouse or running a job on your Spark cluster. Many of these feature pipelines are expensive, and they need to actually, to compute a feature, you pre-compute it. You compute it ahead of time before you need it for real-time prediction. And the feature store handles two things: running those pre-computations, but also handling smart backfills for features. So when you're iterating on new features, you're doing feature engineering as you're experimenting with new features and building new models, trying new ideas. You need historical values of features, and the feature store handles automatically backfilling those values so you can easily get a new feature set. The folks at Intuit are talking about how they manage feature transformations within their feature store. And that's a talk that's happening, I think, later today. You should check that out as well. I think that's from Simar Pal and Ian. So another really important capability for this hub of data flows for your ML application is monitoring, obviously. Ensuring data quality and validating data is extremely important to anybody running a production ML application. So, the feature store is the interface between your models and your data, and they organize all the data that is important for model operation, but also for model debugging and auditing. So feature stores do not only like data quality monitoring, but they're also pluggable with external monitoring or data observability systems. So it's really about organizing these data sets, making all of the training data, the serving data accessible to any other system that wants to generate metrics and validate data quality. Feature stores can be extended not only to like monitor data quality, but also for operational metrics like serving latencies and a variety of other things around feature computation. The folks at Atlassian actually extended their feature store. They added a layer on top of Tekton that measures the cost of computation for every single feature. And so they have this whole layer of cost analytics on top of every feature. They're giving a talk on that tomorrow. You should check out Josh and Jeff's talk about that. It's really cool. The final part here is the registry. The registry is the single interface for users to interact with this single source of truth about features in an organization. For users, it contains all of the definitions and the metadata that can be used to discover new features and share and reuse features. The registry, all the data in the registry configures the feature store system behavior. So automated jobs use the registry to figure out when to ingest data, when transformation should happen, what data to store and how to organize it. But all of this together allows the feature store to become almost this data catalog of production ready signals. So you suddenly have this library of signals that have already been found useful for other people, and they're ready to go in production right now. What's great about this is that it removes a cold start problem for data science projects, for testing new data science ideas. Now you can essentially just like new idea, create a model with these set of previously existing features that others have already found useful, and put it into in a full-scale production experiment in minutes. And so this dramatically speeds up the data science experimentation cycle and really solves this cold start problem. So looking at the feature store as a whole, the feature store contains a variety of components that work well together to provide a nice platform, a nice hub for all the data flows in your ML application. and it solves a lot of the data engineering challenges needed to build and maintain these production ML applications, transformations, storage, serving these features, and then monitoring them to ensure they're correct, and then the layer of discoverability and governance that's really important for sharing things across organizations. So there's a couple of things that are important to know if you're considering using a feature store. The first is that modern feature stores are really lightweight. We're not talking about adopting a whole duplicate data stack. Feature stores aren't introducing a new type of database, a custom re-implemented key value store. They run in your cloud environment. They reuse your existing data stack. They extend your existing infrastructure. So they reuse your Spark cluster, they reuse your warehouse, and it will even reuse your storage layer. So its features will be stored in your warehouse or in your data lake, so you can access them for other use cases beyond just feature retrieval for machine learning as well. Getting benefit from a feature store is not an all or nothing proposition. Feature stores are incrementally adoptable. So what does this mean? Well, you probably already have some existing feature pipelines, right? So here we're looking at two existing pipelines, one that powers your training, one that computes some features for your serving environment. And to get started with a feature store, you probably don't want to have to rewrite these into the feature store or do a big migration. You really are just trying to add some new signals to your model. And the feature store is all about that. So it's really an incrementally adoptable system. You don't need to rewrite your existing pipelines to begin using the feature stores. They're built to work alongside your existing infrastructure that you are already happy with, and it's already built and working. So it's common for teams to start using feature stores to just get the new features they've always wanted in production without dealing with migrating a bunch of old stuff that happens to be already working. And another thing that's quite common is after teams get to this point, they actually really like the feature store interface. So they want to integrate their existing pipelines with the feature store. So they get to take advantage of that unified feature retrieval interface that the feature store provides. And so they end up connecting their existing pipelines directly to the feature store and having a single interface that they connect to retrieve their features across all of their models. So we just talked about a lot of different data engineering problems that need to be solved when putting machine learning into production. These problems are problems that ML ops teams are spending a ton of time on. But there are elegant solutions out there, and we want to help all ML teams have success here and do this well. So we're working on a series of contributions to the open source feature store called Feast to establish a really high quality open feature store that can be used as a reference feature store architecture for all ML teams across the industry. So I'm now going to hand it over to Willem, the creator of Feast, who's going to introduce the new release of Feast and is going to show us a nice demo.
Thanks, Mike. Hello, everybody, and let me introduce Feast 0.10 to you all. So the feature store principles and capabilities that Mike just presented form part of a broader vision we have for feature stores. Feast 0.10 is the first step towards that vision, but it's specifically focused on serving. Our goal with Feast 0.10 was to make the simplest and fastest feature store for ML teams to serve their analytic data in production. Feast 0.10 provides training dataset building with point-in-time correctness, helping you avoid feature leakage, online serving of your data at low latency, and provides consistency across these two environments. This first release is GCP focused, meaning you get BigQuery as your offline store, Firestore as the online store. The key problem we're trying to solve with Feast 0.10 is, now how can we make it easy for teams to deal with the complexity of data consistency across environments? So let me walk you through some of the key changes in Feast 0.10. Firstly, at zero config. With Feast 0.10, we allow you to deploy a batteries included feature store without any custom configuration, meaning you can just get started in seconds. Secondly, local mode. Feast 0.10 ships with a full local mode, meaning you can test your end-to-end development workflows completely locally from either your IDE or a notebook. Third, there's no infra involved if you're just getting started. That means no Kubernetes, no serving APIs, no Spark. If you want to use Kubernetes, you're welcome to use the open source components that we provide. That's always the option if you want flexibility, but it's not required if you're getting started. And then finally, Feast 0.10 is extensible. It ships with a provider model that allows teams to easily extend Feast for deployment into their own custom stacks. So let's talk about the demo that I'm going to show you in a second. So first, we're going to show how we're going to set up a feature store with Feast. Then we're going to train a model using features from BigQuery, and we're going to use Feast as the interface to BigQuery. Then we're going to do a testing of the model with a local online store using SQLite. And then we're going to test the model with the production feature store. So we're going to deploy Feast to cloud, to GCP cloud, and we're going to use Firestore for online serving. So here's the use case. We are going to receive a list of driver IDs, and out of these drivers, we need to pick the driver that is most likely to complete a trip with a customer. And so the way we want to do that is we want to train a model and we want to use that model to do inference. But we have a requirement that we need to respond within a few milliseconds. So ideally, this model can be served online with a source of data that is both fresh and can respond in low latency. We know that we have a lot of data in BigQuery for drivers. So let's have a quick look at that. I'm going to run a quick BigQuery query, and we should get results back in a sec. Right, so now we can see that we have a bunch of data in the offline store in BigQuery on drivers, so conversion rate, acceptance rate, and average daily trips. We can use this to train a model. So we know that we have that available. So let's start a Feast repository in order for us to set up our feature store as the first step. So we run Feast init, and we use a GCP template, and we create a driver ranking repository. So that's created, and we can have a look at the top left here. You'll see that we have a new folder here with 2 files. The first file is the feature store YAML. This is a simple little file, and it just tells Feast, you're going to use the driver ranking as your project name. This is just a namespacing key, and the registry is going to be a local file, just a local DB file where your feature definitions will be stored, and we're going to use the provider as GCP, which means it targets GCP for deployment. But we don't want to get there yet, so we want to use local as the provider here because we want to start testing and development locally. Let's have a look at the driver repo py file. So within your repository, you've got a bunch of these py files, and these Python files just contain feature definitions defined as normal Python objects. So in this case, we just have a single feature view, and this tells Feast the combination of the feature view and this BigQuery source, where to find features, and then when it needs to materialize features for training dataset generation or for online serving, how to represent those features and what are the constraints and properties of the data. So basically, this is just telling Feast right now, there's a table with driver features, and we can use that to build training data or to serve that online. So let's just go into the driver ranking repository and run Feast apply. So what this is going to do is register our features and set up a local online store. Since we set the provider to local, now we've got a SQLite online store. It's empty right now, so let's load some of this BigQuery data into our online store so that it's ready for prediction after we've trained our model. And we can just use the Feast materialize incremental command in order to do that. So what this command does is it's just querying BigQuery, finding the latest feature values for each driver and loading that into the online store. So now we've got a registry that's full of feature definitions, and we've got an online store that's ready to serve data. But the first thing we wanted to do was set up a feature store, and we've done that. The second thing we want to do is train a model. Right, so let's go to our training script. Here we have a script that basically just does 4 things. 1, connects to the local feature store. 2, creates a training data set. 3, trains a model, and then 4, saves it. So all you need to do to connect to Feast is create a feature store object and point it to the registry or to a local repo. And so that's what we've done here. Then what you do is you just call a single method in order to build a training data set, get historical features. Feast is going to intelligently build a training data set, and it's going to query BigQuery and find those driver features and join them to the data frame that you provide. In this case, you're providing an orders data frame that has a rows that contain a column called trip completed, and that just says, did this driver complete or did they not complete a historical trip? And so Feast is going to intelligently join those tables together in a point-in-time correct way, and then we're going to train a model and save that model. So let's just quickly run the script. Right, and so a key thing to understand here is that Feast can query from any amount of feature tables or feature views and join those together. So all of the columns do not have to occur in a single source table, and it can stitch those tables together in a way that the timestamps do not have to align perfectly. So it ensures point-in-time correctness, which prevents feature leakage. Right, so now we've trained our model, and if you look on the left, the driver model binary is available. So second step done, we've trained a model. The third step, let's test this model against the local online store. So we go over to our predict class here, to our predict Python file. And what we've already set up here is a driver ranking class. And so what this class typically does for most teams is loads a model and maybe even loads batch data into the class itself, and it's like a static data set that you just serve in production. But and some people connect straight to operational DBs, but that doesn't ensure consistency. So what we do here is we're going to use Feast. So we're going to, when we initialize this class, we're going to load a model into memory, and then we're also going to create a feature store object, just like we did for training. Let me show you what prediction looks like. So for prediction, remember, we're going to get a list of driver IDs, right? So we get that list of driver IDs. Step one, we're going to read features from Feast, the online features. So we take the driver IDs and we take the same list of features we used for training, and then we just query that from Feast. And then we get back, the data frame from Feast. And this in this third step, we're querying the local SQLite online store, meaning we're not touching any cloud infra. It's a completely local feature store. You can iterate quickly and you can develop and then test this, out before you actually go to prod. And so you've got your data, you make a prediction, you choose the best driver, and you return the best driver ID. So let's quickly try that out. We should get a driver ID. Yep, 1001 is the best driver for completing this trip. Right, but let's go to prod. We don't want to use local forever. And so the easiest way to go to prod is just you change your provider to GCP, and then you just reapply the changes with Feast. So now what Feast is going to do is it's going to update your infrastructure based on the feature views that you've registered and the feature definitions. So in this case, the default online store for GCP is Firestore. So now we're going to scaffold Firestore ready to receive data and ready to serve data. But there's no data in there yet right now. So let's materialize data from our BigQuery source, our data source, into the online store. So now we're just synchronizing data. And so we're taking the driver hourly stats and we're loading it into Firestore. This will just take a few seconds. Yep, done. Okay, so let's rerun our prediction routine. The cool thing now is we don't need to change our online prediction routine. We can just rerun it because the online store has changed, but everything has been commoditized about the prediction script. And then we have 1001. That's the exact same result we got locally, and now we have a production store. So just as a recap, we set up a feature store, we trained a model using Feast and querying data from BigQuery in a point in time correct way, and we used the local SQLite to test the online store capabilities quickly, and then we shipped Feast into production, and now you can just ship your model into production, and you have a complete production setup with almost no infrastructure that you have to maintain. It's just a bucket and a serverless Firestore. So what's next? So Tekton, just to recap, is an enterprise feature store with advanced functionality like transformations, access control. It has a UI, it's managed service with production SLAs. Feast, on the other hand, is a completely open source, production-grade feature store that you can get started with today and deploy to your own infrastructure. So we're just working towards a common standard for feature stores, and the release of Feast.10 is the first step towards that. Over time, we'll be converging our APIs and working towards a unified specification for feature definitions. So what does that mean? It means that over time, Tekton will be releasing more and more of its internal technologies into the Feast project, and we'll have the possibility of being able to seamlessly move from Feast into Tekton as a managed offering. So if you want to try out Feast 0.10, check out our quick start or have a look at our documentation. If you want to run Feast on Kubernetes with Spark, that's also available. You can have a look at our Helm charts and our installation guides. And if a full-featured managed feature store is what you're looking for, have a look at tekton.ai and reach out to us. And then finally, also come and catch us on Slack. We were going to do a Q&A after the session. The link is on screen right now. And I hope you have a great conference.
And we're back. That was awesome. So 2021, and we're still working on the streaming thing. I know there's been a lot of questions that have come up. We are hoping to get the quality up high, so bear with us. And we've got another session for you. Before we jump into the other session, there's some questions that are coming up in Slack about where to ask the questions for this last session and all the sessions. That will be happening in the channel called Apply Conference. So jump into that Slack and go to the channel Applied Conference. Next up, we've got Wes McKinney. I've been really excited for this one. You may have heard of pandas. Yep. That Wes McKinney. All right. So Wes is the CEO and founder of Ursa Computing, an enterprise software company creating Arrow-powered computing technology for data science. He created the Python Pandas project and is a co-creator of Apache Arrow. Wes will discuss the coming architectural shift in data analytics systems enabled by the widespread adoption of Apache Arrow. He'll also advise how to plan for a future built increasingly on interoperable open standards. Wes, it is a pleasure to have you here with us, and I hope you all enjoy. So take it away.
All right, thank you. All right, thanks for joining me here today, or watching the video of this stream on recording. This is a pretty high level talk, so we're not going to be looking at a ton of code here. It's more of a higher level discussion of some of the trends that are happening in the world of data analytics and important changes in the infrastructure that are affecting all of our programming languages, all of our computational engines, our data analytics systems, and how we can begin to think about them and to work better together to enable this improvement of our computing infrastructure to happen more quickly. So I was just introduced. Most of you know me from my work on the Python Pandas project. I haven't been doing as much Pandas development for the last 8 years or so. So Pandas, in fact, is a 13-year-old project as of this month. And I was very active with it the first 5 years of its life, building the first versions of the project, beginning to build a developer community around it, writing my book Python for data analysis. But I handed over the project to the open source community and the other key contributors in the project. People like you may know, like Jeff Reback, Joris van den Bosch, Tom Augsburger, and others who have carried on development up through the present. So when you're using Pandas and you're benefiting from its stability, its functionality, its speed, remember that there are many other people that are involved with making that project as good as it is today and as reliable as it is. So be sure to thank them and remember that it's been going on for over a decade, and a lot of the work has been carried on by the other volunteers in the project. So this talk is going to be specifically about different aspects of what I call computing silos that have developed in different parts of our infrastructure. And the three different kinds of computing silos that I want to focus on are data silos. So data itself, how data is stored, how data is accessed, how data flows around our systems. And then we come to computing engines, so systems that access data, compute queries on it, perform ETL, feature engineering, machine learning, AI, where the rubber meets the road and the computing happens. And then there is the problem of programming languages and language interfaces. And of course, computing engines and data have to be used through some programming language. And so the programming interfaces that we use are, of course, very important to us because they're the only way that we can get access to these systems. And one of the reasons that Python has become such a popular language for data science, for data engineering, is because the Python language itself is very pleasant to program in. You can express yourself very easily. Not only is it a good language for building software, but as a user and just doing your day-to-day job, it's a language that as Fernando Perez says. The creator of IPython and Jupyter, Python is a language that gets out of your way. And so that's one of the reasons why it's become so popular. But there are other programming languages as well. There's R, there's JVM languages like Scala and Java. There's Rust, and a lot of people are excited about Rust nowadays. And of course, there's languages like C and C++ that have been around seemingly forever. So we have a lot of programming languages, and it creates distinct ecosystem problems around them and how they're used within, particularly within enterprises where you can't, it's not that you don't only have one programming language. In reality, you have multiple programming languages. So some of the problems that we see that are what I call data silo problems. One of the biggest issues is that many workloads are plagued by serialization overhead. And serialization is the computing work that is spent converting data between different formats. And so that might be loading data out of a CSV file or loading data out of a Parquet file. The data is loaded into memory, perhaps, or it might be converted into some other serialization or data format for use in another system. But it's not uncommon to see workloads spend 70, 80, 90% of their time simply converting data from one format to another. Another problem that we see is that depending on the tool that you're using, how the data is stored, where you're accessing it, that the performance of getting and the performance and overhead associated with data access and delivering data to applications is completely all over the place. So some systems are really fast to access data. Some systems are really slow. You have many different implementations of reader interfaces to files. So you might be able to read one CSV file in one application pretty quickly, whereas in another application, it's much slower because you're using a different library to read the CSV file. So, ideally, we would like to have consistently good performance accessing and delivering data in all of the places where we need it. Another problem that we see a lot is this problem of data being held hostage by a system. And this is not, it's sort of an artifact of the traditional way that data analytics systems were built, which was in a very vertically integrated fashion. So you buy an appliance, which is your database system. The people in your company insert data into that system, and then the analysts who are working on the data send queries to the database, which serves as the Oracle. And there, of course, it's no surprise that one of the first database companies was called Oracle. The database computes those queries and returns the answers. But if you have an application where you need to export large quantities of data from a vertically integrated system that is responsible for storage, computing, and query interface, it can be quite slow to get data out of those types of systems. And so even though you can technically get the data out of many data warehouse systems, the performance of importing and exporting large quantities of data can create a lot of pain for the users. Another issue we see is that of different systems operating on different data. And so in modern enterprises, we see a lot of different systems for handling streaming and real-time data, and so systems that capture and deal with real-time data, and then a data warehouse system which operates on data that's been ETL'd into a particular schema that's optimized for query processing. And so many organizations are operating and running their workloads on stale data where they might have an ETL lag of 12 or 20 or 24 hours or even more in some cases. Some of the problems that we see with compute engines, firstly is that performance is pretty inconsistent. So if you're a data scientist, there are many different data frame libraries that are available in Python now. There's different data frame libraries in R. Though there isn't a great deal of overlap in the code between those systems, and so the performance can be all over the place. And you see a lot of internal competition within programming language communities, trying to see who can implement the best algorithms to attract more users to use their tool. One symptom of the fragmentation in computing engines is that hardware frequently goes underutilized. So, for example, a lot of systems in Python were built were built in the old days where you had a single core machine or maybe a dual core machine, and so writing algorithms to be able to utilize modern CPUs with 8 physical cores or 16 physical cores was not part of the design requirements. And so so many of our pieces of software are not fully leveraging the hardware capabilities that we have today. Of course, there are new kinds of hardware that have been created, like GPUs, and now there's many different custom chips for analytics and data science workloads, AI workloads that are in development. And so building software that is optimized for these new kinds of hardware, not only the current generation of CPUs and taking advantage of the specialized hardware accelerations that are available in those chips, but also taking advantage of new kinds of hardware. It's been pretty slow in practice for those improvements in hardware to make their way into the hands of data scientists in their everyday, in their everyday work. So, for example, right now I'm working on an M1. I'm giving this talk from an M1 MacBook Pro. So Apple just changed architectures in their CPUs from Intel to ARM. And so all of that software, which has been built, that's been optimized for Intel hardware optimizations, can't be used on an ARM chip. And so an entirely different set of hardware optimizations utilizing SIMD instructions for ARM need to be developed in order to fully utilize these new processors. The use of a particular computing engine can also create like a sort of lock-in using that engine, especially where there is a coupling to a programming language that you must use. If you're using Spark, you really should use Scala to get the best out of Spark. So even though you can use Python, you do pay a penalty when you use Python on top of Spark. Another problem that we see with programming languages is that a lot of the computational machinery which is used in the implementation of the libraries that we have, data frame libraries, data science libraries, that there isn't as much code sharing between programming languages as we would like to see. And so many of these projects are their own little islands of algorithms and IO code. And so essentially, if you look at Pandas has its own CSV reader, it has its own implementation of most of its critical analytics algorithms. And so at the time that we built the project, that was the best way to solve the problem very quickly. But a lot of other open source projects have done the same thing. They've built their own full stack solutions to all of these problems. And there hasn't really been a basis of code sharing and collaboration across projects within languages and between programming languages. Another issue we see is that the language interface to a computing engine, what I was saying before, one programming language running on top of a certain computing engine can perform differently from another. And so to use Spark as an example, the performance of using Spark for certain workloads can be variable depending on whether you're using Python, R, or Scala. And so ideally what we'd like to see is consistent performance across programming languages. So if we had our way and we could take a magic wand and redo the whole computing stack to be the way that we would ideally like things to be, we would like to see programming languages becoming much more first-class citizens. So you can choose the programming language that best suits the way that you want to work, and that you don't face these various penalties around data access or computing performance or feature support in your programming language. So if you want to build applications in Rust, you can do that just as well as you could in Python or in Java. Our computing engines, we would like the libraries and the computing infrastructure that we're building on to be more portable and more usable in more places. We'd like them to be able to take advantage of hardware acceleration, new innovations in CPUs and new kinds of hardware like GPUs and specialized computing chips. We'd like to see those improvements make their way into the majority of users' hands as soon as possible, rather than taking years for the software to be developed to take advantage of those take advantage of those platforms. And by sharing more systems code, the work, the optimizing the compute engines will benefit everyone. So not simply the users of one particular computing engine. And around the data itself, pretty simple. We want to be able to access data efficiently, productively, quickly, in all of the places that we need it. Of course, the real world is messy, and so creating utopias in many areas of life is not always practical. But perhaps there are some things that we can do to put ourselves on a path to make things meaningfully better for all of our data analytics work. So to build better computing engines, we want to be able to take advantage of hardware improvements much more quickly. We'd like to have systems that can leverage hardware heterogeneity. So if you have a system that has GPUs on it, that you can leverage both the CPU and the GPU and to run, to optimize for the hardware that you have to run your workloads as quickly as possible. We'd like to see more ecosystem-wide collaboration on algorithms, particularly on leveraging advanced features in hardware. So we see canonical high performance implementations of the critical algorithms that we need that can be reused by everyone. And another point with computing engines that's often lost is the importance of having high quality computing at the small scale, at the laptop scale or the workstation scale. So you've seen so much work happen on scalable computing at the 100 gigabyte or 1 terabyte and upscale up to the multi-petabyte scale, but there's been relatively little progress or comparatively little progress on efficient computing at the single node scale. And so ideally we'd like to have compute engines that work well or that can be used as the basis of a scalable big data workload, but that can also be used efficiently and take advantage of and be optimal at the single node scale on the current generation of CPUs and GPUs. In our programming languages, we'd like to be able to pick the programming language that best suits us, to not have an impossible choice between a programming language that we prefer to program in, but where we pay a significant performance penalty to use that language. Often that overhead can be the result of serialization overhead associated with data movement. The compute engines should create interfaces to make themselves usable from any programming language that can bind with their low level interfaces, so that you aren't forced to go through necessarily a higher level language in order to access that system. And on data, where frankly the most progress has been made in recent years, the adoption of open standards like Parquet and Orc for analytical data storage has improved the data silo problem significantly. There's still many problems around dealing with very large data sets, large scale metadata, and the creation and adoption of open standards that are community maintained for data storage and metadata is a big part of the solution here. Moving data around and accessing data, having standardized protocols for data access, for moving data between systems is critical for dealing with the data silo problem. And to the extent that we can reduce couplings between data storage, data access in a particular compute engine to make compute engines more pluggable, more interchangeable, to have that architectural requirement forces will force better design decisions and less lock-in to particular compute engines. So we've been working on the Apache Arrow project as a development platform to address these low level issues in data computing engines and programming languages. And so I'm going to tell you a little bit about how we're doing that and where we are in the process, because many of you have heard of Arrow. It's been around for more than 5 years now. So maybe you're wondering, when is this going to make its way into my life and make things better for me? But we really do, from the early days in the project, 2015, when we began putting the project together, we saw it as a critical and fundamental part of beginning to solve these data analytics silo problems around computing data and programming languages. So we started this project around 5 years ago as a collaboration between a collection of data science, big data, and database systems developers. And the purpose was to create these shared technologies that could be used as the basis of a better development platform for data analytic systems. So not only data access, serialization, and data movement, but also building better computing engines and having better cross-language support for building our next generation of ETL, feature engineering, data analytics, machine learning architectures. So our approach and the way that we're thinking about the problem is, on the data side, that we would like to see more and more systems accessing data and moving data around in the Arrow tabular columnar data format. And that's the area where the most progress has been made. And I'll speak shortly about some of the systems where this work has been done, and it's in progress in many other systems around the ecosystem. So it's not enough to be accessing and moving data around an Arrow. We also need to compute natively on the Arrow data. So we specifically designed the Arrow data format to be efficient for computing. So it's suitable for efficient computing in CPUs and GPUs. And we designed the format specifically for the needs of modern hardware. And so we need to see more computing engines using Arrow as its internal native data format. Secondly, by building strong libraries to support Arrow in different programming languages, we can enable them to plug into systems that are written in other programming languages and achieve interoperability or provide a language interface, for example, in Python or in Rust or in Go that has almost no overhead by virtue of having a common data structure, a common data format on both sides of the language divide. So the project has been growing rapidly. We've made 20 major releases. We have over 600 contributors, 600 unique contributors. So we've created a vibrant community around the project. We have 11 programming languages, soon to be 12. Julia is kind of the newest language to the project. So we've made good progress on making this a community-led effort, and I expect that this graph of contributors will continue to grow, up and to the right as time goes on. For the people listening here, I think the most exciting thing that we've seen and that's making the most impact on your day-to-day lives is the rise of Arrow as a standard format for bulk data access and data interchange. And so we've seen many databases and data warehouse systems adopt Arrow as a means of getting data to you more efficiently. So, for example, when you're using when you're using BigQuery or Snowflake, you can request data to come back to you in Arrow format, and then Arrow data can be loaded into Pandas really efficiently. We use Arrow to accelerate user-defined code running in Apache Spark. And Spark SQL does not use Arrow internally, and so there still is some serialization overhead when using Python on Spark or R on Spark. But by using Arrow for the bulk data movement between the Spark runtime and the custom user-defined Python and R code, we were still able to make things a lot faster. So we've seen adoption in many other places as more and more systems have standardized on columnar data files like Parquet and Orc. We've invested heavily in making sure that the interface between Arrow and Parquet files or Orc files is high quality, so that we can encourage more, that kind of in-memory interface where Arrow, Arrow, we want Arrow to be the dominant technology, and the storage layer, Parquet, that's an optimal kind of pairing of technologies, and we've seen that uptake robustly, especially in the Python ecosystem. The next stage of work that I'm really excited about is the rise of Arrow native computing systems. And so Dremio, which I partnered with on the creation of the Arrow project from the early days, was built as an Arrow native engine from the ground up. But I see I put Dremio twice on the slides. I apologize for that. One really exciting project has been NVIDIA's Rapids project, the cuDF library and related projects, along with the Blazing SQL distributed SQL query engine built on top of Rapids, which is a GPU native data frame project and analytics framework, and has demonstrated that you can achieve amazingly good performance, not only in wall clock time, but also in power utilization and total cost of ownership. And so we show that by using Arrow, not only do we get the benefits of this faster data access and faster data movement, but we can also bring down the cost of computing by utilizing hardware innovations and hardware acceleration. And so I think that the role of GPUs and custom chips for data analytics is going to become more and more important in our lives. We're starting to see some in the Arrow project itself. We have a native query engine for Arrow, which is built in Rust, called Data Fusion. We've seen a really vibrant Rust community develop there, and so there's a number of projects which are using Data Fusion, which is written in Rust, as the basis of their query engines, and so excited to see how that develops there. Also seeing some academic projects like the Noise Page project from CMU adopt Arrow as their cold storage format and as part of their query engine runtime. And so to see Arrow embraced by the academic database community is an important step in the growth of the project, and seeing that both not only robust adoption in industry, but also in the academic world. So a cool project, just to give you an idea of some of what's become possible in 2021. There's a new Python project called Polars, which is named after kind of inspired by pandas, of course. It's a data frame library similar to pandas. It is built on the Rust Arrow project and Data Fusion. So the core of it is all written in Rust. The data processing, the kind of the internals of it. But you can use it from Python. You can extend Data Fusion with custom code written in Python, and so Python code can be pushed into the Rust Data Fusion engine with zero cost, which is exactly the whole purpose of creating this stack of technology. And through this project, it's achieved really impressive analytics performance. So I encourage you to check it out as a glimpse of what the future looks like. In the C++ project in Arrow, we've been over the last couple of years been working on creating a full stack kind of data platform, query execution, data transport, the Arrow Flight framework. Some of you may have seen other talks that I've given where I've talked about Arrow Flight and our use of gRPC and making it easier to add Arrow support to systems so that they can send and receive Arrow data natively at high speeds. And so if you're interested in this work, I encourage you to check out what we're doing in the open source project. The way that we're integrating a lot of this functionality into user languages like R is through existing query interfaces. So if you're a dplyr user in R, we've integrated the Arrow-based data access and computing functionalities natively into dplyr. So you can access a multi-file Parquet data set in S3 that is all accessed with Arrow, and then query it using the same primitives, dplyr constructs that you're familiar with, and we'll compile this to an Arrow query internally and execute it, as best we can directly on top of Arrow. So very exciting stuff, and we'll be seeing a lot of improvements and new features here over time. So so definitely a high level view of the changes that are taking place, but I would say to to keep an eye on what's happening here. Encourage your software vendors, if they are not doing things with Arrow already, to look at how they can plug into it, provide an Arrow-based interface, at least for data input and output, so that you can get your data in or get your data out more quickly, and that we can be on a path to making all these systems compose with each other and be a lot more interoperable. So I'm very excited about the future of data analytics systems, and excited. Definitely the last 5 years has been really interesting building this project. The next 5 years are going to be even more interesting, and so a lot of innovation to happen here. So thanks for coming to the talk, and thanks for having me, Tekton, and everyone at the conference.
Wes, do you mind if I ask you a few questions real fast?
Sure.
Nice. Well, I blew through the intro, so we're running a little early, and
Okay.
we get time to talk with you. Thanks for doing
Great.
this, man. Absolute legend. I appreciate it. And there's some cool questions coming through in Slack.
Mm-hmm.
First one is more of a statement, but it's from Dave saying, "Oh, it's interesting. Wes didn't mention Julia when you were going through all of the different stuff. Was there a reason for that?"
No particular reason. There is a Julia Arrow project. I mean, to be honest, I haven't kept up. I haven't kept up too much with developments in data analytics, specifically in Julia. But I'm very excited about what's possible there. I think that the single language, the best of both worlds approach of Julia makes a lot of sense for as a user language, where you can get really fast user-defined functions, which are compiled by Julia, that can be pushed into a general purpose query engine. So at the moment, it would be relatively straightforward. I understand to write a custom function that could be inlined or passed into the Rust Data Fusion query engine. So that's something a proof of concept that I would be interested for somebody to build. So we're working on getting the Julia Arrow project integrated with the Apache community, and I'm interested to see a developer community develop there. So I think I talked a lot about Rust in the talk, because we've just seen this explosion of development and tons of new developers coming into the community, and it seems that for systems development, that people are really excited. Of course, C++ is not going anywhere, but it's great to see so many people excited about doing data analytics in Rust.
Awesome. Very cool. So next question for you. Do you think Arrow becomes an alternative to Parquet for storing data that will eliminate the constant translation of Parquet to Arrow and vice versa?
It depends on what's meant by storage. I think for longer term or archival storage, Arrow is not designed for the needs of that. So, for example, it's not intended to be space efficient on disk. And so if you want your data to compress down to be as small as possible, but then can be read quite quickly, Parquet is a quite good format for that. So you can have a massive data set that ends up being quite small when it's encoded to Parquet format. Whereas Arrow is designed for memory speed performance. So as a data format for caching, it's ideal for that, where you can deliver data at memory speed, or if you've got very fast networking, you can deliver data over Aeroflight at more than 10 gigabits a second. There's a new project at Microsoft called Magpie, where they've created an Arrow-based data fabric that uses Aeroflight to cache and access Arrow data and different query engines and to deliver query results to users. So there's different, yeah, I think there's different needs there. But I think replacing Parquet for archival storage, I think there might be scenarios where it would make sense, but in general, the data formats are optimized for different needs, and we found that we can deserialize Parquet files so fast to Arrow format that the overhead there is not contributing that much to slowing down systems at the moment. But we'll see how things change over time. Of course, if disk and cloud performance starts to approach memory speed, then I think I think the story might change. What would change there? But we can, we'll be ready to react when and if that happens.
Yeah, cross that bridge when you come to it. So next up for you is a question from Reed. As potential ways to reduce language silos, have you tried OpenAI's GPT-3 for high-level programming language intertranslation for analysis?
I have not. Yeah, I mean, to be honest, it sounds like science fiction to me. But perhaps in the fullness of time, we'll be able to do code auto translation from one language to another. I will say that given the experience of building a project like Pandas, which is very complex and has hundreds or thousands of different APIs, that statically reasoning about the semantics of a particular piece of code can be really challenging. And so to create a machine translation framework for code strikes me as being very difficult. I mean, I think human language is also very difficult. But it's a different kind of challenge where, I'd be excited if somebody is able to solve that problem. But it's outside of my wheelhouse.
Yeah, for sure. So last one that I'm seeing here in the chat, and I've got one for you if you would permit me after this one. But is there a good GUI front end that is easy to use, similar to VB6 or C# for Python? I have tried Streamlit and Tinker. There's probably a way to say that I am not privy to knowing.
Yeah, to be honest, given that I spend most of my time in Emacs, and so I wish I could help more on that question. But I know that people build graphical interfaces for Pandas now. Like there's one I heard of called Bamboo that you could check out. For programming itself. I'm not sure what's the latest and greatest front end environment for programming.
Yeah, I understand. You're sinking your teeth into other stuff at the moment. There's another question. So there's a few other questions that are jumping up last minute, as they do. Does Arrow support common Pandas data frame methods?
It is beginning to. So we have a narrow subset of functionality that's implemented. If you use PyArrow, the Python Arrow library, it's a low-level framework, so it's intended for package developers to use. So it provides low-level access to various algorithms, data access, in-memory computing. It's not trying to provide an end-user experience similar to the way that Pandas is. So our goal for the Arrow libraries is to be used to build new data frame libraries, or to be used to retrofit libraries like Pandas with Arrow-based computing machinery. So we don't have the desire to craft like the next data frame library, but the low-level computing facilities we've built a number of them. We intend to build the rest so that we can efficiently compute complex queries natively against Arrow data and have good performance on the current generation of hardware. So we're implementing Intel optimizations for things. We'll need to implement ARM optimizations for things as well. But we'd like to do as much of that work in one place and to have just a large community collaborating to build really efficient code for Arrow.
All right, last one. Well, maybe not. You mentioned CPUs and GPUs. What about FPGAs? Thank you very much.
I know that there has been some work using Arrow on FPGAs. I myself have never written VHDL or used an FPGA, but there was a project out of TU Delft, I believe, where they built a project called Fletcher, which provides some glue between Arrow and FPGAs to make it easier to program, to provide like easier programmability for FPGAs. So I think there's FPGAs, and there's a number of companies now that are building AI optimized or data analytics optimized kind of specialty computing chips. You can look them up. I won't name them here, but I think we will see more specialty hardware that can be used within a heterogeneous computing context. So maybe like certain algorithms, like this hardware is really good at aggregating data, like doing group bys, and so we'll push the data to that chip to do group bys and things like that. So I'd be excited about that.
Nice. Okay. So last one for real this time. They just keep popping up, so I guess that's a good thing. What's your perspective on using protobuf as a binary storage format? In my opinion, great for in-flight data using gRPC, but haven't seen much in terms of storing proto on disk.
Well, I know that Google warehouses a lot of data in protobuf format, so it's certainly there's pros and cons of doing that. So one of the cons is that you have to get the .proto file, and you have to compile. You have to run a code generator in order to access the data file. So it does make things more difficult to access the data. There's definitely use cases for protobuf that don't make sense for Arrow, like highly sparse data with thousands or hundreds of fields that are mostly null. So there's still lots of valuable uses for protobuf, even with new formats like Arrow that are designed for analytical query processing.
Nice. So that's all the time we got. There are more questions that are coming in for you, but I'm going to have to direct you to Slack. And if anyone else wants to ask you questions, Wes is in the Slack. So jump in it. Thanks, Wes.
Thank you.
This was awesome.
Thank you.
This was very cool. Absolute legend right there in the flesh. Pandas. Lots of people thank you for it. I know a few people that don't, but we'll talk about that later. So great. Let's talk about the next speaker. We have got Chip coming up. Yes. Very cool. Machine learning is going real time. And I imagine that a lot of you know who Chip is. I don't even need to say her last name because she is like the influencer when it comes to machine learning and machine learning operations. Definitely an exciting one coming up in just a moment. So stick around and we're going to get started in like 1 minute.
she got no time. How does she know? Will she take me for a ride? Do you believe we can find the answers in our mind? I've been waking up from dreams and who's to blame? There's no looking back on love, it's too late. How does she know? Will she take me for a ride? Do you believe we can find the answers in our mind? I've been waking up from dreams and who's to blame? There's no looking back on love, it's too late.
All right, here we go. Thanks for waiting. We have got Chip coming up. So, she is a machine learning professor at Stanford who will discuss how machine learning is going real time. If you didn't catch it on the slide, that's what we're talking about. So, Chip has helped companies like Snorkel AI, NVIDIA, and Netflix deploy machine learning systems. She's also published 4 best-selling Vietnamese books. Talk about versatility. And now she's going to come on here and talk to us. And like I said before, you probably know who she is. She is quite prolific when it comes to being out there and talking about machine learning and ML ops. I am very excited to have her on. So thanks, Chip.
Hi, my name is Chip. I'm very excited to be here today. Thank you so much for having me. I'm going to be talking about real-time machine learning. A little bit about my background. So I actually come from a very non-technical background. I had published a few non-technical books before I went to college and became an engineer. I have done machine learning at several startups and big companies such as Netflix and NVIDIA. So currently I am working on my own project on real-time machine learning, and I'm also writing a book for O'Reilly. As a motivation for this talk, I just want to mention TikTok. I could assume that a lot of you have already heard of it or have an account on it. I never got a hang with it, but I heard it's amazing. So TikTok is one of the biggest social phenomenon in the last few years. Like it totally eclipsed what came before it, like Vine or Snapchat. And one of the adjectives I kept hearing people say when they mention TikTok is that it is extremely, extremely addictive. So like, and there are many reasons to explain why TikTok is so addictive. And I would say one of the reasons is their technologies. So TikTok's parent company, ByteDance, has been able to build a really, really incredible infrastructure that allows them to do online real-time machine learning, to allow them to learn users' preference very quickly. So if you download a TikTok, you can just like spend a few minutes scrolling through a few videos and they can learn exactly what you like, and they recommend to you like what videos you will most likely to watch next, giving you a really, really great user experience. Happy user love, really. In my talk today, so I'm gonna cover 2 levels of real-time machine learning. The first is online predictions, and the second is online learning. Before we go ahead, I just want to go over the definitions of real-time. So real-time is this quite ambiguous term. And I think people might want to argue, whenever I bring up real-time machine learning, people always ask me, what do you mean by real-time? So you talk to philosopher and recently quantum physicists, they might say something like, there's no such thing as time. And if you talk to software engineers, they're going to say something like, there's no such thing as real time. Like no matter how fast the systems are doing things, there's always some delay, whether it can be a millisecond to like even a nanosecond, but there's a delay. So, what real-time means is different for different type of systems. So for online predictions, real-time is defined to be like, in my definitions, is defined to be between milliseconds to like 2 seconds. Whereas when you do online learning, real-time means like in order of minutes. So also like, I just want to go over like what it means to be like a model versus system, because I say system a lot. So model here means machine learning model, whereas systems means the entire system, including the interface, data, compute infrastructure. So let's go first to the first level is online predictions. If you have built any kind of system for users, everybody knows that like latency matters a lot. There have been many research done to highlight the importance of latency. And here's two of my favorite research studies. One is by Google. Google, even back in 2009, they found out if you increase latencies from like 100 to 400 milliseconds, you can reduce searches by like 0.2%, 0.6% per users. And Booking.com is a more recent study, and it says found that if you increase the latency in like by 30%, you can reduce conversion rate by 0.5%. And because conversion rate is directly tied to a revenue, like 0.5% conversion rate means a lot in terms of financial consequences. So no matter how great some machine learning model are, if they take just milliseconds too long, users are going to click on something else. A trend with machine learning in the last few years is that we are embracing the bigger, better approach. So I remember that back then we were talking about like we can build like a model with 1 million parameters, and it was like, whoa, that's crazy. And then we had like a model with 1 billion parameters, and now we are talking about models with 1 trillion of parameters. So we have seen that as models get bigger, their performance, so they will achieve better performance. But a cost of that is that like they tend to take longer to make inference. So when models like BERT or GPT first came out, a lot of people worried that this model is going to be too slow to be useful. So imagine if you want to predict what user going to time next on the phone, and if the time it takes for the model to predict the next character is longer than the time it takes for users to actually type that character, that model is not going to be very useful. So one way to get around this is that like just don't do online predictions. So it's like when users enter a query, you just don't make prediction based on query right away, but instead you try to generate all the predictions beforehand. So if you don't do online predictions, there can be no prediction latency. So so if you don't do online predictions, what can you do? So one approach is doing batch predictions. Is that you generate all the predictions before offline in batch, and you store them somewhere, such as in a SQL table, and you only print out pre-computed predictions when needed. So batch predictions have been very successful, and a lot of companies are still using it. For example, Netflix. Netflix is definitely very famous for their recommendation systems. So when you open the Netflix homepage, you will see a lot of recommended movies to you. And these recommendations are not generated as you open the web page. They're actually pre-computed somewhere. And only when you opened the Netflix website that you can see this recommendation, because they're going to be fetched from there somewhere in storage somewhere. So if you try to refresh your Netflix, you will see that even though the order of the rows might change, the actual movie recommendations don't change. So there are like a lot of problems with batch predictions. Yes, they are great, but they have certain drawbacks. One is that you need to know exactly how many predictions you generate beforehand. So it means that you need to have a finite input space. So in the case of Netflix know exactly how many users are there, and you just need to pre-compute on the recommendations for these users. If there's a new users coming, you can just give them some generic recommendations, such as an average or just the most popular movies. So another problem with batch predictions is that they can't adapt to changing interests, right? So for example, you have been using Netflix and you've been watching a lot of horror movies. So the recommendations are going to include a lot of recommendations for horror movie. But then you're feeling very happy today, so you want to watch comedy. So look into comedy category. You want to search for comedy movies. So you would think that Netflix would be able to change the predictions recommendation to show you more comedy movies, but actually Netflix can't, and it can only update the recommendations for you the next time you open the next time Netflix generates the next batch of recommendations. So for companies, a lot of them try to adapt to this by forcing the input space to be finite. So for example, TripAdvisors, when you open TripAdvisors, they first make you choose a city, for example, San Francisco or New York, and choose a category like inn, a hotel, or restaurant that can show you good recommendations. But if you try to enter some wide queries, such as high rating Thai restaurants in Hayes Valley, the result you receive is not going to be very good. Online predictions can help you overcome these drawbacks. And also online predictions can allow you to use dynamic features. So what are dynamic features? Static features are features that don't change very often, such as like age, gender, neighborhood, job, income. Whereas dynamic features are those you can change like very quickly. For example, like what am I reading right now? What am I watching right now? Because you can imagine just what am I reading or watching right now is very important to predict what I want to watch or read next. So to be able to do things, to do online predictions, you will need several things. The first is that you need fast inference, a model that can make predictions in the order of milliseconds. The second thing you need is a real-time pipeline, a pipeline that can process data, input into a model, and return prediction in real time. So the first, like for fast inference, there are like many ways, because there are three main ways to make it happen. So first is to make models faster. Second is to make models smaller. And the third is to make hardware more powerful. To make models faster, there have been many exciting approaches. And here are two of my favorite solutions I have seen as come across. So to make model faster, you can do things such as like you can fuse operations together, or you can like write specific kernels like to do certain operations. You can do dynamic tensor memory. You can so like compile a model to like optimize the executions on certain hardware. So here's my two favorite solutions. One is Apache TVM and another is TensorRT. Feel free to check them out. They're really awesome. To make models smaller, also known as model compressions, there are like many different approach. So so the most popular approach is pre-quantizations. It's like to reduce the precisions of the model. Precision is not like precision as in precision accuracy, but precision as in as the number of bits that you need to store a number. So usually, if you want to store a float, is 32 bits. So if you reduce the precision by half, then you need like 16 bits. A lot of companies currently using integer inference, so they usually store weight in integer, which usually takes up 8 bits. Another approach is knowledge distillations. It's also known as like student teacher network. So you have a big model that does something really well, and then you want to train a smaller model to mimic the behavior of this big model. Also, pruning is when you try to like set on the weight or activation that's not very useful to 0. And so lowering factorization, like you have a very large matrix, you want to reduce the demand. So you want to factorize this very large matrix into like lower ranked matrices. I think it's just really interesting. And when I just look into like what kind of model compression solutions are there, and I just found like 42 model compression open source projects. I think there have been more have been coming out since then. If you're interested in how to make models like smaller, faster, I highly recommend you check out this blog post by Roblox. So by using different techniques for model compressions and inference optimizations, they were able to improve their latency by like 30 times. Another approach to make fast inference is just to make hardware more powerful, so you can do inference of this hardware faster. And there have been many different hardware startups focusing on like both training and inference on both like cloud and on-device hardware. And this, I think, just a list of a few startups that have raised money recently, and you can see that they spread out all over the world, and they have raised a lot of money. The next part to allow for online predictions is a real-time pipeline. And just to highlight what a real-time pipeline is, I'm going to use a ride-sharing example. So imagine you're trying to predict whether a transaction is fraught with a ride-sharing system such as Uber. You might need features from various aspects, such as like you want to know about the specific transactions. You want to know about users' recent transactions, for example, over the last 7 days. You want to know about this credit card recent transactions. For example, like if this credit card had been added was added only 2 days ago, I have seen like 20 different transactions, and maybe it's a red flag. You also want to look at the recent in-app frauds, because maybe it's been a new way of like committing fraud, and maybe this is related to that somehow. So you want to use a lot of recent features. And the question here is that how do we quickly access these features? Because you don't want to put those features in some permanent storage like S3, because like each time you need to pull out these features, it's too slow, and you want to detect the fraud as soon as possible. So one way to do it is just actually store all those recent features into memory. So every time something happens, like every time users does something in app, for example, like fix the locations, book a trip, you can like add a credit card or contact driver or cancel a trip. You want to store all of them into memory. So for only the event, after like 7 days, or you can set like 7 days or 10 days, it's up to you. Once these events are no longer useful, you can either discard them or move them to permanent storage or S3. And this is exactly what a stream storage is. So the most popular solutions is probably Apache Kafka, and Amazon also has a very popular solutions. It's called Amazon Kinesis. And if you go on StackShare, you can see like hundreds of companies are using these solutions. So when you want to do online predictions, you need not just static features, you also need both static features and dynamic features. So static features come from like static data. So you can have data in something like CSV or Packet. Packet is a really exciting data format that I always recommend companies I work with to use. So for static data, it's usually bounded, so you know when a job finishes. But with streaming data, you just like don't know when it finished. It might never finish. So for static data, you can process them in batch, so using something like SQL or MapReduce. Whereas like for stream data, you want to process them as soon as they arrive. So you want to use tools such as like Apache Flink or Samza. So you can a lot of people like both in academia and in the industry, when you train a model, you usually train model using static data. So whereas when you do inference, you usually do inference on streaming data. So you can see that like there are already two pipelines. So you have one machine learning model, but like two pipelines. So for training, you have static data, you go batch processing and you extract features and you input into the model. And in doing inference, you have streaming data, you go through stream processing, you extract features and you input the feature into machine learning model. So it's actually a very common source of errors in productions, and it's especially common when these two different pipelines are maintained by different teams. So imagine, for example, the training pipeline is maintained by the machine learning team, whereas the inference pipeline is maintained by the DevOps team. It might seem like an overfetching example, but actually pretty common. So here's an example of Weibo. So before they actually have two completely different pipelines for training and inference. They call it offline pipeline and online pipeline. So Weibo actually spent a lot of effort into unifying this pipeline using Apache Flink. So you can see like on the top is a previous pipeline, and now they have like unified pipeline. And it's not just Weibo. We have seen that in companies like Uber, Alibaba, or Lyft. So if you try to talk about like stream processing, you might want to talk about microservices as well. So you must have heard about microservices. It has taken the world by storm the last decade, and going hand in hand with microservices, usually REST API. If REST API like doesn't mean anything to you, don't worry yet. We're gonna go over it very quickly. So for REST API, usually REST API is request driven. So what it means is that you have a client and a server, and the client sent a request via something like PostGet to the server, and server is going to return a response. So server has to listen for the request to register. So if for some reason the server is down, then the client will have to keep on pinging the server until it gets a response back, or it can have something time out when it doesn't work anymore. So it can get like really complicated. So imagine you have a ride-sharing service again, and you have like three different services. One is rider management, and another is driver management and price optimizations. So rider management needs to ping the driver management to get like understand driver availability, and paying the price optimization to get the price to show riders. And so the driver management needs to ping the rider management and price optimization so that they can tell like how many drivers they should mobilize, or what surcharge they can give drivers so they can encourage them to get on the street if they're like an overwhelming demand for rides right now. And similar with price optimizations, we tend to link both rider and driver to get information. So inter-service communication can get really complicated and can make it very slow with data transferring back and forth. So another problem with request driven is that because like each microservice manages their own thing, it's just no way you can, or it's it's gonna be very difficult to map the data transformation through the entire system to get a good pictures of like what's going on, it's gonna be very hard to debug. Like if something is down with price optimization, you need to go back into rider management and driver management to get a good picture of what happened and what causes. So instead of doing this like request-driven model, what if instead of like different services, microservices pinging each other, what if we have like on the microservices to like publish something to a stream, and whoever wants information from that service can just like subscribe to the stream and get the information. So now instead of having this mess of like inter-service communications, now everyone might publish and subscribe to a same stream and gets in and publish information they want and just gets information they want from the stream. So because now we have like data flow through this stream, so you can actually build a dashboard to monitor data transformation through the entire system. And this model is called PubSub, short for publish and subscribe, but there are also other systems for event-driven approach as well. A lot of companies have been doing stream processing, but also a lot of companies are not doing stream processing. And there are like a lot of reasons. One reason is that companies don't see the benefits of streaming. So maybe it's our system. The system is not as a scale where inter-service communications is a problem. And so you don't have to switch to the event-driven model. Or like the best predictions have been working just fine. And also because you have never done online predictions before, so maybe online predictions can help give you improvement, but because you have never done it before, you don't know that they will, and therefore you're not motivated to like change our infrastructure to do that. Also, like to switch from like batch processing to stream processing can require high initial investment on infrastructure, which a lot of companies are not willing to do, especially when they can't see the added benefits yet. It also like require mental shift from doing batch processing to stream processing. So like if you used to do things like in static data, it's very hard to like work with data that will never terminate. And also like a lot of tools in streaming processing right now is Java based, and a lot of people working with machine learning is like very comfortable with Python. So you need to switch to using stream processing. You will need to like work with tools that you're not familiar with, and of course there are tools that like let you handle things in Python, but it can be like, pretty awkward to use. And for the next part, is next level of real-time machine learning is online learning. So something I'm really excited about. So to begin, like online learning is different from online training. So online training is you can learn from each incoming data point, and it has a lot of it's very difficult to do because it can suffer from catastrophic forgetting. I talked to several companies, they have tried doing it and none of it ever worked. And it can get very, very expensive because like imagine you have some hardware that is capable of doing computations on like a lot of samples at the same time. So if you use that hardware to make the computation on only one sample, that can get very, very expensive and wasteful. So the companies that have seen that doing online learning successful in practice, they learn in micro batches. So instead of learning with every incoming sample, they learn with every incoming like 500 or 1,000 of samples. With online learning, one challenge it was evaluations, right? So the first step you want to do is do offline evaluations, so that you want to evaluate some models on some static data to make sure that it's not doing something crazy and like ruin everything. But the point of online learning is that you can adapt the model into changing interest, changing environment. So it doesn't make sense to test the model on something that is non-changing invariable. So the only way for you to really test the model is to like farm it out to different users and see how they behave. So the popular system is A/B testing, and it's just so A/B testing here is make it sound very simple, as you just need to compare like system A and system B, whereas you actually have to compare like many different versions of your system. So actually, it's just totally a startup idea. You can build a system to help companies do complex A/B testings with online learning. Many companies say also online learning that doesn't mean that you don't do offline learning. Many companies do online learning in tandem with offline learning so that you can produce a more stable system. So in traditional offline learning, the iteration cycle can take up to like months. Some companies can be really fast and in weeks. But when you do online learning, Weibo is for companies like Weibo, you can do it in 10 minutes iterations. So you can like extract new features. You can train models, and you can deploy the model within minutes. And it's been really impressive. I have heard similar number from other companies in China as well. There's different use cases for online learning. And the most popular use case right now is for recommendation systems. So the reason is that like recommendation systems problems have natural labels. So if you give users a lot of recommendations, you can just observe how users react to these recommendations and get the label from it. So like if user click on a recommendations, you know that it's a good prediction. If they don't click on it, so they look on it, it's probably not a good recommendations. I also just want to clarify that not all recommendation systems need online learning, because there are many systems that many systems that have very slow to change references. For example, like users' preference for houses, cars, flights, hotels are unlikely to change very quickly, whereas like users' preference for things like online content such as like videos, article, tweets, memes, they can change very quickly from seconds to seconds. And for this kind of systems that have like quick to change preferences, you want to learn user preferences very quickly. So online learning is going to be very important for this kind of system. There are other use cases for online learning. So one use case is for rare events. So imagine you have some events that like rarely occur, such as Black Friday for shopping. So Black Friday happens only once a year. It's really impossible for you to get enough historical data to predict what users are gonna do this year. To be really effective, you want to learn on the fly on that day, on Black Friday, like just from like the beginning, to see what users gonna behave, what users gonna do next. Also, like it can help you avoid the cold start problem. So imagine you ship an app to users because it is a new user. You don't have any data on that user to like predict what they like. So if you don't do online learning and you do offline learning, then you have to wait until the next time models is trained and deployed, so that you can like produce like relevant recommendations for that user. But like if you do online learning, then you can just like wait for users to like spend a few minutes on the app, and you can like get users to can show users very relevant predictions like TikTok does. And online learning is actually a very different, it's also like a very different mindset from offline learning. So if when you start looking into online learning, a lot of things that you know about offline learning are no longer true. So in school, I was taught that like offline machine learning is to train the model with sufficient number of epochs until conversions and evaluate on a static test set, right? In online learning, there's like no such thing as epoch, because you've seen each data point at most once. There's no conversions because like the data is like constantly shifting. You have no idea what the model should be converging to. And also there's no static test sets. You have to do like online testing, like A/B testing. So actually when I was looking into real-time machine learning, I was actually very surprised because a lot of great examples I found actually from China, and I haven't heard of this before. So I posted this thing on like link on social media. I know social media is not like legitimate evidence, but I think I started some really interesting observation from people who have been working with both Chinese and American company, and they have some of them has told me that they have observed the same thing as well. So if you have seen something similar, I would love to hear. So when we talk about the AI race between US and China, a lot of people have been like citing things like the number of papers, the citations, but also there's another very interesting metric is the adoption rate. So if you look at like firms that are adopting AI and firms that are piloting AI, you can see that actually the number is a lot higher in China than in the US. So it seems like there's the AI adoption in China is more mature, and maybe that's why they can build better infrastructure. There's also other reasons. So like somebody told me that I know a lot of this is like very hand-wavy. There's no scientific research behind it. It's a lot of this is anecdotal evidence. So please take it with a grain of salt. I would love to hear your feedback as well. So someone told me that like it looks like a lot of internet companies in the US are like old. And yes, they're decades ahead of Chinese companies. And one thing that come with that is that they have more legacy infrastructure. So like, every time they want to change the way they do things, they need to update the infrastructure. Is very expensive. Whereas in Chinese companies, they can just like build things from scratch, and it makes it easier for them to adopt a new way of doing things. And so it seems like there's a more national effort from China than in China than in the US. So I'm actually working on something that related to machine learning. So if you want to discuss more about it, please feel free to reach out. Thank you very much.
All right. That was awesome. That was super comprehensive. Thank you, Chip. We are going to head into a break, which basically means I get to chat for a little bit. You all can hit the bio break if you need to. I'll be here explaining a few things, and I get to do my favorite thing ever, which is give away a little swag. So if you want some swag, get involved. We have got all kinds of stuff happening in Slack, and there's already some people who have won something because they've been participating in the Slack. Now, let me mention a few things. So we've got the applied Slack, and there are a few channels that you all may or may not be in. We've got the funny channel, which is where you can put your selfie, your applied selfie. And there have been a few really good selfies that are already coming through. So I want to just highlight there is one person who put a funny selfie in already, which is Deepan Shu Sani. For that selfie that you put in, you get some swag. And you're probably wondering, like, what swag am I going to get? We've got a lot of cool partner swag. All of the partners have been really kind, and they donated a bunch of stuff. So let me share my screen real fast, and I will show you some examples of what you're going to get. You should be able to see my screen right now. You get, this is like the Algorithmia partner swag. You get that whole deck of stuff, all of that. The water bottle, the little tall can, tall boy. Oh man, this looks awesome. So then also, if that wasn't good enough, you also get some, what is this? A Monte Carlo hat. You get a Fiddler water bottle. You have a notable Loom cube to make your live streams or just Zoom calls look even cooler. Then you have a Tecton water bottle, a Tecton shirt, Redis shirt. There's so much good stuff here. So again, how do you win some swag? Well, you send over some selfies, and I have some examples of some selfies that have come through. Let's check these out real fast. You might be able to see some of the selfies that are coming through. This is awesome. And I know what you're thinking. You are probably thinking, how in the world can you call this one a selfie? That definitely was not taken by the guy in the right. And I have news that he was using a selfie stick, and it is a selfie. So that is how you can win some swag. Just make sure to hashtag applied selfie or put it in the funny channel. Yes, you can put it in the funny channel in Slack, or you can go ahead and you can make sure that you hashtag it on Twitter or LinkedIn and let the whole world know that you've got a great selfie. Remember, +1 if you get your dog or your cat or your gerbil involved, and another +1 if you got a costume that you're wearing and you want to get after that. So I already mentioned we have one winner from a funny selfie, and we've got a few more winners. Give me a sec. I'm going to find who else gets to get some swag. And so Deepan Shu, oh my, I'm sorry if I'm horrible at pronouncing names. Dipanshu Sani, your selfie gets you some swag. Please reach out to me. And Kaniska Mandal, you've asked multiple questions in Slack. And so we want to just highlight that the questions have been awesome. And we thank you for that. Please reach out to me or anybody from the organization team, and we will get you some swag. That is absolutely awesome. And the last one, the last winner for now it is Chuck Sugnet. Man, this is the problem with having an international conference, that I just butcher every name. So please forgive me if I'm butchering your name, but Chuck, you also are going to get some swag because of the contributions you have been making in Slack. Absolutely awesome. So thank you all for this. It's really cool to see as they come through. Now, the next step, and we're going to randomly be choosing more people for this, but the next step I want to mention is we've got a poll that will be dropping in Slack. So there's a poll happening in Slack. You can go ahead and click on it, and I'll give you a little story behind where that poll came from and why we are doing it. The poll is around questions that have popped up in the MLOps community. Remember, if you're not in the MLOps community, I highly recommend that you get in it. You can find some links to that in Slack and jump over there. But there's all kinds of questions that could pop up in the MLOps community all the time. One is, how much Kubernetes should a data scientist know? Another one is, MLOps is an organizational problem, not a tooling problem. Another one is, are Jupyter notebooks ready for production? Should we use Jupyter notebooks in production? Woo. So we wanted to have a poll, and we wanted to see where you all stand on these questions. Do you think that Jupyter notebooks can be productionized? Do you think that a data scientist should know Kubernetes? We also want to know things like how many models you've got in production. How are you doing this? Are you real time? Are you streaming? Are you batch, like Chip was just talking about? So that's the poll. Go ahead. It's completely anonymous. All right. We're not collecting emails or anything. So you can feel free to share sensitive data, because there's one last question at the end, which is like, have you ever had a model go rogue? And I love that. It's absolutely hilarious to hear war stories. That is in Slack. Go check out the links for that. We also are throwing links to fill out a form for the best talk that you've seen all day. So the best talk today or tomorrow, go ahead and, today, I mean, the best talk. And even if you're just staying for a little bit longer, throw in what the best talk that you saw was, so we can give the speakers some swag and we can spotlight them for having an awesome talk. We've got a few different things like best talk, best slides. And so there's that too. So we've got two different kinds of forms. We're going to be sharing all of this data with you tomorrow at the beginning of the event tomorrow. So go ahead, put the polls in, expect to see that later. All right. So I think that is it. I want to see some selfies by the time we get to break number 2. And coming up next, we've got the good folks from DoorDash. So wait around a minute and we will be getting the great people from DoorDash to come on here.
All right. Hi, everyone. Welcome to the Scaling Online ML Predictions at DoorDash session. My name is Heen Liu, and I lead the ML platform team. In this presentation, I will present the first part, and an engineer, Abbas, on my team will present the second part. As for the agenda, first I will share a little bit about the DoorDash marketplace, then briefly talk about a few interesting machine learning use cases here, then discuss some details about the approach and the strategies we use for building our ML platform. And then Abbas will talk about the main part of the presentation, which is about scaling the online predictions. And then we'll wrap up with the lessons learned and the future work. So DoorDash's mission is to grow and empower local economies. And we do that through a set of product offerings. The first one is delivery and pickup, where customers like you and me, we can order food on demand for breakfast, lunch, and dinners, or for various parties. And second is the emerging product called convenience and grocery, where customers can order non-food related items, such as flowers, maybe charcoal for the barbecue, or maybe sugar for baking cookies. The third product is called Dash Pass, which is a subscription product that is similar to the Amazon Prime. DoorDash also provides a logistics platform that powers the delivery for some of the notable merchants that you see on the slide here, like Chipotle, Walmart, or Target. DoorDash platform is a three-sided marketplace, and like most marketplaces, it also has the flywheel effect. Starting from the center and moving to the right side, as we bring on more customers, there will be more orders. That creates more earnings opportunities for Dashers, and that improves the delivery speed and efficiency for the marketplace. And then starting center and moving to the left-hand side, as we have more customers, then there'll be more revenues for merchants. And as we have more merchants on the marketplace, the more selections there are for the consumers to choose from. As this flywheel speeds up, it brings benefits to all three parties. It drives more growth for merchants, creates greater earnings for Dashers, and bring more convenience and selections for our customers. Before going into a few ML use cases at DoorDash, let's discuss the primary concerns of each of these parts of the three-sided marketplace. At the top, we have merchants. They would like to increase the reach of their business and increase their revenue. And bottom right, we have customers that want convenience of staying at home while having access to a wide selection of items from their favorite merchants. And in bottom left, we have Dashers that want flexibilities in how they work while making good earnings. So the first use case, let's start with the consumers, where there we have search and recommendations. In terms of search and ranking, we would like to show the most relevant results from the customer search query. For example, when a customer searches for Italian food, how do we best rank the restaurants in respect to the distance, the quality, and the customer's past order history? And for recommendations, we would like to provide a personalized food ordering experience for our customers by surfacing up the best stores for them. And for merchants, we want to help them to maximize their sales by providing targeted promotions for certain items at certain time of the day. For example, a promotion about a few dollars off from a certain pizza store between 6 and 9 p.m.s. And for Dashers, how do we best spend the right amount of money to bring new Dashers onto the platform? And once they onboarded, how do we mobilize them to come out at a certain night of the week due to high demand, or moving the Dashers to the right locations to satisfy the demand of the marketplace? For logistics, where there are many interesting and challenging machine learning use cases, its primary job is to dispatch the right Dashers at the right time for the right delivery to maximize the marketplace efficiency. The prediction of food preparation times and travel time estimates has a few interesting nuances, for example, like traffic and weathers, but we don't actually have control of. Another interesting challenge is, unlike Amazon orders, food orders emerge on the fly, and the food quality plays an important role in the delivery. You know, the extra 5 minutes could be the difference between a great meal versus an awful one. Regarding our machine learning platform journey, we started about a year ago, when DoorDash decided to invest in building a centralized platform. As you know, different ML teams have slightly different needs. So it's very important to establish the buy-in from those teams on the idea of a centralized platform. One of the ways to do that is to have a representation from each of these teams, as well as an open forum to voice the collective needs, opinions, and also and be open to the contributions to the development of the platform. The collaboration model that we established include a machine learning council. It is responsible for making the cross-functional team decisions, such as build versus buy. It also acts as a glue for all these teams to work together and learn from each other. We don't claim this approach is the right one, but the one that works for us so far. These are the pillars of our platform that models after the machine learning development process. And it starts with feature engineering all the way to model predictions and insights. The approach we use in building these pillars starts with thinking big, right? Start with customers and work backwards to put together like a product vision document. Start small, building these pieces out incrementally based on the needs of the community, while keeping an eye out for the long-term vision. In addition, our strategies include velocities. How do we accelerate the machine learning development process? What projects or initiatives will help with this? We also want to build a cohesive set of pillars that work together seamlessly to provide the best experience for our ML community. And the last one is ML observability. We want to catch and prevent features and model-related problems before they happen, such as feature qualities or model prediction quality. We use these strategies to guide and help us in the prioritization of the effort of building our ML platform. One of DoorDash's culture values is about customer obsessed. And as a platform, we're only successful when our customers are successful. So all these parts, the architecture, the strategy, the success metrics, are all designed with that in mind. So now I would like to hand over to Abbas to talk about the scaling ML online predictions.
Thanks, Ian, for walking us through the machine learning platform at DoorDash. Hi, everyone. My name is Arbaz, and I'll be talking about scaling the prediction pillar. As an AI platform, you've done all the hard work of building an end-to-end pipeline and serving models in production. As user growth starts to pick up and as company grows, the question is, will you be able to keep up the requirements of the scale? How are you going to keep costs in check while you're scaling out your systems? A model prediction is just one pillar of the machine learning platform, but for companies' day-to-day operations, it would be the most scrutinized one. With that, let's talk about scaling. In the current world of infrastructure as service, scaling is deemed trivial, assuming perfectly distributed systems. With this assumption, we think we can handle any kind of throughput requirements. The solution just scale horizontally. In reality, though, it's not a simple math game. And things start breaking much earlier than infinity. So the question one would ask at this point that how can I prepare myself to grow fast and meet all the scale expectations reliably? Now, there is no silver bullet or a fail-proof handbook to get you there, because there will always be a new problem you discover. But I have a short answer to this problem at this point. That how can you prepare for reliable growth? Here our journey. Here is talk today about the problems we faced and how we went past them. Oh, let me actually make it better. That keep hearing everything we share now on around our journey of building and evolving the machine learning platform. All right, done with the shameless plugs. The elixir, the portion here is just to keep doing what all of us are doing right now. Just like attend enterprises, narrate their experiences, and share our own. It's DoorDash's turn today, so let me do the honors. So I'll start first with the anatomy of a prediction to help build an essential workflow. This will be our common base for any further discussion. Then we'll start to scale this essential workflow and see things break. And as things will start breaking, we'll try to tackle and wrestle, try to survive this collapse. You can expect a few wrestling picks there. And then finally, we'll talk about the challenges going forward. So here's a sketch of a prediction, just to understand the fundamental aspects of what's going out there. So the inputs for a prediction are the feature set and a model. The output is obviously a prediction score, and it's all mediated via a computation. Now, if I were to convert each unit into a scalable module, this is how it will look like. The computation engine can be horizontally scaled if it is put in a microservice deployment. The feature store and the prediction store, they're queryable, and so they're put as a data store. Now, since we're talking about production and a microservice, there's one important piece to be added here, which is monitoring and observability. We've got the essential design in place. These would be the core elements involved in scaling from a machine learning infrastructure perspective. And this is what we're going to discuss, like these particular elements. And so before we talk about the how of scaling, let's talk about the why and the what. So for the why we needed scaling, so one thing was to support more models in our framework. That was the first thing. Second was, as models get used more often, either due to the impact on the business use cases or they add new use cases, we want to be able to seamlessly support that. Third, we wanted to thrive and not throttle our callers when the product grows. And then last, incidental growth. We wanted to not be a bottleneck for incidental growth. What is incidental growth here? It's a situational uptick in demand. So for us at DoorDash, the last year, it was the pandemic, the IPO that we went through, or the Super Bowl teasers. That was what caused a situational uptick in our demand. Now, what exactly needs to scale? First, increase number of computations per interval. That is a throughput increase. With each prediction, you need features. So the features will have to, the feature QPS will have to grow synonymously. And also, as more features get added, some of these features are high cardinality. The another dimension to scale is the payload size of a prediction request. If a model demands for it, we need to be able to support it. And finally, allow more models to be stored and looked up. It feels that the top two are the more significant one for the more general use case, and at least for DoorDash it was. And that's what I'm going to now next talk about, that how we did the scaling for these two particular aspects. And we're going to do it through a time travel. Mind you, it won't be a smooth ride though. It will be a bumpy ride. We'll describe each bump that we hit and how we went past that bump. Right, so it's March of last year. That's when we finished building a machine learning platform. It was in its first phase. We have 2 models out there. We're making 1,000 predictions per second. And once the machine learning platform POC was established, our customers gained trust, we gained confidence, and things started to pick up quickly. As you can see from the graph here, by the time we hit June, we were at 16 models and making 15,000 predictions per second at peak. Now, also, there was other developments happening around the world at that time. The pandemic had started taking full effect, and DoorDash, being a food delivery industry, was seeing volumes escalate. However, our systems were also pushed harder. We started seeing pronounced effects of cannibalization. What is cannibalization? That some models consume more resources than the others. If you look at from the top to bottom, you see the highest latency that we saw for one of the use cases was 50 times more than the lowest one. And so the thought there is that, is the lowest latency model, the low latency model, is it getting overwhelmed because most of the resources are consumed by the high latency model? And so we start to think of isolation, divide and defend. So when I said expect some wrestling picks, I was not being figurative. Here's an actual wrestling pick. So Big Show, as he is one of the biggest wrestlers in World Wrestling Entertainment and the federation that does wrestling. As the name suggests, he's meant to be like a dominating wrestler. His size commands his competitors to collaborate to take him down. Like usually one competitor is not enough. Here are two wrestlers that you see trying to take him down or trying to defend themselves in the process. And that's what we are going to do with the problem. We have this like large set of requests coming in. So what do? We begin sharding at the most overwhelmed connections. We start to make a clean divide in the system, all the way as far as possible, so that one use case does not overwhelm another. We have grew shards and we hit 6 figures in peak predictions per second. Also, system layout now starts to look more like a model serving farm. Notice though that all this time there's this one shard which is taking more load than the others, the one with the red connections. And so that is what we call a fat shard, which is taking much more traffic than the others. Just take the case of recommendations for elaboration how a fat shard could come into being. When ranking content, in the case of DoorDash, for feed, homepage feed or carousels, you're doing thousands of predictions for a particular customer because you are ranking thousands of stores as compared to less than 20 for a cart recommendation, which you're just like considering the items in the menu of a restaurant. And so you'd expect that a feed ranking algorithm or feed ranking model will be hit much harder than a cart recommendation model. So this is when we hit that tipping point that one of our shards started growing much faster than the others. We were hitting AWS hardware limits. It was that big. We couldn't scale horizontally any further, but we still needed the predictions to keep flowing. And that's when we had to take our second tactic, which is beefing up. WWE was trying to promote a new wrestler some time back in the form of this wrestler called as Roman Reigns. They were giving him too many high-profile fights so as to gain reputation, but he didn't gain any fanhood regardless. So what did they do next to him? They tried to beef him up to make him look better, to make him more likable in the WWE audience. That's what does it mean for us? For us, it means that we have to run some exercises on the fat shard, make it leaner and more powerful. And so how do we do that? We do a bunch of optimizations. We try to go through this like whole round of observations and iterations. For microservice optimizations, in the observation part, we'll do some load testing simulations locally and in production and try to understand our limits. Also, we'll increase our instrumentation to closely understand bottlenecks. We'll do things such as latency profiling, or this more specifically because we use gRPC-based microservices, we use gRPC tracing as a way for more observations, more understanding of what the bottlenecks are. And using this observations platform, we could exercise a few iterations and discover what works best. So there were some low-hanging fruits. We tuned the configurable parameters, such as the sizes of our payloads and how we batch our requests together, how much should be the batch size. Other things such as the timeouts that we put on the connections. And a little more further, should we disable or enable bandwidth optimization? And then there were like more involved optimizations, which involved things such as aggressive compiler optimization flags or payload compression when sending requests. On the feature store side, we did similar observation iteration cycles. For the observation part, we did benchmarking where we tried to see that can we replace a feature store, which was an in-memory feature store in the form of Redis, with a disk-based memory store, and see if we can get more performance out of it, if we can cut the size of our cluster to be much smaller if we switch from an in-memory to a disk-based store. Too bad we found out that in-memory store is our cheapest solution and the most performant solution. So we started to re-engineer a feature store and do some optimizations natively within, in our case, Redis, discovered some cool concepts there, which we have published a lot out there. And so with all these optimizations, it started working, and we breached the magic number of 1 million predictions per second, and the system was running stable all this time. It was a major accomplishment for us because we were able to take it even further. We were able to hold up traffic to even 2 million predictions per second. But it was not the end of our problems. There was one major unknown that was going to come to life. At this point, we had started hitting scales that would impact the entire DoorDash infrastructure. Mind you, the entire DoorDash infrastructure, because of one service. Think of implications such as bringing the entire site down because one of our service deployments went haywire. And this is not something that the wrestling world didn't teach us, though. Big Show, our biggest wrestlers of the generation, when got suplexed over the top rope by a beefed up Brock Lesnar, the ring broke with their combined weight. And this is what happened to us. A beefed up prediction service was facing this high volume of requests, and our infrastructure stifled as our logging and metrics infrastructure started breaching the limits. A console, a service discovery module got overwhelmed by our deployment so much that all these pods that we had spun up, they started continuously sending requests and updating their addresses, because of which all of the services were impacted. And so all of these things become part of that whole impact that infrastructure can have if a service grows that big. One of our third-party vendors called Segment for streaming, they started blocking us for sending too many events. This is what happened at that time. And so what did we do? We tackled them one by one. We started to cut our logging to bare minimum so that we just send only the logs that we need. For our observability, we moved from a pull-based monitoring framework in Start3 to a push-based monitoring framework, that is Prometheus. We migrated away from a third-party streaming vendor to an in-house Kafka solution. Also, to help our service discovery module, we reduced our total number of pods employed by scaling them vertically, like increasing the number of vCPUs instead of increasing the number of pods that we had. And so this conscious and sampled use of resources allowed us to hit much larger volumes, 6 million plus predictions per second, which was great. It was part of a load testing for Super Bowl, and we were able to sustain that. However, there's still things that need to be taken care of as we try to strive for more and more growth. There will be these bottlenecks that will come to life again and start to push us to do more optimization, more scaling up. So if you were to ask me in all this process, what were the 3 key takeaways? First is that isolate your use cases that don't overlap so that they don't overwhelm one another. If there's one use case that's being overwhelmed, it won't affect the others. Second, introspect. Keep your costs in check. Keep that testing going, profiling, benchmarking, and reserve that time to scale up rather than scale out. And then lastly, note down your dependency that you have in the infrastructure and think of the implications that it can have, because those could be real serious ones. With that, I'm going to hand it over to Hin, who will walk us through the last leg of this presentation.
Cool. Thank you, Abbas. As Abbas mentioned, the prediction service is a part of the production traffic flow. So ideally, it shouldn't cause any outage if something went wrong while fetching features from feature store. So therefore, it's very important to have the proper default values in place as part of the model setup. For the second bullet point, in addition to collaborating with our ML teams closely, we also strive to understand the business problems that they're trying to solve, as well as the business impact. And for the last bullet point, we're building our platform incrementally, and it gives us a lot of opportunities to receive feedback, so we can make the necessary adjustments along the way, and that has been really helpful. For future work, as mentioned above, the prediction volume is increasing over time. So we look into the potential of caching the feature values as well as the prediction values. For the second one, so far most of the machine learning use cases are based on the structured data. Moving forward, we see more use cases in the areas of NLP and image recognition. So we need to extend our platform to support these model types. And for the last bullet point, as the ML platform adoption increases, we want to provide an easy and optimized way of making prediction requests for our customers. So that's all we have for you today, and thank you for attending this session. There's a link there to the DoorDash Engineering blog that you can find out very interesting blogs that Abaz wrote and many other blogs.
Excellent. Thank you both. There is a lot of chatter happening in Slack on that talk. That was incredible. So hopefully you can answer the questions that are coming through there. I know there's a lot of interest. It's really cool to see. So thanks again. And next up, it is my pleasure to introduce Dr. Walid Kadus. He's the head of engineering for Anyscale. Prior to Anyscale, Walid worked at Uber, where he led system architecture and evangelized machine learning. He led the location and maps team. So he's a multitasker. He previously worked at Google, where he founded the Android location and sensing team. Today, Dr. Walid will share his outlook for the third generation production machine learning architectures and share case studies of how Ray is being used in all that. Walid, it is a pleasure to have you here. And paging Walid to the stage. There he is. All right, cool.
Yes, thank you so much for the introduction, the warm introduction. Cool.
No problem.
Excellent. So it's really great to see you folks today. I'm really excited to share some thinking that I've been doing recently about where our production ML architecture is going. Let me just start presenting my slide. And hopefully everyone can see that. So let's dive right in. Cool. So I'm just going to cut to the chase and say what my conclusions were. So if you look at how production ML architectures have evolved, the way that I see it is that it's had a first generation, which is kind of like a fixed function pipeline. The second generation being a programmability within a pipeline of particular existing actions. And the question is, what's the third generation? And what I will assert is that we can use history as a guide to help us understand where it's likely that production ML architectures are going. And my assertion is if we look at the history of the evolution of GPU programming architectures, it will give us a guide to where the third generation of computer programmability and production ML architectures are going. And so after that, I'd like to introduce you to Ray and ask the question, is it possible that Ray and systems like Ray that make ML much more programmable, the next generation of programmable architectures? So my plan from here is just to quickly review GPU programming history and compare that with the evolution of production ML architectures. I'll talk about Ray and what it is, and then show how Ray is being used to build existing applications in a different way, but also enabling new applications. And I've left some time at the end for folks to ask me questions, so please don't, so I'm ready for that, and we'll have a few minutes at the end for Q&A. So I mentioned earlier on production ML architectures. And to be concrete about that, what I mean are systems deployed into production that operate at considerable scale. And I was tuned into the DoorDash presentation just before this. And as you folks saw, they were doing 7 million predictions a second peak, or 6.8 million. That's the type of thing that we're talking about when we're talking production ML architectures. One characteristic, as you saw just in that talk, is that they often require distributed training and distributed inference. And that distributed character is more or less universal now in production ML architectures. So what we're going to do now is dive into the history of GPUs. And this is a topic of some passion for me. And I'll try to keep it super basic, but I hope that it will provide sufficient insight for us to kind of see what the future might hold. So going back to the mid to late 90s, we saw the first generation of GPU programming architectures. And that was things like OpenGL 1.0 and Direct3D. And as input, you would have things like textures, polygon, meshes, that type of thing. And it would go through this pipeline of transform, clipping, polygonization, and then pixel operations. And finally, what would pop out at the end is this beautiful 3D image, right? And the revolution that happened with that first fixed function pipeline is that this was all hardware accelerated. And that allowed for basically the first time that consumers had accessible hardware accelerated 3D graphics. And that really massively expanded the possibilities. And that's what started the 3D gaming revolution with games like Quake and so on. The flexibility, though, came from the choice of the inputs. And there was a little bit of configurability in tweaking the pipeline, like, hey, where are the light sources and that type of thing. But the downside of this was you could not do complex effects. And if you wanted to do something more beautiful or artistic or creative within the limitations of that, they were out of reach from hardware acceleration. You got what you got with the hardware. If the hardware supported, I don't know, shadow buffers or something, then you got that. But if it didn't, right? So it was constraining to people. And that led to the second generation. And what I mean by the second generation now is that the pipeline stays the same, but you break the pipeline into sections with programmability within those sections. And some of you may have come across the term vertex and fragment shaders, and this is exactly what happened here. So vertex and fragment shaders are nothing more than small programs that run in hardware. And this is, about the time of Direct3D, OpenGL2, this started to happen. So they took that existing pipeline and made it more programmable. So to look at that, now you have a bit more flexibility. You have programmability within the pipeline. And these programs would be written in a C-like language. The two most popular at the time were the GL shading language and the high-level shading language from Microsoft. They were very similar, but from different companies and groups. But you still had to conform to the existing pipeline. So let me just go forward a slide and we'll come back to this one. This is what I mean. If you look at the formats between these different sections, it itself is pretty rigid, right? Like you have the vertices and geometry coming in here. Out of here pops vertices with a set of different properties that the vertex shaders have produced. And then finally, the fragment shader pumps out pixels at this end, also known as fragments, that get to the display. So these formats at these different stages are fixed. And that itself is where the limitation is coming now. But this is when we started to see something very interesting happen. This was the beginning of the GPU movement, that being general purpose GPUs. And so you can look at GPUs and those vertex and fragment shaders, and you know that it's Turing complete, right? Like every computation is possible in those vertex and fragment shaders, but there's a big difference between possible and easy. And so what happened is people started to write libraries for doing things like physics, but they were forced to take the problem that they were working on and make it conform to this weird combination of vertex and fragment shaders. And so I think that basically, it was a step forward, but it also indicated that people wanted to be able to code more generally for these things. And so as we mentioned, now you can actually go to a website and you can type in a small little program. This is just an example of the programmability for a fragment shader. And there would have been equivalent programs for vertex shaders. All right, now we come to the third generation. And the third generation, which examples of that are things like CG and OpenCL, is basically says, forget all of that. Stop worrying about pipelines and everything else. We're just gonna make it completely programmable. And when you think about that full programmability, you first realize that, basically the first generation and second generation pipelines, this is a superset of that. In fact, what happens is the first and second generation pipelines become libraries in this new system. And that kind of enables you to do some fascinating things. The interface now is just a programming language that for all intents and purposes looks like a normal day-to-day programming language with some extras for parallelization. And this really led to an explosion of applications. And this is what all of the modern deep learning infrastructure is built on, is this change that happened to complete programmability. And that led, to give you a chain, CUDA was another one of these early languages that led to CUDNN. Caffe was built on CUDNN. Caffe led to Torch. Torch led to PyTorch. And that's one of the most popular machine deep learning libraries available now. But you've heard me mention libraries a few times. And it's really important to understand this shift in focus, right? Originally, when you would talk to people in the games industry, they would be talking about OpenGL and Direct3D and writing code that runs on OpenGL and Direct3D. But over time, because of this programmability, this flexibility, people use engines like Unity or Unreal Engine 4 to kind of rate these games now. The GPU almost becomes a detail. And what this does is you've now taken that GPU and made it so that people without that level of experience of understanding pipelines and vertex shaders and fragment shaders and transforms and clipping can just use it like a normal code library. And that's really what opened up the GPUs that led to the Cambrian explosion of deep learning. And what's happened is no one talks about OpenGL now. Nobody talks, people do, but they talk about Unity, and OpenGL is just a way of getting to the compute, right? And when I say nobody's talking about, maybe that's a bit of an exaggeration, but just a little bit, right? So this is a Google Trends showing, popularities of the term OpenGL descending over time and Unity increasing in popularity over time with a crossover around 2000 and 2010. So literally people are not worrying less about the architecture and focusing more and more on the characteristics and the libraries. So to give an example, this is code for doing a Mandelbrot fractal. Mandelbrot fractal is this very beautiful shape that some of you may be familiar with. And this at the time was revolutionary. Instead of doing maths on the processor to work this out, you could write this tiny little program that didn't look much different from C. And all of a sudden it would be hardware accelerated. And all of a sudden you could do Mandelbrot sets at amazing resolutions in real time because of this. All right, so I can completely understand if some folks in the audience at this point are going, I came for a machine learning talk. Why is this guy going on about GPUs and all of this kind of stuff? And aside from our current machine learning revolution largely being built on these hardware accelerations that came from this previous generation, my assertion is that this can be a guide to history. And this can be a guide for us, right? Like history, one quote that I like is that history doesn't repeat, but it sometimes rhymes. And I'm wondering if there's a rhyme between GPU programming and where we will see ML production architectures go. And so when I look at this, I actually see surprising similarities with that transition. And so what I'm going to do now is I'm going to walk through the evolutions of Uber's ML production architecture. And I think you got some hint of the magnitude of that architecture from DoorDash's previous presentation, right? And that's, Uber Eats is just one small part of Uber. So you can imagine that the concerns there about ML architecture are even greater. And actually, as a side note, that's where I got to work with Mike and Jeremy, who were actually the founders of Tekton, the organizers of Apply. I was there as an ML evangelist while they were actually doing the hard work, not just opening their mouth, but actually writing code. So I'm going to use Uber as an example to walk us through this and their system, Michelangelo, but you can feel free to apply your other systems. I think it very generally describes a lot of the other production ML architectures that exist. So the first generation is described in an Uber engineering blog post from 2017 that you folks can look up. And this is a diagram from that paper that shows a pipeline, right? And it's the very standard pipeline that many of us are aware of, a little bit of data preparation, you put some stuff in feature stores, you have a batch trading job, you have a repository for the models, you have offline training as well as online inference as well as offline inference. This kind of get data, train models, eval models, deploy and predict and monitor, right? Like this is very much the standard machine learning pipeline that we use for supervised classification and learning. So as I was looking at this and reflecting in preparation for this talk, I kind of looked at that and said, all right, that looks surprisingly familiar. So in much the same way that you get data, train models, eval models, deploy, predict, and monitor, you also have exactly the same thing. It reminded me of the GPU architectures, that very much fixed function pipeline. These are the stages, and the output is finally a classification. Instead of inputs being vertices, it's features, and the output is a prediction, right? But it had that same kind of linear progression character. Then we come to the second generation. And I was looking in preparation for this talk in the 2019 blog post. So you can see first generation 2017, second generation 2019. And they themselves described the first version of Michelangelo as essentially a monolithic architecture that managed tightly coupled workflows. And that they were finding that this was limiting what they could do and precluded serving of models. And so basically what that led us to do was to think about Michelangelo in a different way. We separated it out into components where, just like before, the interfaces were standardized, but you could put your own module in. And so this is a picture from that blog post that shows that exact same thing. So I'm going to flip forward and flip backward just so we can have a look at it. So this is a generation 2 GPU programming architecture. And this is the generation 2 Uber Michelangelo architecture. And you can see the similarities, right? They basically made it so that you could replace the first part of the pipeline with any of the standard tools that any of us prefer to code in, scikit-learn or Spark or so on, right? And then the second stage, the model training, again, you got this kind of library effect where it was pluggable and you could write bits of code. So I at least saw the similarity there and thought, interesting. So let's now ask, if mostly where we are right now is in the second generation, let's ask the question, what would the third generation look like? And what I would suggest is, number one, just like before, it can do everything that the first gen and second generation libraries can do, as pipelines can do. The interface is a programming language. At least in the case of GPUs, it led to an explosion of applications. So there's the potential here to have that same explosion of applications. And the key change is the focus of the shift to libraries, right? So you could argue then that the focus is now on libraries. The compute engine is just a detail now, just like the way people started to think about writing games and so on was in engines like Unity and so on. It has the potential to open up power of machine learning to a huge number of users, and it moves the focus away. So you don't need to know what a P13 16x large EC2 instance is, right? You can, that's just a library function that you have to deal with. And so you don't have to worry about the details at that level. So that brings us to Ray. And what I would like, Ray could be considered as one of these third generation systems. Let me make the case, let me introduce you to it. And I'm not trying to shelve for Ray here. I am trying to suggest that there's a new way for us to think about machine learning, but Ray is a convenient example. And might give us hints about what we are going to see in terms of the evolution of ML production architectures. So Ray is basically a simple and flexible framework for distributed computation. And what makes it simple is that you make some minor annotations to functions and classes in, say, a language like Python. And all of a sudden, those same functions and classes can be deployed in a distributed manner. And what gives it the flexibility is that it's not a batch model at all. Tasks and actors can create new tasks and new actors, so that you can have a more dynamic creation of functionality. And there's not a huge cost to creating a new task or a new actor. And that allows you to think about the problem in vastly different ways. The second thing that makes it up is that it's a cloud provider independent compute launcher autoscaler. So once you've described an application in Ray, it will then take that and kind of work out how to distribute it on your favorite cloud provider. And then just as importantly, and hopefully by now you have some intuition about why libraries are so important. It's an ecosystem of distributed computation libraries built on top of that API in the first case. So just to show it diagrammatically, at the bottom layer, you have your favorite compute service provider, whether it's AWS or Azure or GCP or whatever, Kubernetes, whatever you need. You have Ray, which acts as an interface for these machine learning libraries to run on those particular things. And then you have that family of of machine learning oriented libraries. So there's some that are native Ray libraries designed from the beginning to run on top of Ray, but there's also a very healthy ecosystem of third-party libraries that includes many of our favorite things when we build ML models. Yeah, so that's kind of a quick overview of Ray. Ray's that little layer in the middle that that makes it easy for people to write distributed ML libraries and then takes care of the distribution of them across machines for you. So how does this fit with ML? So I think one way to think about it is this third generation is about making ML programmable and tackling the problem of programmability. But what we also discussed is that it moves the focus to libraries. So when you're using one of these libraries, you don't have to worry about the details about how the distributed computation is happening. You focus on the algorithm in much the same way that the third generation of GPU architectures allowed you to focus on the algorithm, and you now had a library of systems that you could use, just like folks shifted to Unity or PyTorch or whatever the library was. So with that, I'm going to take a moment to, that's been a description of Ray. But let's evaluate whether it's actually being used in the way that we're describing, right? Let's evaluate whether it's showing similar properties to what we saw before. So I'm going to talk a little bit about 4 different ways that Ray was used. And the first is that it's going to be a simpler way to build first-gen and second-gen pipelines. As you may remember, that was one of the characteristics we saw, that the standard pipelines just become a library in that. The second one is as a tool to parallelize high-performance ML systems. The third one is around making ML accessible. And you're starting to see the themes, like very much what we saw in the case of GPUs, we are now seeing in ML. And then the final one is this little thing about winning the America's Cup. So we'll get to that. So let's talk about its use as a simpler way to build first and second generation pipelines. So we mentioned earlier that one of the reasons to use this is basically you can implement existing systems more efficiently and allow for more sharing and distribution you get basically out of the box. So just recently, Uber basically shared its use of Ray to essentially show what Michelangelo 3 would look like, right? And what they said in their recent blog post was that it allowed them to treat the entire training pipeline as a single Python script. And that made it so much easier for them to work with and so much more intuitive. But what's even more interesting is that they themselves mentioned the concept of the ecosystem, the importance of libraries, and a standardized way for people to write machine learning libraries, both within Uber and also at the industry at large. So you can kind of see it show that thing that we talked about earlier, which is that the existing tasks that you're trying to do get a little bit easier. There's no, you can do the things that you can already do without too much trouble. It's just expressed rather than in the standard pipeline of stages, you just write it in code. So let's talk about the second use case now. The second one was really around high performance ML systems. And so there's a company using Ray called RoboVision, and they wanted to run a vehicle detection using 5 ML models running concurrently. And it didn't easily fit on a GPU. They could make it fit, but they had to cut their models. So they tried to just use standard Python to do it. And then even on a single machine, they were able to parallelize it using Ray and get a 3x performance improvement on the same hardware. And the thing is, I'll show you the code in a moment, or pseudocode for that. But I want folks to think about if you didn't have something like Ray, how would you do this? Would you convert each ML model into a microservice, for example? It's definitely doable. I mean, it's not like this is the first time, someone's done stacked models, but just think about the complexity. So this is the basic pipeline of what they were trying to do. They were trying to process images and output classifications about what the vehicles were and what they're going. And they took each of these things and wrapped it in array actor. And that gave them a lot of, an actor is just the basic primitive in the language. That gave them a lot more flexibility and especially gave them an accessible way to get to the GPU. And obviously I don't have enough time to go through the code, but it actually is surprisingly easy to do this, right? So this is the code. There's this little annotation at the top to describe a class called model. And then you have subclasses that you change the computation for. And basically what you do is in each case, you just specify who's next in the chain. And then you just feed the input to the first one, and then they land at the result collector, the thing that's actually capturing the data. So we took a relatively complex stacked model, wrote it in this way, and it can run on your local machine, but by changing the cluster that it runs on, all of a sudden it's distributed. And instead of trying to run 5 stacked models on one machine, you're running 5 stacked models on 5 machines, each with their own GPU. And Ray is taking care of all of the coordination and setting up those 5 machines. So a third example that I wanted to share was around making ML accessible. So there's a company called Descartes Labs, and they provide geospatial data analysis. And what people want to do, let's say that you are looking at images all over the world and you're trying to look at the ocean and find piles of garbage that have come into the ocean, right? Where is the garbage around the globe accumulating? So how they use Ray is that they create a simple interface like this, where you write a little bit of code on the left-hand side. You might be looking at a particular area. You develop your algorithm looking at that particular area, and then you click execute it. And for all intents and purposes, you can take all of the data for the entire world and run that same algorithm to identify all of those locations. And so what we see here is that Ray is enabling a small startup to analyze petabytes of data at their users' behest and making machine learning and data processing more accessible, giving access to that massive distributed computing power. And so the final example that I'm going to give is undertaking ML projects that don't fit the standard ML pipeline. And so I want folks to think about things like reinforcement learning. And we had that very standard pipeline earlier on, but there are some things about that pipeline that kind of don't make sense for reinforcement learning. You may want to update your values and your behavior online. And so that means that you have a feedback loop. You're updating your model every minute, every 2 minutes, right? Those types of things are not so well supported in the pipeline. And so there's a lot of things that are not that simple. So what I'm going to talk about now is a company called Quantum Black, which is part of McKinsey. And they actually used Ray to build the algorithms that helped that team win the America's Cup. America's Cup is a big deal in the sailing industry. It's one of the world's oldest competitions. But here's what they did, just to give you some idea. They built an AI sailor using RL on RLlib, which is one of those libraries. And so they trained a reinforcement learning sailor. And then what they did is they trained a reinforcement learning boat designer. And the sailor was really strong and the boat designer was really strong. And now you can play these two things off each other, right? You can take the boat designer and the sailor, and the sailor builds a new, the sailor designs, the boat designer builds a new boat, the sailor tries it out. And this allows you to analyze 10 times as many designs as you would be able to if you had a human in the loop during evaluation. And they themselves comment on it enabling them to run training jobs across dozens of systems with a few lines of code. And so that shows the potential there. But the question I'm asking is, if you wanted to build something like this on the conventional production ML architectures, and yes, they used quite a few machines to run these analysis, right? It does meet that property of inferences that we said earlier. How would you design that? What architectural support would you have? And this is what I mean by the third generation allowing flexibility and new applications at a distributed level that would have taken much more time if you had to code them natively. So in conclusion, the history of GPU rendering architectures might be giving us hints to where the ML production architectures are going as well. And so what we saw is that evolution from fixed function pipelines to evolvable programmability within the function pipelines to full programmability. And that led to a massive explosion. And Ray might be one example of these third generation programmable production ML architectures. And it's leading to new applications, simplifying existing architectures, parallelizing high performance ML systems, making ML accessible to non-specialists and highly scalable algorithms for reinforcement learning. So if you'd like to learn more, you can look up the Ray framework. If you'd like to hear from companies like Uber and McKinsey that we talked about earlier, there is a Ray Summit coming up, June 22 to 24. And please don't hesitate to send me email if you have questions, and like many companies, we are hiring. And with that, I think we have a few minutes left for Q&A.
Nice. Awesome. So I've coagulated or congregated all of the questions that I found. First one up, how is OpenGL related to MLOps?
Ooh, how is OpenGL related to MLOps? I think OpenGL would correspond to something like cluster maintenance. And so maintaining that cluster, having ML people maintain that cluster capability and make those distributed machines. It's not easy to maintain a Kubernetes cluster with 1,000 GPUs in it, right? Like that's not an easy thing to do. And OpenGL made that easy, and I really appreciate MLOps making that easy for people working on machine learning.
Sweet. I like it. Right to the point. I like these answers, Waleed. So how does this compare with Dask or something like Metaflow, who coincidentally we're going to hear from right now in just a minute. So if you are interested in Metaflow, stick around. But
Yeah.
How does this compare?
Yeah, so you can, so Dask can be thought of in a number of different ways. But one thing you can do, for example, and is being worked on and showing very promising performance results, is Dask on top of Ray. So you take the Dask system and replace the distributed computing layer of it, and then you can use Ray and still have the advantages of auto scaling, cluster management, all that kind of stuff being done for you. So it serves the same purpose in the sense of making distributed computing easy and accessible. It does it in different ways, and there's different choices there about the level of flexibility that you want to make available to users.
Have you tried Ray in a federated learning context?
Ooh, that's a really interesting one. We don't have much of a presence on mobile devices. Python in general doesn't have much of a presence on mobile devices, though Ray does support Java and C++ in addition, but most of our use is on Python. I guess in federated learning, we're talking about parts of it happening at the edge. It's definitely something that we've had some internal conversations about how you would structure that, but we haven't built anything out seriously or anything like that. But that's a really interesting application, and I think it would be, as I think about, there are some primitive, like I'm already designing this in my head. I know how we do it, but it's not something that we've thought about architecturally how you would support in that federated learning model. But wow, what a great question.
Maybe it's a little spark of inspiration for you.
Thank you.
So,
reach out to me if you want to follow up. Yes,
there we go. I like when connections happen like that. So next one, and then I feel like we got to cut it short. And for everyone asking questions in Slack, I think Waleed's going to go over there after we cut him off on here, and he can continue answering all the questions. So last one that is pretty interesting for me too. I'm going to +1 this one. How does Ray handle observability?
Whoa, okay, that's a good one. Every time an actor, obviously this is something that we're trying to improve. There is a dashboard. You can actually, so we have a basic dashboard in the tool, but we're also continually adding features, and the community is helping us to continually add features to make understanding what's actually happening in the Ray cluster easier. So obviously things like tracing as well as observability, and understanding things like how much is this particular Ray piece using memory are things that are continually being improved. There's some existence there, but there's always room for more and to make things better. And there's also a Ray debugger. So that gives you some capabilities to actually dive in and explore what's going on. Cool.
Thank
All
you
right,
for
thank
that,
you, everyone. I
Waleed.
had a blast talking to you today. I'll see you folks on Slack, and thank you, Demetrius, for introducing me.
Yeah, awesome conversation, awesome presentation. I appreciate it. And yeah, everyone else that is out there and has more questions for Waleed, feel free to ask it in Slack. It is going down over there. So jump in it. Take care, Waleed. Appreciate that. Next up,
See you folks later.
we've got, if you heard me earlier, we've got a few fellas from Netflix. They're coming to talk to us. And I'm just going to tell a little story. What's happening, Ravi and Jan? I see you guys are here. Nice. I want to tell a little story to everyone about how I ruined Ravi's presentation when he came onto the MLOps community meetup. I managed to jump the gun and I said, oh, you know what I love about Metaflow is that diagram you guys did. And I shared the screen on the diagram, the best diagram ever, before Ravi did his presentation. And then he's like, yeah, thanks. That was my presentation. There you go. So I'm not going to do that today. I'm going to hopefully keep it really clean. And we're just going to cruise into it. No screen sharing from my part, but it is a great it is a great diagram. So hopefully you guys have that in this talk also, because it's one of those ones that's timeless and it will stand the test of time. Now, for those who don't know who the speakers are that are coming up next, we've got Jan and Ravi from Netflix. Jan is a senior data scientist and Ravi is a software engineer working on the Metaflow project. They're going to share with us how the magic of Metaflow, the ML framework at Netflix, gives the data scientists more autonomy, creativity, and productivity in their work. So without further ado, I'll let you two take it away. Great seeing you both. Here we go.
Thank you very much, Demetrius. So thanks everybody for joining us today. My name is Jan Florianchik. I'm joined by Ravi Kiran. We're going to talk about Metaflow. It's a piece of software that he and his team build to help supercharge data scientists like me at Netflix. So I work on a team at Netflix called Content Demand Modeling. And content demand modeling, we're focused on two really broad areas. And the first of those is trying to answer the question, which titles are similar to which other titles and in what way? You can think of the sort of classic Hollywood comparison between two titles, like the existential angst of The Eternal Sunshine of the Spotless Mind meets the surrealist flourishes of The One I Love, these kind of title comparisons. If you're interested in this area for what we work on, there's a great blog post that was written by some of the scientists that do so. The link is at the bottom there. It's very thorough and you can learn all about it. I put a graph up because it's sort of a graph embedding type problem. The second question we tend to work on is how large is the potential audience of a show in a given region? And this happens to be the area that I work on. You can think of this as a supervised regression problem. And I'm focused on solving this problem after a show launches. And if you've done supervised regression before, like most regression problems, it's better to solve it earlier and it's better to solve it more accurately. Those are usually useful improvements for the problem. So let me tell you a little bit about something that we did earlier in 2020. So earlier in 2020, my team members, Ashish, Natalie, and I, we were wondering about exactly this question. Could we make this model that we own more accurate and even more accurate earlier? So we had some discussions, we tried a few ideas of our own, and we decided there was a good chance of success for this if we made an investment in a brand new model. So initially, we're expecting this to be a project that we could do over the course of like a quarter, and we have tons of time to incrementally work on it. We certainly weren't thinking yet about how to take this project to production. However, when we wrote up our plan, we got this overwhelming interest from stakeholders, and so we decided let's get this done sooner rather than later. And specifically, we decided we wanted to launch it at the same time as this fresh coat of paint was going down on this set of internal tools and apps that use the model. So this gave us a window of about 2 weeks to go from almost 0 to 1 on this project. And in order to get there, we realized we needed to satisfy 3 things with the way that we were going to work. The first of these was that we needed to iterate quickly. This 2-week time frame was very tight, and we had a long backlog of feature ideas to try for our model. The second was that between the three of us, we had varying levels of context. Some of us were more familiar with domain-specific ETL and the table schemas that are sort of populated all over the place. And some of us are closer to machine learning engineering, others are closer to strict ML. And the last and very important to us piece was that we needed a fast path to production. And we needed to push scores into an existing ecosystem of internal apps. And what's more is integration testing against those apps were pretty costly to repeat, and so we didn't want to have to do them multiple times. Now, this was a really big thing to ask, but it is exactly what I asked of Ravi.
Thank you, Jan. I thought it may be best to first open with an alternative visualization of Jan's constraints, perhaps from the vantage point of an engineer. In that spirit, Jan wants to iterate quickly on model development and feature engineering. Jan and his team have multiple ideas they wish to quickly prototype and figure out what might be the best route to pick. In fact, it would be incredible if we can empower all our data scientists with the highest degree of freedom at this layer of the stack, since there are many excellent off-the-shelf libraries like PyTorch, TensorFlow, XGBoost, and we'd love for our data scientists to have their preference depending on the task at hand. He also mentioned having multiple collaborators like Natalie and Ashish with varying levels of context. Some who may prefer to just work on a notebook on just the modeling logic, for example, and just access Jan's data, while some others might want to probably take an entire copy of his workflow and mutate it. Having multiple collaborators and the need for trying out different versions makes versioning a key concern to solve. Machine learning also involves a lot of experimentation, and therefore model operations become a pertinent question. How do you keep the code reliably in production? How do you monitor its performance? And so many other concerns as well. Lastly, he wants a fast path to production to get even a basic version out. Now, this probably sounds quite simple, but I feel like this is actually more nuanced than some of you may think. Just to sort of dive deep a little bit into that workflow, right? Like Jan has to access data from probably a data warehouse. This could either be a database or a multi-petabyte data lake like Amazon S3 in Netflix. He probably would also want to write out some of the data into a common place for his coworkers to access, for example, maybe the model, maybe some training data. Jan might also want to create a simple enough benchmark model just to vet the data, for example. And for this, he would want access to a compute environment to both crunch the data and also produce the model. In this case, we want to sort of see if he can support a spectrum of machines, like all the way from his laptop to probably a really beefy cluster. Lastly, we will also want an integration to a job scheduler to orchestrate multiple units of work and run the workload on a consistent schedule. Beyond these layers of infrastructure, Jan and his team might also have to answer a few software engineering related questions. How do you architect the code to be executed? How do you want to think about dependencies? What about the packaging story and like getting it to run on different environments? Now, the interesting part is these set of questions outlined on this slide are not just specific to Jan's project. What we realized looking at several other data science projects at Netflix is that production grade data science projects typically rely on this thick stack of infrastructure as presented on the slide. And that's kind of what brings us to our next insight. I should say this is the favorite picture of Demetrius. So yeah, I'm hoping it's timeless. But in our experience, given a choice, data scientists would prefer to sort of stay atop the stack as much as possible. They probably don't want to spend too much time thinking about the software architecture or probably having strong opinions about the right choice of infrastructure integrations, but definitely want to spend a lot of their time thinking about feature engineering and model operations, as Jan mentioned a while ago. Conversely enough, in fact, this is where the role of us as machine learning infrastructure can add a lot of value. We could probably take care of all the heavy lifting required to translating the data scientist's intent of a machine learning workflow and getting it to run safely and reliably in production, integrating with all the relevant layers in the stack to do so. We could also afford to be quite strongly opinionated at the lower levels of the stack and probably build a lot of software engineering best practices so that all our data scientists can get them for free. To answer not only Jan's problem at hand, but also several other data scientists at Netflix, we built Metaflow, a human-centric framework for building and managing real-life data science projects at Netflix. It's actually been battle tested for over 3 years now and is used for an array of machine learning use cases, definitely related to catalog performance, content production, and several others. Metaflow beautifully packages all of its offerings into one simple library that is actually now available open source for both Python and R with easy integrations to the AWS cloud, giving you immense amount of freedom at the higher levels of the stack while being somewhat opinionated on the lower layers of this infrastructure stack. Next, I thought I'll just sort of switch gears and maybe walk you through kind of the storyboard of how this partnership between Jan and us came about. So first of all, Jan had this idea and just wanted to sort of start with the basic questions like how does he go about thinking, structuring his workflow? To that end, the first thing I want to introduce to all of you is the concept of a DAG, or a directed acyclic graph. It's probably the first thing most people would like to understand about Metaflow. Here, Jan might want to break his machine learning pipeline into a workflow of steps. For example, he may want to deal with data preparation at first, probably moving on to feature computation after that, while finally rounding it up with training multiple models and seeing which one might do really well. We try to keep the Metaflow syntax as Pythonic as possible so that our users don't have to pick up a new DSL or domain-specific language and can just quickly onboard. Each step is annotated with an @step decorator. And as you can see on this slide, the step also specifies the transition to the next step. And we support static branching as demonstrated on the slide, so you can have some degree of parallelism. Core to any data science problem is data. Now, we probably don't want Jan to think too much about how to sort of save different parts of the data, whether to save something, whether it's too expensive, and also just have all he may want for debugging. So let's see what we have in store for that. Metaflow actually makes the concept of storing things, I think, as easy as possible. For that, we have this concept of artifacts. And this is as easy as writing to an instance variable in a Python class. So for example, on this slide, self.x represents, you can imagine something like maybe a machine learning model that you can write to and then get access to it later on. Now, I should say everything is versioned and stored in our data store at the end of task completion. To keep our storage footprint low, we efficiently compress the data and store it in a content address fashion to avoid storing duplicate copies across multiple tasks. Another thing that I kind of want to call out here is Jan may also probably want to make his training data available to all his colleagues so that they can iterate over their modeling logic. And that's also another candidate for something that you can store in a model, in a Metaflow artifact, for example. Great. I think we figured out the story with the data, and probably I feel confident about getting access to AWS S3, both read and write. Now, I'm sure Jan's getting excited and he kind of wants to get his hands dirty on some basic machine learning model or maybe something fancy, I don't know. So let's see if we can equip him with the right compute possible for all his needs. The first kind of compute story I want to introduce to all of you, and I think this is maybe perhaps underappreciated, is that concept of vertical scaling. And Metaflow being cloud first can easily achieve vertical scalability by simply leveraging @resources and @batch, for example, decorators in tandem. And also vertical scalability is mostly trying to sort of see if we can equip all our data scientists with just bigger laptops on demand in the cloud. This will kind of make not having to think about the perils of distributed computing as much as we probably need to in sort of other forms. And here, Jan might want to train his model, maybe using a GPU, depending on some video processing work that he may have, or might just want larger memory for a data processing step if he's using some data science libraries like Pandas, for example, with heavy RAM requirements. And as denoted on the slide, Metaflow makes it quite easy to get different resources for your different tasks and different steps. And as denoted on the slide, you can have one that's probably CPU intensive or GPU necessary, and then the other, which is just sort of RAM heavy. We also understand that not always a single box might work for all your machine learning workloads. Therefore, we also have a story for achieving some easy kind of horizontal scalability through our for each construct. Here on this slide, we demonstrate how you could just have this concept of sharding your data, maybe into several buckets, and trying to sort of process them in parallel. And for that, you simply have an instance variable denoting what that list of buckets might be. And in this case, it's shards. And then you just tell our for each construct that. And Metaflow takes care of distributing your work onto different containers, each getting their own copy of the data that they're supposed to process, the individual slice. And then the author doesn't have to actually care about this specific detail. This, for example, in Jan's use case, could be very helpful with just dealing with the very large data set and just sort of distributing some work, if I had to guess. Yeah, I think we kind of got a version working, but I think this is probably another kind of, in my experience, something very specific to machine learning, and the fact that a lot of its major development happens in Python. There's a lot of packaging, dependency, various things that you have to think about. First off, I want to open with dependency management. And this is the one that I think I really feel is actually sort of spoken less about, and I feel needs more attention than people may think. At least at Netflix, we felt this to be a key concern to solve. And therefore, I want to highlight the need for dependency management. There are many excellent off-the-shelf libraries in Python. And you probably have your TensorFlow, Scikit, maybe some esoteric library as well. But data scientists would not want to worry about, if their pipeline sort of suddenly breaking in production just because some version moved somewhere or some TensorFlow latest version is incompatible with a different thing. So overall, for this problem, what we've done is we've sort of integrated with an open source offering of Conda, and we make it as easy as just specifying a bunch of libraries and their versions. And we take care of providing isolated, reproducible environments in sort of wherever the compute ecosystem your code might be running. This makes it sort of possible that the machine learning pipeline just doesn't surprisingly fail, even though there's no change made by a data scientist. And one last thing I want to kind of call out is that this is probably substantial enough for like a talk of its own. And we have several other talks on Metaflow that stress the dependency management problem. So I encourage all of you to check them out as well. The last step in our journey is to production is that of a scheduler integration. Once we have a workflow looking promising at scale, we want our data scientists effectively to make zero code changes as much as possible and be able to still get it to run on a consistent schedule on some partner scheduler integration like AWS Step Functions or something. We have a different one internally at Netflix. What we've done is we've provided a reference implementation by integrating with AWS Step Functions in open source. And we've written more about our experience and how we think about the sort of abstractions between scheduling, compute, and just the overall architecture of your workflow to much better detail on this blog post. So I encourage all of you all to go check this out if you're interested. Jan has a lot of questions, but I mean, I don't know if this is his last one, but it seems like he's quite happy with getting it to run in production, but he seems to definitely go back to thinking about his colleagues as well, which is really great. So let's see what all we can do to kind of help him and his teammates. Metaflow supports a first level concept in versioning, and every task execution for every run, every flow, every user is all stored in our metadata database. And we make it quite easy to get access to this information with a simple enough Python client. And this is quite useful for collaboration. We've also, like in this particular case, Jan might just want to look back at his run and maybe look at some of the model artifacts and see how they performed. And what's nice here is that you can also just very quickly compare to Natalie's run in case she made a copy of his workflow and had a different idea. And then just sort of compare and contrast. And I think this is really cool. Now, while we won't get into more details, the concept of tags also makes it quite easy for all our users to annotate their runs with some human readable information so that they can quickly retrieve them later. Using the same Python client, you can also sort of inspect the data of each task in a notebook if you want for monitoring purposes or as a business facing dashboard. And also the topic of model operations is becoming a key pertinent question generally in the data science community. And internally, we've been thinking about the interplay between Metaflow for compute and notebooks for dashboarding and auditing purposes, because notebooks are also quite heavily used within Netflix. So we've tried to sort of come up with quite a nice story within Netflix, and we're more than happy to hopefully kind of bring this open source as well. But just quickly, like something like this could be useful for Jan and his team just to simply impose some safety checks after training a model consistently on a schedule, and just having some possible ability to have a manual audit so as to ensure safety, for example. So, I mean, I spoke about a lot of features, and they're all happy cases, but I think it's equally important to sort of emphasize that the fact that failures happen. We do want our workflow sort of safely and running reliably in production, but we also think there's this cyclical nature between prototyping and production when it comes to data science. And we'd want to not think of production as a terminal goal. Since everything is versioned, stored in S3, tagged by a single metadata service, Metaflow makes it quite easy to switch between local scheduling on your laptop and the production environment using something like Resume. Suppose something failed in production, we try to make it quite easy for you to be able to reproduce that locally on your laptop, quickly ship out a fix, and just push out a new version to production, and there you go. So I've been speaking about a lot of features of Metaflow, and I understand that, but I thought it's best to sort of let Jan kind of circle all of this up and just talk to you all about what actually ended up being the story for his problem at hand, and maybe just sort of quickly summarize the problem itself. So with that, the floor is yours, Jan.
Thank you, Ravi. So as we take you back to those 2 weeks in 2020, let me also tell you how it is that our team uses Metaflow today. One way that we use Metaflow is we do some live scoring through API. Some of these models need user inputs, and so we expose them through APIs for the apps that require them. Another way that we use Metaflow is we do a lot of batch scoring. We run about 60 to 70 production jobs just on our own team, and that produces a lot of records for our data warehouse. And the last one, and the one that we're going to focus on now, is collaborative prototyping. One aspect of our team is that the project to owner mapping is many to many, which means that we need to collaborate pretty frequently. It's a necessity for the way that we operate. So let's talk about this collaborative prototyping idea. I wanted to do something in that 2-week sprint. I wanted to try a new technique, which I was going to call, or I did call, the skeleton flow. Here's what the skeleton flow did. It was a simple flow that I could share with my team. It did feature preparation and large in-memory joins for me, and it was running on cloud infrastructure. So already in the skeleton flow, I'm using horizontal scalability because I'm farming out things across a large fan out in the DAG. And I'm using vertical scalability because I can go and use more resources up in the cloud. So then let's talk about how Ashish and Natalie actually interacted with the skeleton flow. what the skeleton flow was doing is what we realized was our problem was highly data parallel. And so we could divide it up into a bunch of subtasks. And what I pointed Ashish and Natalie to was the result of one of those tasks and said, inside this task, we're going to agree on what our training and test data is. And you can just pull that training and test data by addressing the flow. So they're using the client API feature there, and we're using the storage feature as well. This was a really great way for them to get access to lots of great pre-processed data. And it aligned our team so that throughout that experimentation phase, we were using the exact same set all the time. Then what would happen is over those 2 weeks, I would go and I would clean up the data, or I would add new features, or include more training samples. And whenever I would do that, I could simply go back to Ashish and Natalie and say, hey, at the top of your notebooks, point your notebooks to a different run and just continue working. And we were able to keep in sync that way. So eventually the skeleton flow did grow to be our real modeling flow. So we put it on a scheduler. We locked all the dependencies, and obviously things fail, things break. So we do use the resuming flows feature. So that sort of accounts for all 8 of the features you've seen today. We actually use in those 2 weeks and in production. That's a summary of what we wanted and a summary of what we got. And we're very happy with it. But as consumers of Metaflow, what would we tell you? What are the sort of big takeaways that CDM would tell you about Metaflow? Well, first is we got accuracy wins. And as a data scientist, you can't be happier than that. In that 2-week sprint, we were able to increase our model's accuracy by about 25%. I know that number means nothing without units, but it was important to us. We were able to get an improvement. It also felt very pick up and go. There's no new DSL to learn, which means that our production code looks a lot like our experiments. Now, I'm not saying we do copy pasta. Well, obviously, we think very carefully about the code we put in, but we didn't have to relearn anything or rethink anything when we were going to production. And what's great, too, is when we onboard new team members, we can just show them Metaflow and say, hey, this looks a lot like what you're used to anyway. And the last piece is we have low ops overhead. Versioning is great. Dependency management is really important, and that gives us a ton of reliability as we run these things daily in production at really large scales. So if you like what you heard, go pip install Metaflow, reach out to us. We're a very happy developer, very happy customer. Thank you all for listening to us today.
Awesome. Very cool. So, Jan, I'm going to ask you this one, because Ravi wouldn't answer it last time he was on the MLOps meetup. When is the next season of Stranger Things coming out? I know you can't answer.
Really, even if I knew, I can't.
All right. Fair play. Looks like there's a lot of chatter happening in Slack right now. People are pretty stoked on Metaflow. So again, if you would like to talk to these folks, get in Slack, ask the questions. I know there's some questions coming through in the chat that we have right here, but we're asking everyone to go to Slack and ask those questions, because then Ravi and Jan can be there and answer questions. I also saw that Savin is in the chat too. He's another guy that's working on this project, on the Metaflow project. So super cool to have you all in Slack and answering those questions. The Slack, we'll drop a link for people who are just joining us right now. We'll drop a link to how you can sign up and get over there. And yeah, that's it. Jan, Ravi, that was excellent. Thank you both. So now we have got another break. And during this break, I'm going to do a guided meditation. It's getting a little late over here in Europe. So in case anyone was trying to sleep, you can just put this on low and let the sounds of nature take you away, light some incense, put on some essential oils. But before we jump into the meditation, I realized that I have a few announcements, and I will say them real fast, and we'll do like a 3-minute meditation, and we will start the next session. So if you need to go to the bathroom right now, get after it. If you don't like meditation, you feel like it's for weird hippies like myself, then now's your time to go grab some snacks or whatever. The announcements that I wanted to mention were, again, please go into Slack, ask your questions, and ask them in the Apply channel, Apply-conference channel. That is where lots of good stuff is happening. There are all kinds of questions that are jumping in there. Savin, Ravi, and Jan are all in there. So the last session you can ask them about. And then the other thing is we've got a selfie contest. Applied Selfie is happening in Funny channel, #funny. Get after it. Send us your selfie and you can win some swag. There have been some excellent selfies coming through so far. So I love what I'm seeing. Also, I'm seeing some good like comic jokes, which is a nice little side effect. So if you have funny jokes or cool comics, throw those in there too. It's always good to get a laugh. So #funny channel, throw your selfies in, throw the jokes, whatever jokes you have. All right. And the last thing is I want to let everyone know that it looks like for this conference, we had over 7,000 registered participants. That is incredible. That shows that there is some real need and desire to learn more about ML ops and productionizing machine learning. I love seeing that. 7,000. Wow. That's a lot of people. So, and especially these days when we're all probably a little burnt out from the online conferences and we're ready to get back into real life conferences, but it's still cool to see. So thank you all for registering, participating. Really cool. And I know I said the last one ago, but now this is for real, the last thing. The last thing that I will say is we have 2 forms that we're asking people to fill out. One is a poll, and you can tell us what you think about if a data scientist should learn Kubernetes, or if MLOps is an organizational problem, or if it's a tooling problem. So the links to the forms are in Slack. Go and check those out. We've also got a really cool question around if you've ever had a model go rogue. We want to hear your war stories, and we're going to be giving out some swag for the best war story also. So it's completely anonymous. We're not going to tell. You can like make sure that we don't know what company it is you're talking about unless you want to. And that's that. The poll is there. And then we also have the best speech or the best talk poll or voting. So we're going to give some of the speakers some swag too. We don't want to let them feel left out. So that is the 2 polls that we're asking you to get involved in. And without further ado, now is the time to light some incense, grab your tea or whatever it is that you enjoy drinking. And we're going to do a quick, like, I'll call it 3-minute meditation, just so we can close our eyes, get our little rest into our eyes and, you know, not have to look at the screen all the time. So let's do it. Let's get into it. And if you don't want to do it and you're slacking all of us about how funny we look with our eyes closed, good thing I'm the only one that is on screen. So nobody else can see you if you are closing your eyes and looking away from the computer. So no judgment. You don't have to take a selfie while you're doing the meditation. That is not part of it. Now, let's go ahead. Let's get started and let's start just breathing and noticing how we're breathing. If you'd like to close your eyes, you can. If you feel like you're in a comfortable position, I would just ask that you bring your spine up nice and tall. Gently close your eyes if you'd like. Start to notice your breath. See if you're leaning back. I encourage you to get that spine so it's not leaning against anything. You're propping yourself up. As you begin to let the breath deepen, starting to notice random thoughts that are flying through your head. Starting to notice the chatter that's going on in your mind. You can let your exhale just become a little bit longer. With each new exhale, you're trying to make it a little bit longer than the last one. As we're lengthening our breath. Seeing if we can find a place of calm, serenity. Now that we're in this state, I'm going to go ahead and ask you to direct your attention towards the center of your chest. Feeling your rib cage as it expands and contracts with the breath. Feeling your lungs fill up with air. Maybe you can even feel your heart beating. We'll take this moment to consciously choose something that we're grateful for today. It can be anything under the sun. Whatever you feel like you can cultivate a bit of gratitude towards. Let's go ahead and think of that thing. Could be that you're here at this conference. Could be that you don't have to work because you're watching the conference. Might just be that it's snowing where you are, or it's sunny where you are. Whatever it is, go ahead and bring that to mind and start to feel grateful. Feel that gratitude in the center of your chest and allow it to manifest itself there. With each new breath, you're letting that gratitude grow. Let that feeling, immerse yourself in that feeling. All right. We say thanks for whatever it is that we're grateful for today. And when you're ready, you can gently begin to move around again. Open your eyes. Come back to the room that you're in. want to say thank you to everyone here that participated in this meditation with me. And thank you to everyone on Slack who was talking a bunch of crap, trying to get me out of my groove. But I'm too centered now. I'm too focused. I really appreciate everyone here. Hopefully that was a nice little break from looking at the screen. And we're gonna get moving. We're gonna get going in about 8 minutes with some lightning talks. These lightning talks are just gonna be 10 minutes each. And they're gonna be packed with a bunch of stuff. Let me see if I can get back up to speed. I'm all coming out of this meditation. I see someone asking if we're posting a video of the meditation. Maybe we may have to, just so you can share with people and say, look at how ridiculous this conference was that I went to. We had guided meditations. All right, cool. I'm seeing some people liked it. Wow, this is a surprise. Okay, nice. Well, thank you all for being part of that. That was a bit of an experiment. I'm glad that some of you liked it. I saw that the attendees that we had just dropped by 100 people. So either they went to YouTube or they went to the bathroom or they left. I'm seeing in Slack mustache meditation. Amazing. Thank you all for joining. And yeah, let's keep that feeling of gratitude rolling. Remember, anytime throughout the day, you can go ahead and just bring yourself back to that feeling. It's so easy to get involved in that. It's so easy just to like reconnect with that in any moment. So take a deep breath, reconnect with that. And in 5 minutes, we're going to be jumping on the lightning talk. So we will take a little pause here and we're going to see you back in 5 minutes. I will talk to you all in 5 minutes. Let's get that. We'll be talking with Bar Moses. Ooh, little data observability. Nice. So thanks again, everybody. See you soon. back. What's good, everyone? So, we've got some lightning talks. Let's hear it for Bar Moses. This is our first lightning talk of the day. We're going to kick it off. And if you didn't catch it, these are 10-minute talks. They're going to be jam-packed. We're going to have a few of them. So should be quick, and we're going to rotate them in and out and in and out. It's going to be pretty nice. Lots of information in the next hour, 2 hours. So let's get ready. Let's do it. Bar Moses, if you don't know who she is, she's the CEO of Monte Carlo Data. What's happening, Bar? Great to have you here.
Hey, great to be here.
Nice. So Monte Carlo and data observability, you're kind of known for that. I think that's what you're going to talk to us about, right?
Yeah, that's exactly right. It's either that or meditation. I'm not sure.
Were you part of the meditation? Did you see that?
Yeah, I did, and I loved it. I'm so in the meditation groove now. We might just do 10 minutes of meditation.
You're in the zone. You're going to deliver an incredible speech, an incredible 10 minutes. Well, the time is on. 10 minutes on the clock. It's over to you, Bar.
Awesome. Can you see my screen, my slides?
Oh, yeah.
Fantastic. So hi, everyone. It's great to be right after the meditation. I hope everyone is jazzed up for some data observability. My name is Bar. I'm the founder and CEO of Monte Carlo. And in the next 10 minutes, I'll do a very brief walkthrough of what is data observability and why you should care about it. I'll talk a little bit about why I think it's the next frontier of data engineering, why the best data teams are adopting these best practices around data observability, and what it actually looks like in the wild. I'll show you all some examples. So hopefully leave you here with a couple of sort of practical tips that you can take and implement, or just learn a little bit more about what data observability is. So just a little bit about myself. As I mentioned, Monte Carlo is a data reliability company. So we actually help companies trust their data by minimize what we call data downtime. Before founding Monte Carlo, I served as VP at a company called Gainsight, the customer data company. My background is in math and stats, and I'm a huge fan of Bruce Willis movies. So I've watched them all multiple times. Happy to take any questions about that. So now that we've gotten the important things out of the way, let's talk about data observability. So actually start by introducing sort of a pain point or a common story that might have happened to you if you had anything to do with data. So, a story about myself, this was several years ago. I was responsible for the data and analytics team, and responsible for some key data that our executives in our company were relying on to make some important decisions, both day-to-day decisions, operational decisions, and also strategic decisions, like where are we going to take our product and which customer segments should we work with. And, it felt like literally every Monday morning, I would start sort of the week, commute into the office back in the day, and actually would be sort of hit with this wave of things that were wrong with the data. And oftentimes we weren't the first to find out about it. We learned about it from people who were using the data, people who were relying on our data, people who were using our products to relying on the data. And there were just so many of those. And we just felt like we entered fire drill mode for the entire week. And we were always sort of proactive, sort of reactive around these issues. And, in talking with other data teams and other folks in the data space, it just felt like this was such a common issue. Regardless of sort of what role you're in, and what kind of data you're working with, it feels like, data that's inaccurate or wrong or late, or sort of, someone makes a change somewhere that has an impact downstream that then you're surprised by. All of these sort of changes happen so often, and we're often the last people to actually find out about it. And so the question is, what is a solution to that, right? I have to believe there is a solution to that. There's no way that we're living in this world and we're all sort of running around trying to solve sort of the latest data problem. And this is where, the concept of data observability comes in. And actually, I think the solution to this problem starts with looking at our counterparts in software engineering. The good news is that software engineering has actually solved similar problems, and we can use some corollaries and lessons learned from software engineering to apply to data. So let me explain a little bit more about what I mean. So if you're familiar, sort of the concept with observability more broadly, this is, some principles from DevOps for the last couple of decades that have been, developed and help actually make sure that some of our favorite things don't break, like Netflix or Slack. And if they do, they're fixed very, very quickly. And the teams that are responsible for observability in applications and infrastructure are folks who are responsible for building and maintaining and actually fixing things that break down at nearly every company, right? Even if we're not aware of them. And so, I think that solving the problem of sort of bad data can be tackled by relying on some of these best practices. So I'll give you a corollary for this. A couple of decades ago, if your company website, like if you had an e-commerce company or if you were sort of running the Slack of the times and your website was down, no one noticed. But in today's world, if something like that happens, totally unacceptable, and we have all these best practices to make sure that that doesn't happen. How do we create the same thing for data, right? And so if you think about DevOps and observability, there's sort of three pillars, commonly referred to as metrics, traces, and logs. Now, if we wanted to take this concept and apply that to data, what would that actually look like? So we actually defined the concept of observability in data as an organization's ability to fully understand the health of the data in their system, thereby actually eliminating or reducing data downtime. So observability allows us to understand the health of a system by observing the output of that system. And so if we wanted to determine the health of our pipelines, meaning the data that's running in our pipelines, how can we apply the same concept to detect whether the data that we're relying on is actually accurate? And so to do that, we actually define the 5 pillars of data observability. And we believe that, and what we're seeing in the market is that companies and data teams that are actually very diligent about how to think about data observability are able to get a strong view of the health of their data. Now, I'm not talking particularly about the health of the pipelines itself. I'm talking about the health of the data that's running the pipelines, the data that we're actually relying on. We sort of call this the good pipelines, bad data problem. Oftentimes we'll have sort of a job that's completed, everything looks fine, but actually the data is, all wrong or has been late or has all null values. Suddenly we're surprised by that. How do you actually detect those issues and be the first to know them? How do you make sure that you are ahead of the game in the sense that when you identify that there's a problem, you can also trace the root cause and identify what led to that problem? How can you quickly answer questions like who's impacted by these problems? Who's impacted by this data that's stale or inaccurate? So specifically, some of these the data observability pillars are freshness, which helps us determine whether the data is up to date or not. Distribution, what helps us understand at the field level, are the values of the data that I'm expecting accurate? A volume, meaning is the amount of data is the amount of data that I'm expecting, in line with historical rates. For example, if I'm used to getting, 1 million rows and suddenly I'm getting 5 million or 6 million rows, is something wrong. The fourth is schema, which helps us understand the structure of the data. If there's a field that's added or removed or changed in type, and is often a culprit of data problems. And lineage, which helps us tie all of this together and answer questions around tracing and root cause and provides context to a problem. So say if a table was typically updating every 3 hours and suddenly stops updating, and there's a number of machine learning models that rely on that table probably is very important. And you want to make sure that you're aware of how often it's updated and that it's updated on time. What if there was a table that had no dependencies? Maybe you don't care about that one. In that case, you wouldn't even need to know about that incident. And so thinking about these 5 pillars of observability helps us understand the health of our system and be the first to know about data problems, be able to troubleshoot them with rich context about them, and be able to resolve those faster. So what does this actually look in practice? I'll just share a couple of examples of how folks have actually used data observability to see real value for their teams. The first example is Yotpo. So Yotpo has a very strong data engineering and BI team. And they, Yotpo is a company that works with e-commerce companies to help them drive revenue with things like site reviews, just as an example. And they obviously sort of rely on data both to make decisions internally, but also to power their products. And so as they started implementing data observability, what you can see here is an example of an anomalous data volume detected, where you can see the volume sort of pretty steadily over time, and then suddenly a very high spike in volume, which helped them identify when there was a real problem. The other thing that was very helpful in this case was actually understanding the relationship between schema changes that were happening in one team impacting tables and data assets downstream. And by improving the communication around those schema changes, many data disasters were avoided. I'll walk through another example here. So Blinkist is a company that got very serious around data observability, actually as a result of some of the COVID-19 issues. So as you note, you may be familiar with Blinkist, is an ebook subscription service, has over 16 million users worldwide, and as part of their growth strategy, actually use paid performance marketing to fuel their customer acquisition. And with COVID-19, actually, their 2020 strategy completely changed because historical data could no longer be relied on, and they needed to actually use real-time data to optimize some of their campaigns, and use channels like Facebook and Google, which would basically auto-optimize based on behavioral data. And so, with historical data no longer relevant, they needed to actually implement data observability to help make sure that the quality of their data is accurate in real time. And so actually saw faster data incident resolutions and many hours of engineering time saved. And looks like I'm up with my time here. So with that in mind, I'll just wrap up. Thinking about data observability starts with kind of setting these baseline expectations about your data. What does actually good data look like? Thinking about sort of the 5 pillars of data observability and how they apply to your business, and how the overall view provides a context along with rich metadata about your most critical data assets. And thank you so much. It was a pleasure seeing you all, and feel free to reach out if any other questions.
That was lightning fast. All right. We've got Stefan coming up next. Stefan, what's happening, man? I see you in there. I know we don't have a lot of time, so I'm just going to let you get into it. But for people that want to know who and why you should be listening to Stefan, he's the manager and lead ML platform engineer at Stitch Fix. We all know Stitch Fix is doing some crazy advanced stuff in ML, and I'm going to just let him get going right now.
Cool. Thanks. I'm excited today to talk to you about a micro framework we built at Stitch Fix for creating data frames. So 2 things to keep in mind for the next 8 minutes that I'll hopefully kind of convince you of. The first is what I'm talking about. Hamilton is a new paradigm for creating data frames from a user perspective. The second is Hamilton enables data scientists to focus on functions rather than glue code. So to start, I'm going to talk about backstory of why we created Hamilton, then talk about Hamilton itself, our experience using it, and then future directions. So backstory, there's a forecasting, estimation, and demand team, or FED for short. They're a team of data scientists at Stitch Fix who help create forecasts for the business that then the business uses to make operational decisions. So for instance, what should our staffing levels be at the warehouse? It's also one of the oldest teams at Stitch Fix, so their code base has been around a while. Their basic workflow is the following. They take business actuals, so signups, marketing spend. They create a featureized data frame from it. They fit a bunch of time series models on that, which predict the future, which then output a forecast that the business uses to make decisions. What was happening was this pipeline was on fire for them. And given the operational nature of their role in that they need to help the business make decisions, when this was happening, they were understandably quite stressed. What ended up happening was the biggest problem that they were encountering was in creating and managing this featureized data frame. And so this is the focus of the talk and where Hamilton solves their problem. Specifically, what's wrong? What was troublesome about this data frame? Well, this data frame is essentially thousands of columns wide, but maybe on the order of like 1,000 rows kind of deep. The point here is it's not big data, so it all fits on a single machine, or Amazon has big enough machines for it. The second is why there's so many columns. Well, in their featureization process, they're given some initial data column. They're creating new columns from inputs of other columns. So one column can be an input to another column, which can be an input to another column, etc. And so they were having trouble managing this type of dependency chain. Why was that the case? Well, here I have some code. For those of you who know pandas, this should look pretty normal, like nothing egregious. You're probably like, this looks like normal pandas code. And I want to tell you, if you scale this to 1,000 columns in a growing team, you're going to run into issues. Specifically, like if you scale this code, like what happens is you have a lot of different like heterogeneity in terms of how people define functions. So they're trying to create add things to a data frame. So do you pass in the entire data frame to the function or just the columns? Do you modify it in the function or outside of it? And then this being data frames, people are doing a lot of inline data frame manipulations. But the overarching kind of problem with this is like you need to really understand how the code is ordered to really understand what depends on what. What this ends up resulting in the code base is that unit testing is very difficult, especially with inline data frame manipulations, or at least it's very inconsistent. Similarly with documentation. As the code base grew, onboarding and debugging kind of grew, became more costly just because it's really hard to understand what depends on what in what ordering was this executed, etc. In terms of the backstory summary, so the two things to take away is the code for featureization was causing them headaches, and the other is that data all fits in memory. So what is Hamilton? Hamilton mechanically is data scientists write code that gets translated into a DAG, which then gets translated into a data frame. Specifically, the data scientists write code that does not manipulate any data frame whatsoever, which then Hamilton takes over, which is code owned by platform. And then the data scientists then tell the library like, hey, I want a data frame, and then they get one. As I mentioned, I think Hamilton's a new paradigm for them in terms of creating a data frame, and that's because they write functions. They don't manipulate a data frame directly. Here I have an example that we kind of translate to. So I'm trying to create, say, column C from summing column A and column B. With Hamilton, what we would do is that we'd write a function where the function name corresponds to the output column we want to create. And the input parameters end up being the input columns that are required for that function. From that, we can go then build a DAG. Along the way, we can use Python type hints to statically check this DAG before executing any code. And then documentation is natural just because we can reuse the function doc. You might be wondering, okay, so how do we go from this function to a DAG? Well, pretty easy. Python has a great module called the inspect module, which allows you to kind of introspect code. So we make heavy use of that. And then it's just building nodes and edges and graph theory 101 to create a DAG, and then traverse it to create a data frame. You might be wondering, why is it called Hamilton? Well, as one of the hardest problems in computer science, naming things is hard. When we were coming up with this project, we were thinking about what associations do we have with the Fed. I had recently gone to see Hamilton, the musical, and I was thinking, well, Alexander Hamilton is the father of the Fed, or the Federal Reserve. And the Fed team, in a sense, kind of models the business mechanics. So, an analogy to, say, quantum mechanics, and there are Hamiltonian concepts there. And then we're also doing some basic graph theory, so which also has Hamiltonian things in it, so apropos Hamilton. Okay, so what does this actual code look like? You might be wondering, what are the data scientists actually writing? So here I've actually translated the data frame code that I showed previously, but into Hamilton functions. These functions would live in some sort of module, say myfunctions.py. And the main takeaway here is that the function names correspond to output columns in the data frame, and the input parameters to these functions just correspond to input column dependencies. So to go from that, you're then like, okay, so how do they create the DAG? All right, you need to write then a little script. The data scientist writes a little script to orchestrate things. So specifically, they need to initialize some data or configuration. So they need to handle that themselves. But then they then need to specify what Python module to crawl to create and kind of get these functions from. They create a driver which kind of merges those two things together to create an execution plan. With Hamilton, the nice thing is that if they only want a subset of columns, they can just specify that. Whereas in the old way, you had to get any columns, you had to run everything. And lastly, then with that, they just kind of call execute and they get a data frame. One of the nice things we added is, they can also visualize what's actually being executed, so they can actually understand what's going on under the hood. So what's the result been? This has been in production for over a year and a half, and I think it's been a pretty resounding success. And that's in large part to getting data scientists to kind of reframe and rethink and write these kind of very specific functions. Specifically, unit testing becomes standard and is applicable to the entire code base. We actually found a bunch of bugs in migration that we wouldn't have found otherwise. Documentation is also super easy and natural because you can use the function doc, and then you can use tools like Sphinx to kind of expose it for wider coverage, for wider readership. Visualization comes naturally because we can build a DAG. It's very easy then to visualize. Onboarding therefore becomes simpler because we can give people visual means to understand the code, but then it's also very clear and concise as to how this column was created. Similarly with debugging, since we can specify dependencies, it's very, along with visualization, it's very easy to if there's an issue, isolate it very quickly, and even be test driven with fixing it. Since Hamilton does result in a slight increase in kind of lines of code, just because if you're taking a single line data frame incantation and turning it into a function, you're going to increase the amount that you write. So we do have syntactic sugar to keep things dry. Specifically, we use Python decorators for that. And then what this ends up resulting is data scientists don't have to worry about glue code. They can just focus on writing functions which enable better featurization, which enable better models. And the glue code, therefore, platform and my team kind of owns that. In terms of, here's a quote from a data scientist on their experience kind of onboarding onto the system. The TLDR is, basically previously their experience with onboarding was, code bases are hard to understand. It's not obvious where things are used and it's very easy to break things. But with Hamilton, essentially there's no prior domain knowledge required to ramp up because dependencies are very clearly specified, functions are simple and concise, and it's therefore hard to break things. So future. So we have a DAG. It runs on a single core, single machine, but there are tools and libraries that could potentially enable us to easily scale this out. So for instance, Ray, as you've seen before earlier, or even on Spark, or even compiling to Metaflow. We're interested in open sourcing this. Do hit me up if you're interested. We currently support Python 3.6 and 3.7, but curious to hear if other people would be interested in using this. We can extend this to general featurization problems, especially if we can make it work in distributed settings. So we're looking at ways to take this more mainstream. But Hamilton isn't limited to creating data frames. It can actually be extended to be anything that can be union or merged together. So that's my lightning talk. I talked at you for a bit. Happy to take questions. Thanks.
That was awesome, dude. That was great. So you spoke so fast. You got in so much information in that 10-minute talk. I think all the questions are happening in Slack. So everybody jump in there, tag Stefan.
Yeah, tag me. Yeah, I'll be around after the conference. So even if you don't think of one now, but you think of one later, yeah, just ping me. Else, I'll be sharing these slides on SlideShare at some point later today as well.
Oh, nice. And I'm really stoked that you're thinking about open sourcing this. I know we talked about that before, so that's cool.
Yep. Open sourcing is just a matter of prioritizing it and getting legal and other things to check off. So it helps if there are other people interested, because then that makes me feel like I'm actually doing something people want.
Nice. Well, thank you, Stefan. That was great and right on time. So you're making my job easy.
No worries. Thanks, everyone.
Cheers, man. Now we're going in to the next lightning talk. This one is with okay, so this one is about common use case for Tekton. It's developing and fielding a fraud model. You'll hear all the key highlights from Tekton's own Matt Bleifer, a product manager focused on core development for Tekton and Feast. All right, Matt, thank you. Take it away.
Hi, everyone. My name is Matt Bleifer, and I'm a product manager at Tekton. Today, I'd like to show you hands-on how a feature store like Tekton can help dramatically speed up machine learning application development time for operational models such as fraud detection. Let's dive in. So what makes developing ML applications like fraud detection so hard? Well, first, when it comes to getting feature data, we need to be able to access historical offline features for our model training. But then when we deploy this model to production and use it for real-time serving, we need to be able to access the latest online features at low latency. Often this means re-engineering online pipelines in production, but this is an error-prone process that often leads to training serving skew. Next, our feature data may be derived from multiple different data sources. It could include batch data from data lakes or warehouses, stream data, or even request data, such as the current transaction amount or the user's current location. Lastly, these applications often have strict SLAs. Our online fraud predictions must return at low latency so that we don't keep our users waiting. Our system uptime must be consistent and reliable. And our fraud features need to be super fresh to adapt to recent events and deliver high quality predictions. These are some of the complex requirements that make developing these ML applications difficult, leading to high failure rates and long lead times, including months of development. This is where a feature store can help. A feature store helps data scientists define, deploy, fetch, serve, share, and monitor features for their ML applications. Using a feature store to develop feature sets can help reduce machine learning development time down from months to just minutes. Today, I'd like to show you a hands-on demonstration with Tekton of how this process works. We'll build and serve a feature set for a real fraud detection model. And to do this, we'll first productionize a new feature pipeline, then combine it with other features from the feature store that we found that perhaps others in our organization developed. Then we'll take our new feature set and fetch training data offline using the Tekton SDK. And then we'll fetch real-time feature vectors online at low latency that we could use to be able to pass to our fraud detection model in production. So let's get started. All right, so let's develop a new feature for our fraud detection model. The first thing I'm going to do is take a look at the Tekton web UI, which is kind of like our portal for being able to browse, discover, and understand different data sources, feature pipelines, and feature sets that have been registered with Tekton. First, we'll take a look at this data sources tab on the left, where I can see that there's a variety of batch and streaming data sources that have been registered and are available for me to be able to build features off of. I'll take a look at this credit scores batch data source in particular and see that it contains users' credit scores over time. Now, I think I can use this data source to be able to build a feature that determines if a user has good credit or not. And so to do that, I'm going to hop over to what we call our Tekton feature repo. Now, the Tekton feature repo is simply a local set of Python configuration files that we use in order to define those data sources, feature pipelines, and feature sets that will serve to our models. In order to develop a new feature, I'll open up a file here and add some code. So this is what a feature definition looks like inside of Tekton. We define it as a view against some registered data source. This view can use various transformation languages, such as SQL or PySpark or Pandas UDFs, and it can range from simple one-stage transformations to a full complex pipeline of transformations. Here we can see we have a simple SQL statement that we're running against that credit scores batch data source as an input. We also specify the entities that this feature is indexed off of, in this case, a user, and that transformation type that we want to run, in this case, Spark SQL. Now with just these three parameters up top and this transformation down in this function below, we actually have all the information needed in order to be able to successfully register this feature with Tekton and make it available for users to browse and even experiment with offline. However, because we want to use this data inside of our real-time production model, we also need to configure materialization. So here we specify that we want this data to be materialized to our online and offline feature store to support training and serving. We also specify how far back we want Tekton to backfill the feature data. And then once that backfill is complete, how often to continue orchestrating the compute jobs to calculate the latest feature values. In this case, we specify a batch schedule of 1 day. And that's it. Now, I can take this feature definition and create a feature set for my model. To do that, we'll create what we call a feature service inside of Tekton. A feature service simply defines the set of features that we want to serve for a particular model. In this case, for our online fraud detection model, we will register a fraud detection feature service, and we'll include here a feature set that has both the new feature that we just developed, as well as some other features that are defined inside of the feature repo that perhaps we found through browsing the web UI. So now that we've defined both our feature service and our feature view, we want to register these features with the remote Tekton cluster. Now, in order to do this, I'll simply open up a terminal, navigated to this folder, and run Tecton apply. What this does is it tells Tecton to compare the local definitions that we have inside of the Tecton feature repo with what's registered on the remote cluster. Tecton will notice that we've developed both a new feature view and a new feature service and ask us if we want to apply this plan. We'll hit yes, and Tecton will get to work behind the scenes, backfilling our new feature data to the online and offline store, and then also productionizing a REST API endpoint that we'll be able to use to query online feature vectors in production that we can then pass to our model. If we hop back over to our web UI, we should be able to see that our new feature has been registered here. It's now not just available for us, but available for anyone in our organization to be able to discover here and leverage inside of their own models. If I click into this feature, I can see all sorts of metadata information about it. I can dig deeper and understand the full data lineage and pipeline that makes up this feature, all the way from my credit scores batch data source to the online and offline feature store where this data is materializing. I can also click into materialization here, where I can get information about the jobs that are computing these features and see that my feature is actively backfilling to that online and offline feature store. Lastly, I can see any of the feature services that this feature is a part of. In this case, we notice that this feature is a part of this new fraud detection feature service that we created and registered just a moment ago. If we click into this feature service, similar to the feature view, we can get a wealth of metadata information. We can see an example curl of how we can query this REST API to get feature vectors. And then we can see that full set of features that we're using to power this particular fraud detection model. And then, just like with our feature view, we can click in and really see and understand the full data lineage of all of the different feature pipelines that are powering this model. We can see this from our batch and streaming data sources here on the left, all the way through the feature store to these endpoints that will power our models for training and serving. So now that we've registered the new feature set and the new feature that we developed, we're ready to get data out of Tecton. So in order to get offline data out of Tecton, we'll use the Tecton SDK inside of a notebook. Here, the first thing that I'll do is load up a list of historical training events that I want to use in order to generate training data. In this case, we're looking at historical transactions from users at some particular point in time that were later labeled as fraudulent or not fraudulent. This is the set of training events that we want to be able to get all of those features that we defined for. Now, in order to get that feature data, we'll simply take this input data frame here, and then we'll also fetch that feature set by grabbing that feature service that we developed by name, and then passing both the input training event data frame and the feature set that we want to this get historical features call here. We'll run the cell, and what Tecton will start doing is enriching this provided data frame with extra columns representing all of the different feature data for every single training event. What Tecton will do is actually time travel on a row-by-row basis, and for each training event, for this user ID, for example, it will grab the correct feature values that were valid as of this point in time. And it will do this for each and every row we have here in order to properly guard against data leakage and build a historically accurate training data set. So there we have it. We can see down below that Tecton has built out our training data frame for us, containing all of the historically accurate feature values for this set of training events that we requested. We can now use this data frame to be able to train an offline model that we can later serve in production. Now, you may be wondering how we were able to build a feature set if some of our feature data wasn't yet done materializing to our offline store. Well, luckily, because Tecton has access to the underlying transformations for each and every feature, we can actually tell Tecton to compute some of these transformations on the fly directly from our raw data sources. This allows data scientists to rapidly iterate on and experiment with new features without having to wait for all of their materialization jobs to finish, greatly increasing their iteration speed. So now our final step is to see how we can get this data online from the REST API at low latency so that we can pass these feature vectors to our production fraud detection model. To do this, we'll hop back over to our CLI, and then we'll simply curl that REST API endpoint. And there you have it. We were able to get back a full feature vector at low latency that we can then pass to our fraud detection model for any given transaction that we want feature data for, and to be able to determine if it's fraudulent or not fraudulent. And that's it. In just a short time frame, we were able to develop a brand new feature for our fraud detection model, publish a feature set that serves feature data both online and offline, fetch training data offline to be able to train our model, and then get those real-time feature vectors from the REST API endpoint that Tekton productionized for us. We hope that with tools like this, data science teams will be able to much more rapidly develop new operational machine learning applications and bring more cool new use cases into production. If, like us, you're excited about the future of feature stores, come and chat with us in the Tekton and Feast Slack channel. Thanks for taking the time.
Awesome. Thank you. That was awesome. So next up in this lightning talk, we've got Taimur Rashid, Chief Business Development Officer at Redis Labs. He's talking about the importance of a feature store in your ML stack and how to leverage Redis to improve the quality of your models and and accelerate your machine learning inference. All right, we're going to pass it over to you. But before I do, I just want to mention that the poll is still open. So if you have not filled out the poll, fill it out. All right, it's all yours, Taimur.
All right, hey, thanks so much. Really appreciate that. First off, really excited to be here and really want to thank the Tekton team for organizing this event. Well, in the 10 minutes that I have here, I just really wanted to talk about Redis as an online feature store. So first off, by way of introductions, my name is Taimur Rashid. I'm the Chief Business Officer here at Redis Labs. And in my role here, I'm basically responsible for emerging businesses and new initiatives. And one of the new initiatives that I'm undertaking here is AI and machine learning. A little bit about Redis. So I don't think Redis needs any introduction, but for the benefit of the audience here, Redis is an in-memory open source database. Customers typically use it for caching, and that's where they typically start their journey as they adopt Redis. But very quickly, they realize the power of Redis and they apply it towards, many other use cases, be it, session management, real-time database needs. In fact, even using Redis for recommendation engines, ad serving capabilities, or even real-time analytics and search, right? What we are seeing more and more, though, is Redis being used for machine learning and artificial intelligence use cases. And so at a really broad level, with Redis and AI, we really see that we can empower ML data models, but at the same time also serve as an AI serving and monitoring platform. So as I mentioned earlier, Redis is being used for a variety of different use cases in the machine learning space. And the focal point of what I want to talk about today is how it's being used as an online feature store. And just to orient the audience on the different categories here, if you start on the left-hand side, really what I've identified here is data orchestration tools effectively. And these are just a list of different tools across open source, some of the MLOps providers, and feature store providers as well, including Tekton. And you'll also see a lot of the cloud platforms from AWS, Microsoft Azure, and GCP, actually adding a lot of support for these, end-to-end machine learning ops capabilities. And all of them can effectively interact with the feature store. And if you look at, we're actually doing some work today with Willem and the Feast team on tightening the integration of Feast and Redis. And my hope is that we can work with a number of these other providers here on the left-hand side to get some native integration capability with Redis. Now, as we go to the right-hand side, you can really see the feature store being broken down into, data storage, data serving, and data monitoring. And as I mentioned before, and you've seen some examples already with some of the presenters here at the conference, Redis is being used as the online feature store, particularly in the case of DoorDash and the great work that they've done, right? And so while you can take the database, there's a variety of different things that, optimizations, if you will, that you can do on top of the feature store itself, such as, serialization, compression, and leveraging, hashes in a very particular way that can give you the high utilization of CPU, but at the same time also really reduce the latency that you have in serving those features as well. Now, what's really interesting is, while anyone can kind of take the online, the Redis database and run it as an online feature store, and they may leverage, some of the providers on the left-hand side. They may choose to do some custom engineering to support their environment. One of the things that we've actually done is to bring inferencing closer to the data. And so we have a Redis AI module, which is effectively a module designed for deep learning and machine learning. And what it effectively does, it really takes Redis and it creates a native data type. So we have tensors, models, and scripts. And when you combine that with a back-end runtime environment, such as TensorFlow, TensorFlow Lite, Onyx, or even Torch, effectively what you do is you make Redis an inferencing engine, right? And so when you look at the combined sort of value that developers and organizations can get, if they have data already residing in Redis today in a key value format for feature data, you can actually leverage Redis AI to actually bring inferencing capabilities much closer there, right? And so effectively you can maximize the computation throughput while adhering to that principle of data locality, right? And as we've talked to a number of developers and customers about being able to leverage this capability, what they've actually seen is they've further extended Redis to be able to be a model store, where you can actually store the model binaries, at the same time have metadata around the models as well too. But then as you tie monitoring capabilities, whether it's kind of open source monitoring capabilities or leveraging some of the providers that are in the ecosystem, you can really look at concept drift and data drift, right? And this is where Redis can actually be the store for evaluation data, right? And so if you think about performance metrics, being able to look at, model usage and those typical things that, as a data scientist you want to look at, such as drift, adding those capabilities can really enhance the overall offering, right? And so, we feel we're very early in this journey with understanding how we can really bring value to ML teams that are building, platforms for themselves. And we see this obviously across the three areas: the online feature store, the model store, the evaluation store, and then various actions that get taken place on top of these stores, from real-time calculations on the feature store itself, serving capability on the model store, and then finally drift on the observability platform with the evaluation store, right? And so if you look at it, we've talked to a number of customers for why they're leveraging Redis as that online store. And it comes down to three things ultimately, right? They need a feature store that's live, that's fresh, and that's fast, right? And those capabilities are largely there. And while much of this is available in the open source, Redis Labs, we're custodians of the open source database. At the same time, we also have our commercial version called Redis Enterprise, which actually does address many of the operational pain points that customers go through as they hit scaling limits, right? So with Redis Enterprise, we do have some of those capabilities, which you can learn more about. I know I have a little time here, but we're really excited about this opportunity. If you have a machine learning project and you're leveraging Redis today, or want to learn more about how to leverage it as an online store, evaluation store, or model store, feel free to reach out to us. There's a link here which actually provides a lot of details, a lot of examples about how Redis AI can be leveraged, including some of the packages and integrations that we have with MLflow and a variety of other open source tools. So thank you for the time. And once again, I appreciate the time.
Nice. Thank you so much. Actually, we're really good on time. You were like spot on. So I appreciate that. You made my job easy. And I love this quote, like people want something live, fresh, and fast is what you said, right?
Yep.
How did you figure that one out?
Well, that's really looking at how they leverage Redis to resolve certain pain points. And then you can really derive what they're looking for based on that, right? So it all comes down to those things, especially as you're building real-time AI, real-time capabilities.
Excellent. All right. Thanks again. That was awesome. I know lots of people love Redis, and there's definitely a reason for that. So
thanks.
That's all we got. Then we're going to keep on rolling. We're going to keep on cruising. And the next speaker for our lightning talk, I'm pleased to present and introduce David Louis. He is the head of ML at Pinterest. And wait, head of ML and Signal platforms at Pinterest. Sorry, I missed that part. David, forgive me. You're going to tell us more about how the machine learning platform team has been driving Pinterest engineering to a unified platform for the engineering organization. That sounds excellent. And I'm stoked to hear about Pinterest, what Pinterest is doing. You all have some incredible blogs that we've been reading a lot in the MLOps community. So take it away, David.
Yes, thank you. Very happy to speak to all of you today. Just get the presentation up. Okay, so everyone, my name is David Liu, and I'm head of ML and Signal platforms. The work I'm sharing today, though, is the collaboration of dozens of teams at Pinterest. So today, we're going to talk about how we've grown and eventually unified ML platforms over time. I'll introduce ML at Pinterest, talk about our layered approach to unifying machine learning, and then touch on some of the challenges that we've seen. So Pinterest is a visual discovery engine where people save and organize their ideas or pins into collections called boards. It covers a range of use cases like food, fashion, DIY, and decor. And of course, we operate at web scale with hundreds of billions of pins. So we have a really diverse set of ML applications, actually, which can be roughly categorized as large-scale online ranking and small to medium-scale use cases. Large-scale ranking is the most obvious class of ML on Pinterest. Anytime you see a grid of pins, like on the home feed, search, or related pins, we had to rank thousands of items behind the scenes to show the users the best ones within 100 milliseconds or so. So the scale is tens of millions of items every second, and this has very large infrastructure challenges. The other category is what we call small to medium scale machine learning. By most standards, these are still pretty large data sets, but the inference demands are a bit smaller. So every time a user takes an action, we need to perform a single inference. So this is used for things like image analysis, detecting suspicious logins, or extracting the subject matter of a pin. So the problem that we saw over time was that each team had independently evolved specific solutions for creating features and serving models. This led to a lot of custom infrastructure for each use case with a large maintenance cost and incomplete tooling. So our huge task was to unify these different use cases into a common infrastructure. One of the most important things that we learned was the approach to unification. We had to build a series of layers where each layer provided a foundation and standardized interface for the next. We started with unifying the feature representation, and that gave us a foundation for a common feature store. In turn, that enabled common inference and deployment solutions, and then model insights, analysis, and monitoring tools. So let's look at the feature representation first. Previously, each team had to prepare its own raw data in these custom and highly nested thrift structures, but there's no standardization. This meant that each team had complex decoding logic inside their models, and it blocked teams from sharing features as well. the approach we proposed was to define a standard container for storing features, which would be general enough for any kind of data. We separated the notion of data type, or the physical storage format, from the feature type, which is what that data represents. For example, the storage type could be a vector of ints, but those ints could represent either different dimensions of a dense numeric vector, or it could be a multi-categorical feature. So this feature representation greatly simplified the models because now we can provide well-defined conversions into the inputs for standard models like TensorFlow and PyTorch. This eliminates all of that custom parsing logic. Once we had the feature representation, the next logical step was to have a shared feature store. So we organized the features as a layered key value store where we can get features using an entity type, a key, and feature IDs. So for example, a user with a given ID, and then we can retrieve a feature that provides the country of that user. This standardized store is a foundation for many downstream tools. And one of the most valuable was being able to backfill previously collected training data. Previously, ML engineers commonly logged new features for several weeks in production in order to gather new training data sets. But a standard feature format and a shared store means they can start doing modeling experiments entirely offline and save weeks per iteration. The feature store also enables standardized inference, since the framework can now fetch these standard features and pass them into the models. And we built a feature catalog called Feature Hub, which I'll show you next. Feature Hub is our self-serve UI, and it enables users to do a lot of common tasks. They can browse and view all the metadata about the features. They can see which models use a feature, look up the value of the feature, and they can see whether it's available online. They can even see coverage and distribution stats about those features. There's a whole lot more functionality that we plan to add in the future. Now, one of the technologies underlying our feature store is our in-house signal platform called Galaxy. It's a standardized way for teams to share data sets with each other. And it's actually used for any sort of key value data about Pinterest entities, like pins, users, ads, and so on. But it's also a very convenient managed experience so that users can simply provide some business logic and configuration. And then we handle the scheduling of and execution of their workflow, storing and serving that data. So with this feature store, we began to build standard inference and deployment components. We use the open source MLflow for the standard model artifact format, as well as the model registry. And this gives us a standard way to track our models. We then have our own ML deploy and inference services built around MLflow and the feature store. One interesting architectural choice here is that in order to support the breadth of different use cases, we actually have multiple ways to deploy models. They're all built around our shared core inference engine called Scorpion Model Server. And the simplest deployment is to call it as a standalone service that does inference directly. This is really easy to set up for the smaller scale use cases. The other options can handle larger scale. So the first is embedding the model server component directly inside another C++ process, for example, inside our search index servers. So this achieves higher performance without incurring network transfer to gather features. The third option is to call our full service that performs feature fetching, caching, and scoring. The client just has to tell us which entities they're trying to score, and we'll fetch the features from our shared store automatically. And each request often spans thousands of items, so we actually fan out the work. And the machines form this sharded cache that maximizes the data locality and enables us to score tens of millions of items per second. Once all these use cases are on shared feature format models and inference approaches, it then becomes possible to build even more general shared tooling. So we're still relatively early in some of these, but we have things like real-time feature distribution and coverage monitoring, feature importance analysis, and model rollout monitoring. So now that we've seen this layered unification roadmap, let's discuss some of the challenges that we faced on the way. So it seems pretty simple to draw this idealized layer by layer approach now, but there's actually a huge inertia to existing systems, and it's pretty hard to get everyone to move onto this new system. First, product teams are usually under a lot of pressure to achieve their own business goals, and platform work will often require a short-term pause in order to go faster in the long run. Second, when we talk to people and ask them what they want, they often request these hyper-specific fixes to the current system. And this makes sense from their point of view because it might be the shortest edit distance solution to solve a particular pain point that they're having. But these factors mean you can end up in a local optima where it's not really possible to improve the overall platform without undergoing some temporary productivity hits. So it can take some real concerted effort to work towards a more ambitious general solution. So we figured out some approaches for these challenges. First, we need to figure out a technical path to have a shared foundation and have a step-by-step approach to migrating into this unified ecosystem. But this technical foundation is not enough. So we need various organizational approaches to make the migrations happen. First, when the immediate pain points are big enough, a bottom-up approach can actually work really well. Teams will have a strong incentive, for example, to save several weeks with each iteration if they are able to backfill their features, or they can begin sharing features from other teams. But at some point, it's also necessary to have this top-down alignment to escape the local optima, especially for the teams that are under the most intense business pressure. Leaders need to explicitly prioritize platform goals to give teams the room they need in order to pay down the technical debt of non-standardized infrastructure. Overall, we've made tremendous progress in this journey towards platform unification over the past several years. And I only had time to talk about a few of the projects we've done, but it was a pleasure to share these highlights with you today. Thanks.
Awesome. Thank you so much, David. That was great. I appreciate that. I mean, you all are doing some really cool stuff. So now we're going to take a break. We got another 10-minute break. And in the meantime, during this break, I know you all probably loved the meditation, but now we got to give away some swag. We got so much swag and we got to just give it away. My favorite part of the day is giving away some swag. Here we go. So there's been some fun stuff happening in the Slack, and we're going to go off of that. All right, let me share my screen and we're going to see who wins what with this new swag. All right, and in case you didn't see it, all right, you should see my screen now. In case you missed what you're going to be winning, you got some of this, you got some of this. It all depends on if you are chosen. So this is break 3. We're coming to the end of the day in conferences, and I know there are a few people that are in different time zones. So if you are not here right now and you win some swag, just reach out to me tomorrow when you're watching this replayed live on YouTube or whatever and say, hey, that was me you were talking about. So first up, most dedication goes to Niall. Niall, if you are still around, wow, it's like 6:30 a.m. local time for Niall. So round of applause for you. That is awesome that you stayed up late and you watched this. And so you get most dedication, you get some swag. All right, reach out to me. Let me know. Most helpful on Slack goes to Rohan Singh. Thank you, Rohan. You've been awesome at answering some of the questions, getting involved, being a part of this whole conference. So thank you, Rohan. You get some swag. All right, next up, this one's hilarious. I encourage everyone to go into the funny channel and look at Andre's selfie, the applied selfie. You get the most unhappy applied selfie award. I don't know if you're unhappy because you're at this conference or because you're wearing a costume. But you do not look stoked. The costume is A+. You get some swag, Andres. Go ahead, get that swag. We're going to send it out to you, and hopefully that will make you a bit happier. The next up, most creative applied selfie goes to Cedric Walter. Cedric, I think you are in Switzerland, and right now you're on the same time zone as me, so it's like 11 o'clock here. I don't know if you're still watching, but if you are, reach out to me. You get some swag. And then we've got the cutest pet applied selfie. Oh, and this name I'm probably going to butcher, but Amulya Badal, you get some swag. Reach out to me if you are still up and you're still watching this. That's all we got for now. Tomorrow, we're going to be giving away some swag first thing in the morning, because we are going to be talking about the best model gone rogue story. So if you have not filled out the poll, go ahead, fill it out and tell us about the best model gone rogue. We're going to be choosing from the poll, and we're going to, obviously it's anonymous, so we're just going to talk about that story. And if it is your story, we're going to use the honor system, and you're going to have to reach out to us and tell us, hey, that was my story. And we'll cross-reference it with a few of the other answers that you put, just to make sure nobody's trying to get that free swag unfairly, I should say. So there we go. That's the swag. Again, if you won, please reach out to me and I will put you in touch with the right people. For now, we've got another few minutes before we start with the new lightning round. So I'll let the slide go up for who is coming up next. I think we have Krishna Grade coming up next. And in a few minutes, I'll be right back and I'll introduce Krishna, and then we'll get cracking. All right. Congrats to everybody that won some swag. That should be fun. we've been getting some questions about these music that we've got going on here in the playlist. I will try to share the playlist with you all in case you're wondering. We'll throw that in Slack. So let's get cracking. Krishna, what's happening, man? It's good to have you here. I am pleased to introduce my man, Krishna. We've got a little history. You've come on the MLOps community meetup and blew my mind. So I'm excited to see what you got here. I'll just let you get into it. You're the CEO of Fiddler, who will be describing a new way to ensure high quality model performance with a centralized ML model performance management framework powered by explainable AI. All right, Krishna, let's hear it, man.
Awesome. Thank you, Dimitrios. Nice to meet you again here. Let me share my screen and start the presentation. This is the 10-minute talk. Okay, so today I'm going to talk about model performance management that we're working on at Fiddler using explainability. Just as a brief overview of the company, we are a startup in the Bay Area. We've been around for 2.5 years. We're building this pluggable product that can monitor and explain machine learning models in production today, agnostic to different model types, agnostic to different data sources, and helps teams to continuously manage models and monitor them and explain them in production. Why are we doing what we are doing? A lot of teams are deploying AI today, right? And there are 4 main challenges that we see them run into. Number one is model transparency. A lot of the models that people are deploying are highly complex machine learning and deep learning models. And these days, a lot of organizations are being held accountable to disclose how these algorithms are working, and sort of from both internal people and external stakeholders. And so there's a lot of sort of emerging need around creating transparency into how the models are working across organizations. The other problem, as you all know, is models are stochastic entities, and they drift in their performance when they're deployed, and a lot of teams actually face these issues during the coronavirus. Especially, a lot of teams actually blogged about models losing accuracy post coronavirus, and not having proper monitoring is a big deal. Model bias, this is a huge topic of interest these days across many teams and companies. As models get trained across various different types of data sets, bias could creep into the models either directly or through a proxy. And we've seen many incidents in the past where customers complain about ethnic bias, gender bias, in terms of AI products that they're working with. Compliance is a huge topic. A section of the industry, especially from financial services, healthcare, needs to deal with it day in, day out. And if you have non-compliant models, then obviously it can be like huge litigation and sort of fines can be levied upon. The fundamental problem behind all of this, as you know, is machine learning models are error prone, right? So they, as you know, like when you deploy those models, they can lose performance over time. You can have accuracy dips because of change in user behavior, change in the way the data is actually being processed by the models. Data drift is one of the primary reasons for that. A lot of people have been talking about it these days. You train a model and you deploy it, and the data distribution shifts between production and training, and you see that is affecting the predictive power of the model sometimes. Data integrity, the data quality of the inputs that the model receives is a problem in terms of hurting model performance. We see a lot of times that model performance actually is determined by the quality of inputs that the model is receiving. If you're receiving like null values, missing features, or things that are in a garbage manner, then the models are not necessarily going to process them in a way that you expect. Bias, we talked about it. Transparency. A lot of these models today, we work with highly complex models, deep neural networks, hybrid models, a mix of multi-model inputs like text and tabular inputs that models are processing, and they're very difficult to debug and understand what's going on. So the interesting thing is, despite all these problems, all of you probably who joined this conference and everyone out there are still deploying and going ahead and deploying those models, right? And that sort of puts these teams at 2 big risks, right? One is not having proper monitoring into how the model performance is doing, or week over week, day over day. and then not having the right tools to troubleshoot models when you run into performance issues. And that's basically what we're trying to build at Fiddler. You can think about Fiddler as like a Datadog or a Tableau for machine learning and AI. It's a visual analytics tool that captures all of your model performance data, helps you provide visibility across those models, helps you track bias, helps you set up alerts so that when things go wrong, you can actually go and come and check the dashboards and explain how the model is performing, diagnose the model performance. It's built for the data scientists, built for machine learning engineers, and it's a pluggable module within your machine learning workflow. The way you can attach Fiddler today is you can have your traditional machine learning platform that you're using to train your models and that you're using to serve your models. There are many machine learning platforms out there, SageMaker and other custom machine learning platforms that teams roll out. Literally, some of our customers are able to plug Fiddler as a sidecar to their models so that they can continuously monitor, analyze, and validate these models during this process. And this helps basically close the loop in terms of for their machine learning workflow and illuminate like this model black box, right? So by being able to validate the models after training and being able to monitor them during production and being able to analyze the model performance using explainability is what we are trying to offer here. The vision for us is to take this MPM system and bake it as a centralized component throughout the ML lifecycle so that teams can use it throughout the ML lifecycle and benefit from it. For example, some of our customers use the system to track bias in their training sets and track feature quality, validate models and generate model performance reports, explain them after they're trained. This is obviously very important in a regulated industry. Compare model performance across pre-production and post-production models, observe the model performance over a period of time, set up alerts on different conditions, and then analyze false positives or other things that might emerge as models start running in production. The holy grail for us is to be able to close this feedback loop so that when you're analyzing model performance issues, let's say you find a region of data points where the model is not performing well, use explainability to understand more and therefore and close the feedback loop so that you can either generate better training data sets or better model architectures to fix those issues. And that's the vision that we are working towards. The goal for the MPM is to reduce these operational risks that I talked about, right? Performance degradation risks, bias risks, data quality risks that could hurt model performance and actually hurt your business metrics and hurt your customer trust in the future. We have several customers across various different industries, financial services, e-commerce, ad tech, that are using the platform today as a centralized model monitoring and a validation system across the board. Different types of models, search and recommendation models, anti-fraud models, promotion type models, lending and fraud detection models. The experience is built such that it can serve not only the data science teams, but also related teams like the product teams that work with the data scientists. Oftentimes, a lot of product teams ask a question like, hey, I'm getting this prediction or I'm seeing this model performance issue. Why is this happening? And a lot of times data scientists don't have ready-made answers. And when things do go wrong, when customers complain about ML-based products, there's like a scramble that sort of data scientists will go through to reproduce the issues, right? So Fiddler makes it easy because you can actually collecting all of the model production logs in one place, so you can go back in time and reproduce the issue and understand why a model performance has affected a single data point or a group of data points, and then root cause analysis, the behavior there. And the goal is to serve not just the data scientists, but also the stakeholders that they're working with so that they can consume these insights and sort of democratize the understandability of models across the organization. That's basically it. We are here to help companies transform their AI into a trusted platform so that they can build lots and lots of more models and deploy them into production in a safe and responsible manner, and then do it right for their business as well as for their end users. Thank you so much. If you have any questions, I'm here to answer. You can also reach out to me at krishna@fiddler.ai, or we have a general email address, info@fiddler.ai. Happy to talk more.
Krishna, you're making my life easy. You are right on time.
Absolutely.
I love it. Thank you.
Dimitris.
And I appreciate the insights. So we got another lightning talk coming up. We just keep on rolling, hitting the punches. And Hendrik, what's going on, man? Good to see you here.
Hey, I'm good.
Got
How are you
up
doing?
late, huh?
Yes, 10:20.
Yep, I see that. So for those who do not know who Hendrik is, he's the Director of Data Science and Analytics at Tide. He's going to introduce us to Tide and how they decided to move forward with a feature store. Now, we've talked before, Hendrik, and so I will give a short little plug. If anyone wants to see a deeper dive on this, go to the MLOps community YouTube page and you will get all of this and more. But for now, here's a little taste from Hendrik. Go ahead, take it over, Hendrik.
Yeah, thanks a lot, Dimitros. Yeah, so welcome everyone. So I'm Hendrik. I'm leading the data team at Tide, and I'm going to give you a brief overview of our journey with feature stores. So what are we going to talk about? So briefly, who is Tide? How did we start with ML at Tide? Where are we now? And what is next for us? So who is Tide? So we are a financial platform for really small businesses. So think of it as a Revolut or a Monzo, but for businesses only. So you can register your business through Tide and then do all of your financial needs directly through the platform. So first of all, the bank account, but then also invoicing, expense management, credit, and a variety of other services are directly available through one platform. I think one idea that really illustrates that well is this, what we call internally connectivity chains. So for example, you might be an architect, you buy some supplies, you pay with your Tide card, you then upload some receipt for that payment. We extract that information from that receipt, match it against the payment. We use that to fill in an invoice that you can send to your client in order to pay for this. The invoice might be against your client that might not be of good creditworthiness. So we identify that, automatically give you the option to buy some insurance against that. And then once your invoice is out, we make sure it's being chased so that you actually get payment. And once the payment comes in, we reconcile that directly against the payment as well. And I think from a data perspective, this is really, really exciting because all of these different processes generate a lot of data. And also there's a lot of different machine learning applications across the flow. So for example, the receipt information extraction is a machine learning application, creditworthiness identification, and the payment matching as well. So how did we get started with machine learning at Tide? Well, the very first application we had was actually from our onboarding flow. So trying to identify what are fraudulent or non-fraudulent companies, what are the companies that we could accept directly or not. So what are the problems that we faced when we investigated the current solution? Well, we saw that there wasn't like a data layer or wide data layer available in real time. So we had the data warehouse, which was having much lower freshness requirements. The system that was needed to be put in production was a mixture of both machine learning and rules. And then also, like a lot of what the existing system had, a lot of the deployments resulted in unexpected changes that were not great. So the ideas that we had is we should build a feature store to make the data available in real time, build out the feature layer such that it will not only serve this machine learning models, but it will also serve the rules layer. And finally, we wanted to have some shadowing functionality in place as well, in order to make sure that we can actually log different data points before they reach the live systems. So what we ended up building looked something like this. So we had different data producing services, all raising events onto a stream. Then we had stream processors that were looking at the different data sources one by one and computing parts of a feature vector. And then we had a central entity that was taking all these parts, kind of upserting that into a really large feature vector. And it had some kind of like awareness over when a feature vector would be completed. which would then be streamed out again into this object that was actually applying this machine learning and rules object to the full feature vector, which was then again being consumed by some kind of external service. The offline architecture at that point was completely separate. So this ran all against our data warehouse, and the whole training data pipeline was very much separated from the operational flow. So this is how we started. Since then, we discovered a number of problems. I listed 3 here. I really wish it would have only been 3. So the 3 that I want to point out was that we found a lot of issues around the streaming data not being available since the very beginning, but only since some point in time. So we needed to very much reconcile historical with streaming data. We also found that the training and production pipelines were separate, completely separate, causing a number of bugs due to separate implementations, and the handover process between engineers who were working on the real-time pipelines as well and the data scientists working on the training pipelines caused a lot of delays as well. So we thought a lot about how to deal with this, and we thought about adding in additional features and looked at commercial solutions. And then in the end, we decided to go for Tekton. So how does Tekton actually help us with these 3 problems? So the first one is they make it very easy to have a Lambda type implementation where you can unite streaming data and batch sources. The second one is they give you some kind of contract of an entity, like for example, that unites streaming and batch sources, and you can write all your feature transformations against that, making any diversions in implementations very unlikely. And lastly, all of that is actually simple enough that data scientists can do that reasonably safely as well. And so how does our infrastructure look like at this point? So we again have the data producing services. We then enhance that with various external data sources, so think like credit rating agencies and so on. All of that data flows into Tekton. Tekton also connects to the data warehouse in order to make the streaming and batch aggregation. That data then flows into various feature services, prediction services, still applying these rules and machine learning systems to them, which are then being consumed by various downstream consumers. In terms of offline architecture, there was a major change as well, in the sense that the training data now could actually could be created using the same pipelines as were used for online serving. So you can see here that the Tekton was serving our real-time training data in the production environment as well. We made a number of other changes as well. As you can see, for example, we replaced our initial versioning with MLflow, but they are not really the main focus of this talk. So what's next for us? So really we see a lot of problems, but 3 again that I want to point out here. So the first one is that we still spend a lot of time building these production services. So something that we are looking at automating further. And the second one is on the monitoring side, we want to further standardize and expand our capabilities. So at the moment, what we're doing is very much use case dependent. And lastly, also on these external data integrations, we see at the moment they are very use case dependent, specifically on the freshness requirements, and something that we'd like to unify more, such that they're easier to reuse across different use cases. And with that, I touched on a lot of topics very, very quickly, which is, I think, in the spirit of this talk. If you have any further questions, please join in the discussions within Slack, reach out on LinkedIn or any other way. I'm always happy to discuss any of these issues with you directly.
Awesome. Thank you, Hendrik. We should probably mention that you have a really cool meetup going on too.
Yes, we have a meetup called FinML. There's a Substack if you want to go to finml.substack.com and sign up. There are there's another great opportunity to learn more about machine learning. I think the next one we have planned is around multi-armed bandits and A/B testing. And then there's something more about explainability as well. So please sign up. It's really exciting stuff.
Yeah, definitely doing some cool stuff in this space. I'm happy to see it. And thanks for staying up late, Hendrik. All right. Well, that is the next one. People are asking for links to the meetup. We'll put that in Slack, I imagine. So now we have the next talk coming at you. This is from Kai. He is a field CTO at Confluent who compares a modern streaming architecture to traditional batch and big data alternatives, then achieving a scalable, mission-critical machine learning architecture with Apache Kafka. That sounds like quite the talk. It's also got a little bit of tiered storage involved and TensorFlow. All right, so up next, we've got Kai coming on.
Hey everybody, this is Kai Wehner from Confluent. Today I want to talk about streaming machine learning with Apache Kafka and its ecosystem. This way you can deploy machine learning in the real world without using another data lake. So let's get started with the session. So today in this short session, I will talk about an example with connected cars. This is perfect for streaming a lot of huge volumes of data and process it. For example, for doing predictive maintenance or after sales in this business case. In this example here, we don't have machine learning in here. So this is just a streaming pipeline, like how many people start to build that. You collect a lot of data from many different interfaces, then you process it and ingest it into other systems. These other systems can also be built with the streaming platform, like a real-time monitoring system, or they can be batch analytics platforms, like a data lake, like Spark or something like that. So that's totally up to you and very flexible. But this is how you often build your pipeline from the beginning. And then the good news is to add machine learning to that. It's really not that complex. You just add a few other consumers which use the data. Like in this example now, we have added machine learning here in green. And machine learning, as you probably know, is always two steps. It's the model training part, which we do here in the middle. So here we consume a lot of data from the streaming platform. In this case, it's the historical data from a lot of cars. And then we use that to train an analytic model with any favorite technology like TensorFlow or H2O or a cloud service. And then separated from that, we need to deploy the model somewhere. In this example on the right side, we just enhance an already existing application and use the analytic model to do inference here. So in this case, the business logic is improved. And that's what I see in the real world a lot. It's not just about building completely new use cases like a chatbot with deep learning, but it's also about improving existing applications which use other business logic before machine learning. So in this architecture, you see how easy it is to complement a streaming platform with machine learning technologies. So let's now go a little bit deeper into that. When we talk about a streaming platform, actually, in most cases, we talk about Apache Kafka, which is the de facto standard around the world in the end. And what's important, even if you know Kafka for ingestion layer into a data lake for machine learning, Kafka is much more than that. The heart of it is a combination of messaging and storage for huge volumes of data, but still providing a reliable fault-tolerant system at scale. And with that in mind, you can build mission-critical workloads. So the ingestion into a data lake is just a fraction of use cases. We see really customers deploying machine learning, but also many other mission-critical workloads with Kafka. And also it provides connectivity with Kafka Connect. So you can integrate to all these different sources and things. And last but not least, you can also process the data continuously with Kafka streams. That's all part of Apache Kafka. And that's what many people don't know from the beginning. They only use Kafka as ingestion layer and don't use all these other benefits. But that's what we will do here today. So if you take a look at Kafka from the machine learning perspective, it's very complementary, as you can see here. I mean, machine learning is always starting with model training. So you collect data, you transform it, and then you have a batch process for doing model training. So here, Kafka is a perfect solution for doing the integration to that before you train the model with your Python code or Jupyter Notebook or something like that. But in addition to that, you also need to deploy the model to production. And this is also very often done with Kafka, because here it makes so much sense to have low latency, high reliability, and all of that around Apache Kafka. So in addition to the messaging platform in the middle, in most machine learning projects I've seen around Kafka, also other components are used. For example, the connectors to connect to the streaming data from the IoT systems, or to ingest the data into another data lake or database. So that's totally up to you how you architect it. But with machine learning, you can help the integration layer for model training, but also the model inference layer. And in addition to these two important layers, also about the monitoring and observability of your training and of your scoring pipeline. So this is why we see so much Kafka in machine learning projects these days. Well, and in the model training part, we also see that many people don't use a data lake anymore. You don't need something like HDFS or S3 in addition to Kafka. You can do that, of course, like training a model with Spark then. But also what's possible today, that you connect directly from your machine learning framework to the Kafka stream of data. Like in this example where we use TensorFlow IO to directly put the TensorFlow engine and connect it to Kafka without another data lake in the middle. This totally simplifies your architecture and makes it less costly. So for many use cases, you don't need another data lake just for machine learning. And the other important part where we see this more and more is that now you can also use tiered storage for the Kafka. With that, you can store data forever in Kafka, like in your favorite data lake like Hadoop. Because it's also an object store under the hood in the same way. So you have low cost, but still can store all the data and scale this. And with this in mind, you can use Kafka not just for real-time data, but also for the decoupling and for processing historical data, like for model training. So this is why tiered storage is such a great game changer for Kafka. This example here is from Confluent, which we use in production in our cloud service and provided for our customers using our self-managed platform. But the good news is also that tiered storage is also coming into Apache Kafka. While I'm doing this recording, some of the first code was already merged into the Kafka trunk. So this is coming into open source too as an interface with tiered storage. And Confluent is working together with other people from the community. Uber has the lead for this tiered storage kit. So this is coming soon, and this is really great for the community. In addition to doing the model training, maybe in the cloud where you can scale up new instances easily for model training in batch, the model deployment is often completely separated. Low latency, closer to the edge, with different SLAs than the model training, because this is really the mission critical workloads. With Kafka, this is very easy because you can separate this and deploy this in a hybrid architecture, for example. And as part of this now, with model scoring, it's really super easy to do that with Kafka and your favorite machine learning framework. In this example, we're using KSQLDB, a stream processing engine, which is Kafka native. And here you see it's a very small query, but very powerful. With this query, we have embedded a TensorFlow model into that. And we're doing streaming machine learning at real time for scale, for millions of events with just this query here. So this is how powerful this is. And so to conclude this short session here, this is our architecture with all the Kafka components, like you've seen in the picture in the introduction. So here we're using Kafka connectivity to the IoT layer, but also to the databases, and also for using it with TensorFlow in this example, for both model training and model scoring. All of that without the need for another data lake like Hadoop or Spark or something like that. So this is not always the best option, but you should be aware of it to simplify your architecture where it makes sense. I've also built a lot of demos for that regarding Kafka together with different machine learning frameworks like H2O, TensorFlow, and more. Take a look at that. There is very simple examples, but also an example about the connected car infrastructure, connecting to 100,000 cars and training data with TensorFlow there. That was my session. I hope you liked it. So feel free to reach out to me on LinkedIn and Twitter to stay in touch and let me know if you have any feedback about using Kafka together with machine learning. Thanks for listening.
Thank you, Kai. Awesome. Exciting stuff. Next up, and our last presenter of the day, we've got him staying up real late, coming all the way from Israel. And it's like 1 a.m. where you're at, right? Or
yeah, it's almost 1 a.m.
That's awesome, man. Well, I appreciate the dedication and thank you for coming on here to talk to us about what you got going on at Lemonade. Let's just give you a quick introduction and then we can jump in. You're the machine learning engineering team lead at Lemonade, and you're going to recommend how to use point in time as a first-class citizen on your machine learning platform while still striving to maximize the use of your older, messier data. That's awesome. Or I'm gonna set the stage for you. You're gonna be the last talk, and then we'll wrap it up after this. So take it away. Take us home, Or.
Hello. Thanks, Demetrius, for the introduction. Today, we're going to be talking about point-in-time data or immutable data in online inference. A quick intro. I'm Oren. I'm a software engineer, and I lead the work on Lemonade's machine learning platform. And Lemonade is a full-stack digital-first insurance company driven by automation and behavioral economics. So let's start with an example business database or business application database. Let's say we have a users table with several columns and the transactions table with several columns as well. And we have many transactions per user. One day a new user is created or they add themselves to our table. Then that user makes a transaction. And finally, that user changes some of their data. Down the line, we decide to make predictions during transaction, online predictions during transaction. But the data in the business database has changed. We need the values at time of transaction to train on because we plan to predict at this time in the business process. This notion of a business point in time will seem quite obvious to anyone making online predictions. In our example, the date of birth was null during our prediction, but in our current database, it's now, there's a value there. So there are a number of ways to capture this point-in-time data. They're a little bit less relevant for this talk, but in general, we can do it in our application or in our infrastructure. In our application, we'll probably use events in some way, or in our infrastructure, we can either use change data capture, maybe read the bin log somehow, or worst of all, snapshots, which are probably not granular enough, but we may all have them from some time in the past. So the point in time is a training data notion. I just want to reiterate, during inference time, we get the most recent values, but during training time, we need to recreate data identical to the one we would see at inference. And we'll see momentarily how we can benefit from this point in time. So let's try to define the business point in time as entity values at the time of a business process. Each point in time is dependent on a single entity's column. So for example, maybe if it was a transaction created point in time, it would be the timestamp of when the transaction was created. There's a different timestamp for each entity row. So maybe the transaction time would be different for each row, and then the users table, maybe we would even have, I don't know, multiple views of the same user for each transaction that they made for different timestamps. And most importantly, there are only several of these per business, which we'll see in a few moments how we can create some really cool applications from this. We'll compare the business point in time to snapshots just to make things a little bit more clear. So in the business point in time, there's a timestamp. The timestamp is from the entity. So like we said in the example, maybe when the transaction was created. And then there's a different timestamp per entity. When the snapshot, the timestamp is the same for the whole snapshot. Maybe we had we have daily snapshots, and this whole table is from August 1st, 2020. There are only several business points in time. And you only have to materialize each row once per entity per point in time, whereas per snapshots, you'd have many, many copies and you'd materialize them depending on the granularity. An example of this is if our business was, maybe we have a SaaS business, we have new users sign up, they purchase something, and maybe they cancel their subscription at some point. And we want to make predictions only when new users sign up, when they purchase things, and when they cancel their prediction, and when they cancel their subscription. So I've heard a lot of talk about abstract point in time or maybe time travel, and that's great for a lot of requirements, but we realized that our data scientists actually don't want the freedom to time travel anywhere, only to several specific points in time in our business funnel. And once we understood this, we were able to create abstractions for these specific or non-generic cases, which not only provided less room to make mistakes, but also resulted in some really cool applications. And let's look at several of these. So the first application is to monitor real-time feature service level indicators. So let's say our business application is streaming events and our feature store is processing them into a real-time store in a data warehouse. And then our business application, either through a model or directly, makes some synchronous request to the feature store to get features in order to make a prediction. This can lead to a race condition since the events are processed asynchronously, and this request is made synchronously. An example is maybe we're counting clicks, we're aggregating the number of clicks on some button, and we want to validate that our pipeline processes this aggregation correctly by the time we request the feature. So our feature store will maybe create a sum for these clicks that you can see. And we want to know that we've processed them on time by the time that we make this request. So how do we do this? In the green line, you can see is described the time between when we send the event and when the point in time when we actually synchronously request the features. And our goal is to detect race conditions which result in missing or outdated features. So the steps we've taken in our platform are as follows. Since the machine learning platform supports only a closed set of points in time, feature authors will configure the point in time availability per feature or when they expect a feature to be available. Then the business logic or our actual business application will tell the machine learning platform that a point in time has arrived for each entity where there's a point in time. The platform will calculate all of the features, but for some subset of entities and log them to the data warehouse. And finally, we'll materialize training data and compare that to the real-time inference data that we've created. So consequently, we can know the damage and make an educated decision, whether to synchronously put a feature and maybe not use the feature at all, or decide on any other solution. The drawback to this approach would mean that a feature needs to be productionized or authored before we can validate its correctness. It actually has to be in production, but it only takes several hours within feature authoring to know if a feature is available within a certain point in time, well before any model actually uses it or data scientist decides to use it in a model. So the next application of specific points in time is in communication. So with our stakeholders, the point in time is now part of the model contract, and the stakeholder knows when the model should be used. So this is decided on well before the model is created between the data scientist and the stakeholder. And this allows the consumer to know where in the business logic to use the model and the data scientist to guarantee its SLA. Within the platform, we'll have the point in time all through the machine learning lifecycle, whether it be in research, training and inference development, or monitoring. And this allows the platform to be consistent in its data quality guarantees. And finally, I think the coolest application is to be able to backfill legacy data in a sort of generic way by manually testing and backfilling per point in time. So let's say we're still creating these snapshots that we have from the past. We can now materialize or try to create data manually from these snapshots, or point in time data manually from these snapshots for each type of business point in time that we have. Then we can use our feature store, which obviously can materialize and works with time travel to materialize this same type of data from the feature store. Let's say we're materializing it for the past month, both from our snapshots and from the feature store. And then we can compare these rows from the legacy data to the current data systems. And we can make a calculated or an educated decision whether we want to backfill the data, whether it's good enough to actually train on, or to just throw away this data because it's not good enough, or do something else. But this only has to be done once because we only have several points in time, and not with every new use case. So this is a big time saver for data scientists. So in conclusion, if you're making online predictions, consider making the business point in time part of your machine learning platform. We don't have time for questions, but I will be on the Tekton Slack for the next several minutes or on LinkedIn or email. Thank you so much for your time.
You are actually a little under time. I mean, we could do one question maybe if you wanted.
Let's do a question.
It's surprisingly coherent for how late it is there and you presenting from your bed. I can't believe it.
Actually went into the office.
Nice. So let's see who's got some question for us. Let me just go in and check if there are any. It seems like I'm not finding anything yet. No, I don't see anything. Nobody's got questions here. I guess that's what we're gonna finish it with. Now that we say it, we'll pause. We'll wait for the delay on YouTube. We'll see if anybody's got one. All right, here we go. One question from Ron. Ron's not gonna let us down. Right on. How many snapshots do we need or were needed?
So hopefully you're still creating snapshots. You kind of want to recreate the snapshots that you had in your legacy data. So the point is to backfill data from the past, but you want to prove that that data is good. And so you want to keep using the same granularity that you had. And then once you find out that this data is good, you can maybe get rid of these snapshots. So it really depends on the granularity you had in the past.
Excellent. There we go. So people are saying it was a great talk. That's what I'm seeing. They're saying no questions. That equals perfect talk. Excellent, man. Well, I appreciate you coming on here super late your time, super late my time. We are ready to wrap this up. And if anyone else has questions that they think of, or I imagine you'll be on and off of Slack tomorrow. Is that correct?
Yeah.
You'll be around. Nice. So when this all sinks in and you're having your shower later today and you say, oh, I wanted to ask or something, he'll be on Slack. Jump onto Slack and ask him some questions. Thanks again, man. This was super info and really cool to see how you all are doing it.
Thank you so much.
All right, take care. Now we're going to wrap it up. This means there are only a few announcements before we close it off and we say done for the day. It's been an awesome day. I've had an incredible time with you all. Thank you for joining us. The last announcement is that we have a few more awards for some swag, but this time it's going to the presenters. So presenters, get ready. I don't know if they're still around or not, but we'll see what they get. The swag that the presenters get from your poll. All right. And it's a little unfair because Orr just presented and he potentially could have won something, but since he was later, I know. So if you want to vote for Orr tomorrow, vote for him. Now let's see. What do we have for the wrap up? Most informative talk goes to Dr. Waleed. You're getting some swag. Waleed's getting some swag. If you're still around, Waleed, let me know. Reach out to me and we'll get you some swag. The most entertaining talk, goes to the guys over at Netflix. Nice. Jan and Ravi, if you guys are still here, let me know. You win the most entertaining talk award. Congratulations. I'm glad I didn't spoil that one for you with the slide. It's an epic slide though. All right, the best slides. Ooh, here's one. Stefan, if you're still around, let me know. Reach out to me and you'll get some swag. All right, best slides award goes to Stefan for Hamilton. Sweet. So now, last thing I will mention, complete the survey after each day. We want to know how we're doing. This is going to be super helpful for us to know the production side, what we could have done better. If you didn't like the meditation, if you did like the meditation, let us know. You can be totally candid. I think it is anonymous. Don't quote me on that one though, but it will be awesome to hear your feedback. Give us your honest truth, please, because that way we all can get better. Now, I think that's about it for today. The last thing, I keep saying the last thing. Last thing is that if there's enough interest, I think tomorrow we are looking at doing an after hours Clubhouse session. And it's not going to be me doing it because it's super late where I'm at, but there's some people from the MLOps community that might organize it if there's interest. So if there is interest for that, where everyone can get involved and talk about what they learned over the last couple of days, let us know. Let's put it in the chat and say, yes, I want to be involved. If nobody says anything, we're just going to pretend like that never happened and say, all right, cool. We'll go to bed or we'll go and have lunch wherever you are in the world or breakfast. That's about it. All right. We'll see you tomorrow for more of this. We got more swag tomorrow. We got more great talks. I appreciate everyone. No more meditation, but I will be playing guitar. You see the guitars back there. I'm going to play something. That'll be fun. And yeah, that's it. Congrats, everyone. You made it through day 1 of the Apply conference. See you all later.
Bye.